Hey, I'm Frank Kane, and I spent over 9 years at Amazon.com and IMDb.com making sense of their massive data sets, and I want to teach you about the most powerful technology I know for wrangling big data in the cloud today. That's Apache Spark using the Scala programming language. Spark can run on a Hadoop cluster to spread out massive data analysis and machine learning tasks in the cloud, and knowing how to do that is a very hot skill to have right now. We'll start off with a crash course in the Scala programming language. Don't worry, it's pretty easy to pick up as long as you've done some programming or scripting before. We'll start with some simple examples, but work our way up to more complicated and interesting examples using real massive data sets. By the end of this course, you'll have gone hands-on with over 15 real examples, and you'll be comfortable with writing, debugging, and running your own Spark applications using Scala. And some of them are pretty fun. We'll look at a social network of superheroes and use that data to figure out who is the Kevin Bacon of the superhero universe. We'll also look at 1 million movie ratings from real people and actually construct a real movie recommendation engine that runs on a Spark cluster in the cloud using Amazon's Elastic MapReduce service. We'll also do some big machine learning tasks using Spark's MLlib library, and we'll do some graph analysis using Spark's GraphX library. So give it a try with me. I think you'll be surprised at how just a few lines of code can kick off a massive complex data analysis job on a cluster using Spark. So let's get started. First thing we need to do is install the software we need, so let's get that out of the way right now. So let's dive right in and install the stuff you need for this course. First thing we're going to do is install a Java development kit because Spark is built on top of the Scala programming language, which in turn compiles down to Java bytecode, so we need a Java environment to run it. We'll then install the Spark package itself, and there's a few extra steps we have to do in there for Windows in particular, and a bunch of environment variables we have to set as well. And we'll install the Scala IDE, which is just a special version of Eclipse built for Scala. Now, if you want to follow along, I have written instructions at this download link here that you can get all the details at, so you don't have to follow along at the same pace if you don't have to. And I've also included installation tips for Mac OS and Linux on there as well. Now, what we're going to do right now is walk through installing this on Windows. So if you're on a Windows platform, just keep on watching and I'll walk you through what to do. So let's do it. So let's just plow through this, shall we? First thing we're going to do is install a JDK. So if you head over to oracle.com, you should be able to find the Java downloads page. There'll be a link to all these things in the external resources for the lecture as well, so you don't have to copy these down if you don't want to, but just search for JDK and it will bring you to this page. We're going to download the latest JDK for your specific operating system. I'm on 64-bit Windows, so I'm just going to grab this guy right here. After accepting the license agreement, and we'll let that come down. And now that that's downloaded, let's go ahead and run it. Typical Windows installer. Now, something that's a little bit unusual though is that it's actually going to install two things, a Java runtime environment and a Java development kit. And we're going to have to remember where we put the Java development kit because we need to set an environment variable for that shortly. So we'll just walk through this and you can pretty much accept the defaults, but again, this is the magic path that we're going to need to find later. So remember where that went because we're going to need to find that path later on. And we'll just walk through this. Skip ahead a little bit through the magic of video editing. And there we have it. Our JDK and Java runtime environment are installed. So let's move on to the next step. Let's go ahead and get Spark itself, shall we? So if we head over to spark.apache.org/downloads.html, you should find a page that looks like this. And I want you to get at least Spark version 2.0. You will need that at a minimum to run this course successfully. And you want to make sure you have a pre-built version of it. So make sure it's pre-built for Hadoop something. It doesn't really matter what version on Windows. So we want a direct download and we'll just go ahead and use that link that they give us and suck that down. Now what it's bringing down here is a TGZ file. That's a Unix compression format, kind of like a zip file on Windows, but Windows doesn't come with TGZ file support built in. So you might have to go and download a third-party utility to actually decompress this file on Windows. If you don't have one already, one I use is called WinRAR, and you can download that from rarlab.com/download.htm, just like this, and download the version for your operating system, for example, 64-bit Windows. So once you have that installed, you can actually right-click on these things and install them from the Explorer. So let's go ahead and do that. Navigate to my Downloads folder, and we will right-click on Spark 2.0.tgz, extract to this folder. And if we open that up and open that up, we have Spark itself. And what we need to do is put this somewhere safe. You probably don't want to keep this in your downloads folder. So let's go ahead and select all here with Control A and copy it all with Control C. And I'm going to put it in a folder on my C drive. So I'm going to open up my C drive and make a new folder called Spark. So I'm inside my C Spark folder here, and I'm going to paste in the contents of the Spark directory. And there we have it. So it should look like this at this point. We have a C Spark folder, and inside of it we had a bin folder, conf folder, and so on and so forth. And that is Spark itself. And the beauty of it is that since it's all built on Scala, which is built on top of Java, it all just works. You don't need a special Windows version or anything. Now we're going to do a little bit of tweaking of the configuration here. So open up the conf folder here. And I want you to make sure that on the View tab here, the file name extensions is checked off. Otherwise, you'll get confused. So you should see a folder that says log4j.properties.template. I want you to click on that. And take off the .template. Yeah, I'm sure. Now, I already have properties files associated with WordPad, but you might have to right-click on this and say Open With and specify something like WordPad to edit that file. So go ahead and do so, and you should see something like this. What I want you to do is change this info here to error. And that will just change the log level of Spark for you. It'll drive you a little bit less crazy that way. So trust me, you want to do that. Save that and quit it. And we have configured things to our heart's desire. Now, one thing specific to Windows that's a little bit quirky is we need to trick Spark into thinking that Hadoop is present. And obviously, you're not actually running a Hadoop cluster on your Windows desktop, but there's one little piece that we need to install to kind of make Spark believe that there is. And if you go to this link here, and again, this link is in the external resources for this lecture and also in the written instructions here, go ahead and download that. Yes, it's an executable file. No, there's no virus in it, I promise. If you want to go find this on some other site just to make yourself feel better, go ahead, but whatever. So we should have a winutils.exe file here in our downloads. I'm going to copy that, and I'm going to go back to my C drive and create a new folder called winutils, just like that. Open that up and create a folder inside winutils called bin, just like that. And if I go inside there, so at this point I should be in C winutils bin, and copy that winutils.exe file that I just downloaded into there. Okay, so make sure this is all exactly right. One little mistake is all it takes to mess this whole thing up. All right, so let's go and set the environment variables that we need right now. So to do that, I'm going to right-click on the Windows icon here and go to Control Panel. Click on System and Security. Click on System. And from there, click on Advanced System Settings. And there, finally, we have our environment variables button. So hit that. So let's set up a few new user environment variables here. So go ahead and click the New button here on the top part of this screen. And first thing we're going to enter is Spark_home, just like that. Make sure it's all uppercase, Spark_home. And what we're going to put in here is the path we put our Spark installation into, which was C:\Spark, just like that. All right, we're also going to set up Java home if you don't already have one. And that's going to be where we install Java to in the first step. So to remind yourself of that, you might have to go back to your program files directory here and look for Java. And that is where we put it. So we want this path right here. A little trick, you can click up here and copy it out of the Explorer and paste it in there. I also could have hit the browse directory folder and found it that way if I wanted to. All right. Now we also need to set up Hadoop home, just like that, Hadoop_home, and that's going to be where we put the winutils stuff. So that's going to be C:\winutils. And finally, we need to adjust our path. So you should already have a path directory. If not, create one and hit Edit. And we're going to add two things to the path here. Hit New. First one's going to be %sign Spark_home %sign \bin. Okay, just like that. Hit New again, and we'll also add in %sign Java_home %sign \bin. All right. So double check. This is all very important to get right. We have a Spark home set to C Spark. We have a Java home set to where we install Java. We have Hadoop home set to C winutils, and our path again has %Spark_home %\bin and Java home \bin as well. Okay. Go ahead and OK out of all this stuff. We're done with our system environment variables now. And what we're going to do next is install the Scala IDE. So if I head over to scala-ide.org, I can click the big friendly download IDE button for my operating system, which is going to be, for me, Windows 64-bit. And we'll wait for that to come down. Okay, so if I open this up in my downloads folder, you'll see it's just a big old zip file, and I can just right-click on that and extract it. And the beauty of the Scala IDE is that it too is just built on top of Java, so there's nothing special to install, it's just a bunch of files. So let's go ahead and let that decompress for a while. We'll come back when that's done. Okay, so the Scala IDE has finished decompressing, and what we're left here is an Eclipse folder. And inside there you'll see an Eclipse executable, and that is the Scala IDE right there. That's all there is to it. All it is a special version of Eclipse. So you probably don't want to leave this in your downloads folder, so I would go ahead and copy that Eclipse folder and put it somewhere safe. I put mine under my C drive under Eclipse. And to make life a little bit easier, you can create a little shortcut to your desktop there so you can get to it easily like I've done here. Okay. All right, and that's pretty much everything you need. So let's try it out. Let's see if it works. So go ahead and open up a Windows command prompt. You can do that by right-clicking on your Windows icon here and select Command Prompt Admin. Depending on your privileges, you might need to run as an administrator, so you may as well. So let's go to the directory that we installed Spark. So we'll go to cd space c:\spark, and that will get us into the Spark directory where we copied Spark into. If you do a dir, you should see a directory listing there. Okay, so you should be seeing something a little like this. Now, depending on what version you've installed, there may be different files in here, and that's okay. Well, we want to find a text file of some sort. So usually there's going to be a readme.md file, or maybe a changes.txt file, or even the license file will do. But what we're going to do is write a little simple Scala Spark application that will count the number of lines in a given file. So let's try it out. Let's go ahead and type in spark-shell. And what we should get in a few seconds is a Scala prompt for Spark. Cool. All right, so you should be seeing this at this point. If not, something is wrong. Go back and double check all those installation steps carefully. Like I said, all it takes is one misstep or one mistypo, and things can go wrong. Now, if you are going to go back and adjust your environment variables, make sure that you close out of the command prompt and open up a new one, because it only picks up changes in environment variables when you open up the shell. All right, so assuming you got to this point, let's play with it. See if it works. So follow along with me here. Type in val space RDD equals sc.textfile with a capital F. Case is important here. Open parenthesis. That's a parenthesis, not a less than sign. Quote. And we're going to use the readme.md file that was in there. End quote. And close parenthesis. All right, so just like that. And you should see something like that. And now what we have here is what's called a resilient distributed dataset, which is a Spark construct for basically a database of information. What we've done is create a little mini database where every row is a line of that text file. So let's count them all up. Type in rdd.count, open, close parenthesis, and that should give us the number of lines in that file, 99. So there you have it, your very first Spark application running on your Windows desktop. Congratulations, you got this far. So we got everything set up now. We can move on to doing something more interesting. Again, quick note, if you're on Mac OS, follow the instructions that are attached to this lecture. I recommend using Homebrew to get set up nice and quickly using Mac OS. On Linux, you'll have to use whatever package manager you like to make sure that Java and Scala are installed first before setting up the Spark installation package. So there you have it. We're all ready to go. Congratulations. To get out of this, just hit Control-D, and that will get you back outside of the Scala shell, and you can close out of that window. All right, let's move on. Believe it or not, you've probably gone through the most tedious part of this course already, just getting everything installed and set up. But now that we have that behind us, we can start to have some fun. So stay with me in the next lecture, and we'll actually start playing with some actual movie ratings data and put that Spark installation you just put together to good use. All right, so let's do something useful with all that software we just installed. What we're going to do is get some real movie ratings data and use Spark to analyze it and produce a histogram, if you will, of the distribution of movie ratings. So how many people rate movies 5 stars versus 3 stars versus 1 stars. We'll do that right now. But to do that, first we need some code and we need some data. So let's get the data first. You need a place to put it. So the first thing we have to do is create a folder on your hard drive that you're going to use for all of the course content for this course. So I'm going to go to my C drive here and right-click and go to New Folder, and we'll call it Spark Scala. Okay, so this is going to be the folder where I'm keeping all the resources for this course, all the code, all the projects, all the data. It's kind of like where we're going to put everything in the end. So remember where that is. We'll keep that off to the side. Now let's get some data to put in there. So open up your favorite web browser and go to grouplens.org, just like that. So pause if you need to for a second to go do that. Once you're at grouplens.org, that will take you to the University of Minnesota's research site. And these guys are kind of pioneers in the field of movie recommendations, and they've made a lot of movie rating data freely available for people like us to play around with. So click on the Datasets tab. And what we're going to do is grab the MovieLens 100K dataset. So this is kind of small data, 100,000 ratings, but since we're going to be developing initially in our desktop instead of on a real cluster, we're going to just use a smaller subset of this ratings data to play around with and get familiar with what we're doing. That's actually generally a good thing to do. You know, you want to test out your Spark Scala programs on a smaller data set locally and debug it, and then work your way up to larger data sets. It's generally a good practice. So let's click on the ml-100k.zip file here, let it come down, and that contains all the ratings data we need. If I show that in folder, I can right-click on that and extract all to decompress it. And there we have it. Take a quick peek inside. You can see there's a bunch of files in there. U.data contains the actual movie rating data. It has 100,000 rows of user IDs, movie IDs, ratings, and timestamps. And all this other stuff is things like u.item, which maps things like movie IDs to movie titles and stuff like that. But for now, let's just copy that entire ml-100k folder. Okay, remember this is the decompressed one that contains these files, and copy it into our Spark Scala folder that we created a minute ago. Okay, so that's the start of our little course folder there. Next thing we need is some code to actually run. So I'll have a link for this associated in the lecture resources, but if it's not there for some reason, here's where you want to go. http://media.sundog-soft.com/sparkscala/sparkscala.zip. Okay. Again, pause there if you need to, but I'm just going to go ahead and download that. All right, so let's go ahead and open that up. And you'll see we have sparkscala.zip. Let's decompress that. Extract all, extract. And this is kind of where we're going to be copying stuff out of. So, we're actually going to be importing stuff out of this folder and into that Spark Scala folder that we created. So keep this somewhere safe. For me, it's just going to stay in my downloads folder for now, under the Spark Scala folder that I decompressed. If you want to tuck that away somewhere else, you can, but just make sure you remember where you put all this stuff, because this is all the source and data that you need for the course. And we're going to use it one bit at a time. So next, let's actually try to run that code, shall we? So let's go ahead and open up the Scala IDE that we installed in Lesson 1. So for me, I put a handy-dandy shortcut on my desktop here to eclipse.exe. Going to open that up and make sure you select the right workspace folder. So remember that folder we just made. We're going to hit the Browse button here to select a workspace and set that to, in my case, C Spark Scala, which is that folder we created that's going to have all the stuff for this course. Okay, so that's going to be where all the projects live. Hit OK. And up should come a blank Scala IDE screen. Let's blow that up. All right, first thing we need to do is create a project that we're going to use for this course. So let's go to File, New, Scala Project. And we'll call it, I don't know, Spark Scala Course. How about that? Finish. All right. Hit pause if you need to keep up with me here. Very important that you follow these steps exactly that I'm about to do, okay? All right, now that that project's been created, I can right-click on it and say New Package. And it says Java package, but it is going to contain Scala code. Don't get thrown off by that. And we need a package name for the package we're going to keep all of our code in for this course. Now I'm going to go with com.sundogsoftware.spark. And if you've done Java coding before, you kind of know the naming conventions for packages. But if you're not familiar with it, what you usually do is you use your organization's URL, domain name, as sort of the basis for it. So I have a website called sundogsoftware.com, so just to make sure that my code doesn't conflict with someone else's code in a different package, I'm going to use that as my unique identifier for my package name. So I start off with com.sundogsoftware, which identifies my organization, and Spark is kind of the name that I'm giving for this particular project. Hit finish. So now we need to import the source code for this project, and we're going to right click on this and go to import. So I right clicked on the package, I'm saying import. We're going to go to general and then file system. That means we're going to import source code from my local file system. So remember, we downloaded everything for this course. We're just going to import it from there. So I'm going to browse to my download directory. And under there, I had a Spark Scala folder, which is where I downloaded all the stuff for this course, remember? So I'm going to select that Spark Scala folder in my downloads. And you should see something like this, a little menu here of all the resources for this course that we downloaded from the web. So let's go down to ratingscounter.scala and check that off. And we're going to hit finish. And that should give us, underneath our package, a ratingscounter.scala file. So go ahead and double click on that and you can take a little peek at the code here. And you can see here's some actual Scala Spark code that we're going to run in a minute. So the nice thing about the Scala IDE is that it tells you very clearly when there's a problem before you even run your code. So all these little red X's, that means something's wrong. You can't even compile this, let alone run it. And these X's over here also indicate a problem with the package itself. And if you were to actually go down here to the Problems tab, you could get more information on it. Now, in our case, the only issue is that we haven't actually imported all the Spark libraries to our project yet, so all this Spark code has nothing to really link against or nothing to refer to. But that's easy to fix. So all you need to do is click on the project here, Spark Scala course, and then right-click it and click on Properties. Now I want you to click on Java Build Path. And what we're going to do is go to Libraries and add external jars. What we're going to do is add in all the jars for Spark itself. So to do that, we're going to navigate to where we installed Spark, which should be C Spark on a Windows system, if you followed my instructions earlier in the course. And we'll go to the jars folder here. And basically we're just going to Control A to select everything and import it into our project. Why not? And hit OK. And if you give it a few seconds, those errors should clear up. Sure enough, they do. Very cool. All right, so now we can actually run this puppy. All right, to do that, we're going to go to the Run menu and say Run Configurations. All right, and we're going to create a Scala application. So let's double click on that. Give it a name. We'll call it Ratings Counter. And for the main class, we're going to type in the package name, which is com.sundogsoftware.spark, followed by the name of the object that we're creating, which is Ratings Counter. All right, and now if we're lucky, it will actually work. Let's give it a try. All right, off it goes. Oh my gosh, look at that. Cool, so we actually ran some actual Spark code there and it worked. So what's going on here? Well, our output here is actually telling you that for rating type 1, there are 6,110 one-star ratings in our dataset, 11,372 stars, and so on and so forth. So that's giving you the breakdown of different rating types in that real movie rating data. It's pretty cool, and it happened pretty quickly, too. So how do we interpret this? It's kind of interesting, right? I mean, the most popular movie rating is a 4, and people really reserved one-star ratings for the worst of the worst. 5 stars, not that popular compared to like a 3-star. So, you know, people are fairly critical about their movies in this data set. Now, again, this goes back to 1998. It might be interesting to actually download the latest movie ratings data from MovieLens and see if that distribution has changed. If you want a little bit of a challenge, you might want to go ahead and try that, but it will involve changing this code a little bit. So there you have it. You've actually run some real Spark code using Scala. Woohoo! Congratulations, your first Scala Spark program. Now we're going to go into in more detail of how this actually works and what's going on here, but if you do want to peek at the code, don't let me stop you. Take a look. So it's not that hard to figure it out, right? So we have an object that we're kind of creating our application within. We're going to name it Ratings Counter, and we have a main function that is in everything that we run. And here's where all the action happens. So first thing we do is we get rid of some of the log span. We just say that we only want to see error level messages, and once that line gets executed, all these info messages start getting suppressed. Good thing. Next thing we do is we just set up our Spark context, and what this means is that we're going to run it locally using every core of our CPU that's available. And we're going to name this job Ratings Counter. Now, with one line of code, we actually load up the actual ratings data itself into something we call a resilient distributed data store that we'll talk about more in a couple of lectures. So that kind of loads up our raw data. This next line actually parses that data out. So it splits it out based on tab characters and extracts the actual ratings themselves. Okay, so since all we're doing is counting up rating scores, we're just extracting the actual rating from each line here. And then we have this magic little function called count by value that will automatically give us a count by each rating score. And then we sort it and we print the results. So, you know, it doesn't look that intimidating, does it? I mean, that's just some basic Scala code in Spark. And we're going to go next into understanding Scala. So let's go into some more depth about what's going on with Scala itself and giving you a crash course in the Scala language. Once we're done with that, we'll come back to Spark and see how it all fits together with Spark and Scala. So again, congratulations. Got your very first Spark application with the Scala programming language actually running on your desktop. Congratulations. Let's go learn more about Scala. All right, we've done a lot in these past 2 lectures. We set everything up for developing Spark code on your desktop using Scala, and we actually ran some Spark code using some real movie ratings data. And you know what? You could take that same code and run it on a real cluster, and it would just automatically distribute it as if by magic across the entire cluster. So you've actually made a lot of progress so far. Pat yourself on the back. It's awesome. All right, now we have gone through a lot of steps to get to this point. So if things aren't working as expected, go back and rewatch things. All it takes is one misstep, one little mistype thing, and nothing will work. So if you're having trouble, please go back. Just watch it again. Take it slow, one step at a time. Use the pause button on the video if you need to kind of go slowly one step by one step. Hopefully you'll get there. Now at this point in the course, you might be prompted for a review of this course already. And kind of the way it works is they want to collect your feedback on the course as you go through it. And you know, if you like what you hear so far, if you enjoyed my teaching style and you're feeling productive, awesome, please leave a rating. If you don't feel like you're ready to leave one yet though, and you kind of want to keep on going and see how it goes, there is a Ask Me Later button on there you can hit as well. So don't be afraid to use that too. And if you are having trouble, go ahead and fire me an email. You know, use the messaging feature on this platform or post a question in the Q&A for this course, and I'll be glad to help you out and try to get you going. Okay? All right, so with that, let's move on, and we're going to do our crash course in the Scala programming language next. Big stuff. So here's the plan. First, I'm going to teach you a little bit about the Scala programming language, and you need that before we can actually start writing Spark code in Scala. So first things first. If you already know Scala, that's great. You can skip this whole section, but if not, stick with me to learn some of the basics. All right, let's learn Scala. Just to set expectations, you're not going to be a Scala expert at the end of watching 4 videos with me. So what I'm really trying to do here is just get you familiar with the syntax of the Scala programming language and introduce some of the basic constructs, like how do I call a function in Scala, how does flow control work, what are some basic data structures I might use with Scala, and just show you enough Scala code that it's not going to look scary and intimidating to you as we go through the rest of the course. So with that, let's talk about Scala at a high level first. First of all, why learn Scala? Well, you've probably never heard of it before, or maybe you have, but you certainly probably don't know it. It's mostly used for Spark programming, but it is uniquely suited for Spark because it's really structured in a way that lends itself to doing distributed processing of data over a cluster. You'll see why a little bit later on. It's also what Spark itself is built with, so by learning Scala, you'll get access to all the latest and greatest Spark features as they come out, and it can usually take a pretty long time for those features to trickle down to, say, Python support within Spark. And it's also going to be the most efficient way to run Spark code itself. So by using Scala, you will have the fastest and the most reliable Spark jobs that you can possibly create. And I think you'd be pretty surprised at just how much faster and how much more reliable the same Spark job written in Scala is compared to, say, the same Spark job written in Python. So even though it might be tempting to go off and stick with the language you already know, learning Scala is worth the effort, and it's really not that hard. Truth is, the same Spark code for Scala and Python look very similar to each other at the end of the day. Now, Scala itself runs on top of the Java virtual machine, so it just compiles down to Java bytecodes and gets run by the JVM. So one nice thing about that is that you also have access to all of Java. If there's a Java library you want to pull into your Scala code, you can do that. So you're not limited to what's in the Scala language itself. You can actually reach down to the Java layer and pull up bits of Java that you want to use too. And we'll do that later in this course, for example, for dealing with regular expressions in a little bit more of an intuitive manner than you could otherwise. Another key point about Scala is that it is focused around what is called functional programming, where functions are sort of the crux of what we're dealing with. Functions get passed to other functions and chained together in ways you might not be used to. but this is really how Spark works at a fundamental level. We basically take a abstraction over a chunk of data and we assign it a function to do some processing on that data. And functional programming in Scala makes that very intuitive to do from a language standpoint. So with that, let's dive in. First, a little bit of an administrative note. So as we go through these introductory Scala courses, I'm going to attach the actual source code files to each lecture, assuming you're on a platform that supports that sort of a thing. So, feel free to just download those as we do in the videos. Now, if you did in the previous lecture download the entire big chunk of all of the course materials all at once, same files are going to be in there too. So if you want to just import it from wherever you save those course materials, that's fine too. Either way works, so just don't get confused by that. And with that, let's take a look at some actual Scala code. All right, let's learn some Scala, shall we? So first thing I want you to do is go to the resources for this lecture and download the learningscala1.sc file. That's a Scala workbook file, worksheet file. And just download that wherever you download your stuff, your downloads folder. And hit pause while you go take care of that, please. I'll stay here and wait for you. Done? All right, let's move on. So I've opened up the Scala IDE here by opening up my Eclipse shortcut on the desktop. And what I want you to do next is go to the File menu and say New Scala Project. And let's call this project Learning Scala, shall we? Just like that. All right, now we do actually need a separate project for these worksheet files, and well, the reasons are complicated. Basically, there's a conflict with the Scala version that we used in the other project, but just go with it. So go ahead and right-click on that Learning Scala project and hit Import, and go to the File System, and select whatever folder you download stuff from your browser into, wherever you downloaded that Learning Scala 1 file. So for me, that's the C Downloads folder. And we'll select learningscala1.sc and just hit Finish. And we should have, if we open up Learning Scala, learningscala1.sc. So go ahead and double click on that, and here we go. Now what we're looking at here is what's called a Scala worksheet. It's kind of like a notebook in Python in that you can actually interactively enter commands and see them evaluated right in line there. So you wouldn't, go and write a real script this way, but it's a good way to get familiar with the language and just sort of experiment and try different commands, and you can immediately see the effect they have. So what's going on here is, you have a line of code, and after you evaluate it, which happens automatically whenever you save the worksheet, it will tell you over here on the right the actual output from the Scala interpreter that resulted from that command. So very good way to see, what you're typing in for code and the result that code has immediately. Pretty cool stuff. So let's just dive in and take a look at some of the Scala code. So, every language has variables, right? And variables can be mutable or immutable. And mutable means they can be changed. Immutable means they can't be changed. So in other languages, that might be a constant variable or a final variable, depending on the language we're talking about. Now in Scala, they encourage the use of immutable variables as much as possible. And those are called values with keyword val. So the syntax here for declaring a string value is a little bit unusual. Let's look at what's going on here. So we have val, meaning that it's an immutable constant. We're going to name this immutable constant hello. It's going to be of type string, and then I set its value to hola. So val hello, colon, string equals value. So the syntax here, val, meaning it's immutable. Hello is the name of the variable. Colon, and then the type. Equals whatever it is. Okay, so that's how we declare an immutable value in Scala. Now, just to show you that it actually works, let's change that to, I don't know, what's French for hello? Bonjour. Now, watch what happens when I hit Control S to save it. This actually all gets interpreted again. Unfortunately, it goes to the bottom of the file whenever I do that, but if we scroll back up, we can see that it now says hello, string equals bonjour. And we can print out the value of that string with a print line command. So in Scala, that's how you print out a line of output. Print line, parentheses, hello, the value name, will print out, output the value bonjour. So there you have it. Very simple string, very simple there. Now, although Scala encourages using immutable values, you can also use mutable variables as well if you need to. Sometimes you just can't get around it. So if you need to do that, you use the var keyword instead of val. So here we have an example where we have hello there, which is initially set to the value that we had in hello, which you remember we sent to bonjour. So here we are assigning a variable called hello there and assigning it the value hello. Hello referring to this value up here that contains the string bonjour. With me so far? Makes sense? If you've done any programming before, you can probably follow along what's going on here. So at this point, the value of the hello there variable is set to the string bonjour because that's what my hello value was set to. Now, because it's a variable, I can actually change it. So I can say hello there equals hello plus the string there. So I'm changing the value of hello there from bonjour to bonjour there. And you can see that when I print that out, indeed, it does contain bonjour there. And just for fun, we can change this back to hello up here. Watch everything get reevaluated when I save it, and now it says hello there instead. Okay, so you got it. Basically, there are vals that are immutable, vars that are mutable, and the syntax in Scala is a little bit weird for declaring things. You have the variable name :type equals whatever you're assigning it to. Okay, so that's a little bit backwards for most languages. Takes a little bit of getting used to, but you'll get the hang of it. All right. So one thing I want to point out is that in functional programming, we're using a lot of functions. And the danger of that is that if you have a function that quietly changes the value of something behind your back, that can lead to bugs. It can lead to unexpected behavior. So in functional programming languages like Scala, they really encourage the use of immutable constants whenever possible. So you want to be using vals whenever you can instead of vars. So instead of using a mutable constant and modifying it as you go, create new immutable constants and build them up over time. So here's an example of how that works. So let's say I start off with an immutable hello there that is initially constructed from the concatenation of whatever's in my hello string and the string there. So initially I'm just putting hello there into my immutable hello there. So you see here I'm actually doing the combination here on the right hand side here and putting it into the final value where it won't be changed. Now, you can change these together. So let's say I want to add something else here. Let's say I want a new val that's immutable, more stuff, and I can set that to immutable hello there plus, yeah, I don't know, I'm just making this up as I go, right? So let's see what that does. So now I have hello there, yeah, and basically, I still have two values here. One's called immutable hello there, one's called more stuff, but I never changed the value of immutable hello there, and I never changed the value of more stuff after it was initially created. Okay, so I kind of like always know what's in this symbol, this name here. It doesn't change, and that makes coding a lot more safe. If I need to go back to that value, I can just refer to it by its original name, and that's the best practice for dealing with functional programming. Now, one thing I want to point out too, notice that I didn't actually declare the type here. Scala can actually implicitly figure it out in a lot of cases. So I didn't have to say val immutable hello there :string because it knows that I'm sticking together two strings and that produces a string object in return. So in cases where there's really no ambiguity over the type, Scala can infer it for you automatically, and you don't actually have to do that :type name syntax all the time. Okay? Some other types. We've been dealing with strings so far, but there's all the usual suspects here. If you want an integer, it's just an int type, capital I. We also have Boolean values. That can be true or false, lowercase are the keywords there. If you want a single character, basically one of 256 characters, 8-bit value, represented as an ASCII character, you can use the char type. Double precision floating point is double, single precision is float, and notice that we have the usual f suffix here indicating a floating point constant. Scala is a little bit pickier than other languages in enforcing that you use that. So if you are using single precision constants, make sure you remember to put that f at the end. Double wide integer is a long, and we also have a 8-bit value called byte, just like in Java, that ranges from -127 to 127. And you'll find a lot of these types are very analogous to the types in Java, reason being that Scala is built on top of the Java virtual machine, so there's a lot of transparency between the two languages. All right, moving on. Want to take a break now? It's fine. Go get a drink. Hit pause. It's all right. But let's talk about printing stuff out. So a common thing you need to do in a language is output human-readable stuff. Very simple to do in Scala. If you just want to tack a bunch of stuff together, you can just use the plus operator to do that. So you can see I have a bunch of different types of information up here, and I can just mush them all together with the plus sign here and create a big old giant string. So print line, here's a mess. I'm starting with a string and then I'm concatenating on the number 1, a Boolean value, a character value, a double precision value, and a long value all together. And when we print all that out, we get exactly what you would expect. Here's a mess followed by all this stuff jammed together in the form of a string. And that all just happens automatically. All right. Now sometimes you need to format numerical output, and you might be familiar with the printf style of output in other languages. Scala supports that too, but the syntax is a little bit strange. So what you do, if you want to do formatting of that nature, you need to prefix your string with the character f, and that expands to a little macro that says I'm going to use a printf style format within this string. So here we're saying print line f, meaning that I'm going to be formatting the text in here somehow, and I'm going to say pi is about, then I have a $sign followed by the variable name that I'm going to be formatting, followed by a %, and then the printf format for how I want to display that. So in this case I have 0.3f, meaning that I want to display a floating point value with 3 decimal points of precision on the right hand side of the decimal point. And if you're not familiar with that syntax, you can go look up printf on the interwebs and get more details, but pretty common tool for formatting your output if you need to make sure that it's human readable and only has a reasonable amount of precision. And if we run that, we see sure enough pi is about 3.142, so that took the value of pi single precision, which is 3.141599265, applied this formatting string to it, 0.3f, and that made sure that we only had 3 decimal points, places of precision to the right of the decimal point. Here's another example. You can also use the same trick for putting 0 padding on the left of numbers. Sometimes that's useful for sorting strings, for example. So in here we have the f prefix again, $sign by the variable name number 1. In this case it's an integer, which is the number 1, and we're using a %sign followed by the formatting string, which is 05D. The D means that it is an integer value, and the 05 means that I want 5 places of precision with zeros padding it in if necessary. And the output from that is, with 5 decimal places, 00001. Okay? All right, another trick we can do is actually substitute in variables as part of our string as they're being constructed. So for that, we use the s prefix, and then anything that's preceded by a $sign will just be interpreted as a variable or a value name. So we have this s prefix. I can use the s prefix to use variables like $sign number 1, that will pull in the integer value 1 up here, $sign truth, which should pull in true, $sign letter A, which should pull in the character A, and sure enough it works. When we evaluate that, we get, I can use the s prefix to variables like 1, true, A. And you can also do fancier stuff. You can do more than just reference values and variables. Here's an example where we actually evaluate an expression. So again, that $sign means I'm about to evaluate something, and it might be a variable or a value name, or it might be a whole expression. So if you put something within curly brackets, that basically says, I got a little bit of code here that I want to execute. And you can put whatever you want in there. It might be like a little tiny little function even. But in this case, we're just going to add 1 plus 2 together. And sure enough, it works. When we actually run that, we get the s prefix isn't limited to variables. I can include any expression like 3. So $sign brackets 1 plus 2 just got converted to the value 3 inside that string automatically. So very handy tools for producing output when you're printing stuff out or writing it to a file or what have you. All right, the next section gets a little bit weird. So again, if you want to rest your brain a little bit, let that previous stuff sink in, that's okay. But let's move on. Now, if you're familiar with regular expressions, they can be a powerful tool for pattern matching strings and extracting information out of structured, formatted data. So let's say you have, for example, an Apache access log that has a very specific format. You might use a regular expression to extract fields out of that line of log information. And we do that in this course later on, quite a bit actually. So, for example, let's say I start with a string that has to life, the universe, and everything is 42, and we're going to call that string the ultimate answer. If you read Douglas Adams, you know what I'm talking about. So the syntax for handling regular expressions in Scala is really weird, okay? It's going to blow your mind. It's strange. Nothing I can do about it. Sorry, you just have to live with it. What we have is this strange triple quote syntax followed by a .r. And that basically means I want to construct a regular expression out of the stuff in between the triple quotes. So if you're familiar with regular expressions, you'll know what this all means. Dot star means extract a bunch of characters, then look for a space, and then we're going to look for one or more number characters. That's what the \d plus means, followed by a bunch of other characters. So basically this is saying, go look for the first number in this string. So I'm trying to suck out the 42 out of this string, basically. Now, regular expressions is a whole topic in itself. There are multiple O'Reilly books on the subject that you can do some very, very fancy and some very complicated things with them. So if you want to learn more about regular expressions, go look on the internet or try out the Introduction to Regular Expressions book from O'Reilly. That's probably a good start. But odds are you've seen these before. And if you haven't, you can usually find the one you need on the internet if you just look. I'll provide you the ones you need in this course for logs, for example. So don't get too hung up on the syntax. But the way it works in Scala, like I said, is pretty weird. So we have this regex that we created using this .r operator here. And what we're going to do to apply that, it's really weird how this works. You take that regex and you pass in where you want to put the result that you extract information from. So we're going to basically try to pull out that number from the string and put it into a new value called answer string. And then we use the equal sign to say, well, I want to run this on the string called the ultimate answer. And, you know, the syntax of this really defies human logic. You just have to kind of go with it. You know, it's something about Scala that I just don't like. But keep this worksheet around for reference. So if you do need to do some regular expression stuff later on, you'll have this to look at, because it really doesn't make intuitive sense at all. Anyway, what that does is it does apply that regular expression to this string, extracts out that number 42, and sticks it in the string answer string. Last thing we need to do is, because that is a string, but we really want to treat it as a number, we can call toInt on that string and extract the integer value 42. So toInt will convert any string to an integer. And, you know, like you might expect, there's also toFloat or, you know, whatever else you might need. Conversion operators there as well. Notice that I didn't actually have to put a open and close empty parenthesis there. That's not actually necessary. And we print the answer, we get 42, okay? So honestly, this is about as weird as Scala gets. If you made it through that, it's all downhill from here, okay? It's going to be easier. As promised, with getting easier, Booleans work much as you would expect. So if you just want to compare two things, if one is greater than 2, well, no, the answer is false. 1 is less than 2 will give you true. One thing that's a little bit ambiguous in some languages is, what does 1 ampersand versus 2 ampersands or 1 pipe versus 2 pipe do, you know, when you're doing and or comparisons. You can do either one in Scala. The only difference is that if you use a single ampersand, both expressions get evaluated and then, you know, anded together. Whereas if you use a double ampersand, that means that it can actually bail early. So if is greater were false, it would actually not even bother evaluating is lesser at all, and would go left to right, you know, only as far as it needed to. So for performance, you'd probably want to go with the double ampersand usually. But for safety, a single one might be better, because you might have some expression in there that you assume gets run, and it might not if you're using a double ampersand. Either way, here you get the same answer. You can't be greater and lesser at the same time, so both of these provide a result of false. String comparisons, also something that works differently in different languages. In Scala, it makes sense when you compare two strings using the equals equals operator. It actually compares the contents of the string and not the string objects themselves. So if I set one string equal to Picard, and I have another string called best captain that's also set to Picard, if I test Picard equal best captain, it compares the contents of those strings and says true. And, well, you know, I don't want to get all nerdy on you and debate the values of Star Trek captains, but we'll leave that for an exercise to the reader, shall we? All right. So that's lesson 1 with Scala crash course. Some basic stuff here. All we did was cover, you know, the syntax for declaring mutable and immutable variables. We looked at some different Boolean operators, some ways of printing out information, applying regular expressions, and you have what you need to do a little exercise here, so make it real. So while you're in here, like I said, you can just add in code here and hit save, and it will get evaluated right away, so play around with it. My challenge to you is to write some code that takes the value of pi, doubles it, and then prints it within a string with 3 decimal places of precision to the right. So you should have enough examples within this worksheet to do that pretty easily. You know, this isn't meant to be difficult, but I just want you to get your hands on with some Scala code actually get comfortable with the fact that, yes, you can write Scala code yourself and actually make it run and operate. So please do that exercise, even though it does seem trivial. It will be helpful. So do that, and we'll move on to the next lesson. All right, moving on. This next topic's going to be a little bit easier, a little bit more straightforward. We're just going to talk about flow control in Scala. So to get started, go ahead to the resources for this lecture and download the learningscala2.sc file, wherever you download stuff. And I will sit here and wait for you. So hit pause and take care of that, please. All right, let's move on. So we're going to right-click on Learning Scala, our Scala project here, and say Import, and go to the file system, browse to wherever you download your stuff. For me, that is, C Downloads. And select learningscala2.sc and hit Finish to import that into our Learning Scala project. And double click on that, and you should see this. So let's just talk about flow control. How do we control the flow of our code in Scala? It's all pretty intuitive. There are a few syntactical differences from other languages, but by and large, it should look very familiar to whatever language you're already familiar with. So, for example, you can use if-else syntax. If 1 is greater than 3, print line impossible. 1 isn't greater than 3, else print line the world makes sense. And sure enough, that will output the world makes sense. Now, I could also put brackets around this if I wanted to make it more than one line. That's okay. You'll see that down here, where I'm actually splitting it out to be a little bit more readable. Often in Spark code, you see people jam things onto one line just because they can, and that's kind of a common attribute of functional programming, I'm afraid. But either way works, so that's fine. There is no else-if operator, so you would have to actually do another, else after that if you wanted to. And that's all there is to that. If and else works just the way you would expect. Now, matching. So let's say you have like a switch statement in other languages where you have a value and you want to have different cases where you do something different depending on what value that variable has. So in Scala, that's called a match statement. So instead of switch, we use match. Other than that, pretty similar. So let's say we start with a constant value number that's set to the number 3. We can set number match would be the syntax here. So I want to match on the value of number, and for case 1, so you have this little equal sign greater than thing that sort of says, associate this function with that case. So that could actually be a whole expression if I wanted to, but in this example, we'll keep it simple. So in case 1, we're going to map that to printline 1. Case 2 will be mapped to printline 2. Case 3 will be mapped to printline 3. And then this underscore is basically your default, your catch-all case here. So case underscore, meaning it's something that's not 1, 2, or 3, will printline something else. But in this case, our number is 3, so it falls through to the case 3 and prints 3, which indeed works. So again, there's nothing really complicated going on there. It's just like a switch statement in other languages, but the syntax is a little bit different. We have match followed by the value name here, which is a little bit backwards from other languages, and we have this little mapping operator here, equal greater than, to actually map cases to what you want them to do. So that's the syntactical trickery there. For loops, nothing special about them. Well, a little bit syntactically. So look at what's going on here. We have for x 1 to 4. So basically we want to iterate through the values 1 through 4 inclusively. The only weird thing here is this little less than dash syntax here, and that is basically a range operator in Scala. So this says I'm going to take the value x within the range of 1 to 4, and it's going to create a list of 1, 2, 3, 4 and iterate through that in this for loop. So we will take here the square of each value. So for each value 1 through 4, I'll multiply it by itself and print the result. And we see 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, and 4 times 4 is 16. So the for loop syntax itself is exactly what you would expect, but we have this new range operator here. That's something new. So remember, that's how you specify a range of values in Scala. While loops, absolutely nothing interesting there. It works exactly the same as it would in other languages. So let's say I start with a x variable set to 10, and I want to iterate through this while x is greater than or equal to 0, while I subtract 1 for it as I go, printing the values. So there's really nothing fancy there at all. It does exactly what you would expect. We start with 10, and as we print the value and then decrement it We'll keep on going until it hits 0. So 1098 all the way down to 0. Just like in any other language. And just like we have while loops, we can also do while loops. Also, just like in any other language, there's really nothing Scala special here going on. We have basically starting with the value of 0, do, print the value, increment it by 1, and do that while x is less than or equal to 10. So instead of counting down from 10 to 0, we're going to count up from 0 to 10 using a do while loop. Again, if you have any prior programming experience at all, I'm sure you've seen this all before, and there's really nothing special about it when it comes to Scala. Works this way, you'd think. Now, one thing I want to talk about, though, is expressions in Scala. And one thing that is a little bit different is that when you have a block of code like this, let's say I'm starting with the value of x equal to 10, and then I'm going to add 20 to that. Now, in other languages, that wouldn't actually do anything because we're not actually returning anything from that expression. But in Scala, this has an implicit value. So whatever the last expression is will be what this expression as a whole is set to. So I can actually take this expression and use that as the value 30. So take a look at this. I can say print line, this expression, val x equals 10, x plus 20. That expression gets evaluated, and the number we're left with at the end is 30. So this all gets translated into the value 30, which actually is what gets printed out here, okay? So we're starting to touch on some aspects of functional programming here where expressions can actually be used as values of their own, okay? So that takes a little bit of wrapping your head around. So stare at those two lines a little bit longer and make sure that sinks in for you. Okay. Now just get your hands dirty. A little simple example here. You probably see this on a lot of sort of simple job interviews too. Print the Fibonacci sequence in whatever language you want. In this case, I want you to do it in the Scala programming language. Not hard. All you have to do is write a little loop that goes through the numbers 0 through 10, and the expected output should be something like this, where every time you go through the loop, you're adding in the sum of the two numbers before it. So basically you need to write a loop that keeps track of the previous two values, sums them up as you go. So a little exercise in some flow control and doing some looping in Scala there for you. Have at it and have some fun with it. So I just want you to get your hands dirty. And again, just get some confidence that you can actually write Scala code that runs. All you have to do is write your code in here, and every time you hit Control S to save, it will get evaluated for you, and you'll see the result right alongside your code. So give that a try and see how it goes. On to the next lecture. Moving on, like I said, Scala is a functional programming language, so now it's time to talk about functions, which are obviously very important in Scala. So go to the resources for this lecture and download the learningscala3.sc file. Hit pause while you take care of that. And just like before, we're going to import that into our project as well. So again, right-click on Learning Scala Project, go to Import, go to File System, and select the folder where you download your stuff to, whatever that might be, and select learningscala3.sc. Finish, and you should see it here in your project. Let's double-click that and take a look. Should look like this. All right, so let's talk about functions in Scala. Very important lesson here. Like I said, functional programming. This is kind of the building blocks of it. So syntax for a function in Scala, it looks like this. You start with def, which basically means I'm declaring a function of some sort, followed by the function name, in this case squared. I'm making a function that just squares some value. And the syntax, again, is backwards from what you might expect from other languages. So we start with a parameter of x that is of integer type. The way we say that is x:"int. And then the return value of this function is an integer as well. So we have another colon after that function name declaration in the parameters that is followed by the type that is returned by the function. So again, this is totally different from what other languages might do. Usually you would see int squared int x. Instead, in Scala, it's squared x int. So just it takes some getting used to, but make sure you understand what's happening there. So again, def means we have a function followed by the function name, our parameters, which have a colon that specifies the type of each parameter, and then finally another colon followed by the type that is returned by the function. And then another thing that's a little bit different is that we have an equal sign between that and the actual brackets for the function, because we're basically taking this expression and assigning it to the square it name, okay? So a little bit different there too. But inside, all we're going to do is say x times x. And again, this is an expression, so remember from the previous lecture that we don't have to actually explicitly return anything. Whatever the last value computed in that expression is what gets returned. So this is all we need for a function that actually squares a value. So let's take a look again. Square it, takes in an integer, returns an integer, and it applies this expression to it, x times x, to actually get the square. Now we can do something similar here for cubing. Again, def cube it, takes in an integer x, returns an integer, and uses the expression x times x times x to compute what gets returned. So let's see it in action. If we do print line square it 2, you just call the function like you would in any other language. That will return 4. And if you print line cube it 2, that will give 8, because 2 cubed is 8 and 2 squared is 4. All right, nothing too crazy yet. This all kind of makes sense, right? Things get a little bit weird now. So remember I said before up here, we're basically assigning this expression to that function named square it. So basically every function in Scala is kind of its own little object, and you can pass these functions around to other functions like they are objects themselves. So that makes a lot more sense with an example here. Let's make a new function called transformInt. And what this function does is it will take a function to transform an integer, it could be any function, and apply that to some integer. So our parameters here in this example are going to be an x, which is an integer that we want to transform, followed by a function that transforms an integer to another integer. So we are taking in here as a parameter a function that expects as input one parameter that is an integer and returns an integer. And that's what this syntax here means. Takes in an integer and it outputs an integer as its result. And the return value of this function itself is an integer set equal to f of x. So we're going to take the function f passed in and pass in the parameter x that was passed in, and what gets evaluated is that function f applied to that value x. So let's see how that works. So for example, we can call transformInt with the value 2 and the function cubeit. So this will pass in the value 2 to x and the function cubeit to f. The function will then take the function cubeit and pass in x to that and return the result. So that gives us back 8, because that will pass in 2 to the cubeit function and return 8. And we can print the results, and there it is. Now, for example, we could change that to be square it. Let's just make sure it works. Hit save. Sure enough, we get 4 now, because now I'm passing 2 to the square it function. So, you know, you might want to take a little break here, make sure that sinks in. This is kind of a very fundamental and very important concept of functional programming, that you can pass functions around as parameters themselves, okay? I mean, other languages this is still possible to do, but you don't see it as often, okay? So very important that you understand how that's working. So stare at these little lines of code here, make sure you understand what's happening there before you move on, okay? Now, you don't even need to have a separate function declared for this trick to work. You can actually declare these functions in line as well. And if you've worked with me on my other Spark class in Python, this is very similar to how a lambda function in Python works. It also goes by the name of anonymous functions, or function literals is a popular term in Scala. But you're going to see a lot of this, so make sure you understand the syntax of what's going on here. So here I'm calling transformInt, and instead of passing in a named function that I already declared, I'm just passing in the expression itself. So I don't even need to have a separate function at all. I can say I'm going to pass in the parameter 3, and I'm going to pass in this expression that takes in a value x and transforms it using the expression x times x times x. And this becomes my entire function definition that I pass into that function. So instead of having a separate cubeit function, I can embed what cubeit does just right here within this call. So this is perfectly valid syntax in Scala. I can say I have some value x that gets transformed using equal greater than to x times x times x. And that actually works. You can see here that if I pass in the value 3 to transform int, and I pass in this function, x gets transformed to x times x times x, it actually works. It will pass in 3 into x and execute that function on it to get the number 27 as a result. Okay, let's look at it again. So here's another example. I'm using the same transform int that just takes as parameters some integer and some function, and in this case the function, the only requirement is that it transforms an integer to another integer. I'm taking x and transforming it to x divided by 2. So in this example, 10 gets transformed into 5 that way. Okay. One more time, we can do a more complicated expression here. So instead of just a simple one-liner, we can actually do a multi-line expression as well. And in this example, we're going to take the value 2 and pass it into this function that transforms x into this expression that actually does a couple of different steps. It takes a value of y that's equal to x times 2, and then squares that resulting value, and that becomes the end result of that expression. So we take 2, assign y to 2 times 2, which is 4, and then we multiply y times y, 4 times 4, to get 16. And that is indeed what we get back. So make sure you understand what's going on there. You're going to see this syntax a lot in the world of Scala and in the world of Spark in general. So very important you understand that syntax. It's pretty easy to eyeball it, but to get a really intuitive understanding of what's going on, that's important, okay? So let that sink in. And once it has sunk in, I'll give you a little bit of a challenge here. So a very simple exercise here. Every string has a .to uppercase method that you can call on it to just transform the contents of that string to uppercase characters. So play around with some functions. Write a function that actually converts the string to uppercase. And try it out. Actually execute that function on some strings of your own. Make sure it works. And then actually get rid of this separate function entirely and do it in line, just like we did here with function literals, okay? So I want you to try both doing this with a named separate function that's defined and also with a function literal that you just do in line. So go do that to get some practice with functions. And hey, when you're done, you can say you know functional programming. Congratulations. That's something for the resume. All right, let's move on to our final lecture on our Scala Bootcamp series. All right, we're down to our last lecture in our Scala crash course here. This one's going to be about data structures, and it's a very important lecture. We use these a lot, so don't skip this one if you don't know them already. As before, go to the resources for this lecture and please download the learningscala4.sc file. I'll wait for you. Hit pause while you go take care of that. And when you have that, go on out as before to right-click on the Learning Scala project and say Import File System, browse to wherever you download your stuff, and select the learningscala4.sc file. Open it up, and you should see a little something like this. So let's talk about what's going on in here. Okay, so a really common data structure you see in Scala is called a tuple. And you see this in Python and some other languages as well. Basically, it's a collection of stuff that is treated as its own object. So we can make basically this immutable list is how you can think about a tuple. It's a list of objects that you cannot change once they've been created. Very common in Scala. So how do we declare one? You just put them in parentheses and separate the contents of the list by commas. So for example, we can create a tuple called Captain Stuff that contains the strings Picard, Enterprise D, and NCC 1701D. So maybe this is a tuple that represents information about a Star Trek captain and contains individual fields that have different information about that captain. So it's sort of an easy way to pass around, semi-structured data as its own entity. And if we print that out, we can see that gets converted to the string that is, the same syntax within parentheses, the different contents of that tuple separated by commas. So Captain Stuff itself is a single object, but it contains 3 different values, these 3 different strings here. So that is a good way to sort of stuff different bits of information into one thing, which comes into handy a lot with Spark, as you'll see later on. Now, how do I get stuff out of it? So let's say I want to extract values out of that tuple. Well, the syntax here, again, with Scala is a little bit weird. What you do is you put a dot after the tuple name and then underscore and the number of the field you want to extract. And the thing you have to remember is that it is a 1-based index. So the first value is number 1, the second value is number 2, the third value is number 3. A lot of other things in computer science, you start counting at 0. This is not one of those times. We're starting with 1 here. So for example, if I print captainstuff._1, that extracts the first field of my tuple, which contains the string Picard. ._2 gets the second one, which is Enterprise D. ._3 gets the third element of that tuple, which is NCC 1701D. Okay? With me so far? Nothing too challenging here, but again, you just have to get used to the syntax. Now, a special case is a key value pair, basically a tuple that contains 2 things. And often you'll use this as sort of a key value mapping. So let's say I want to create a tuple that represents a captain and the ship they command. I could use this syntax to do that. That will just create a tuple that maps Picard as the key to the value Enterprise D. And all that does is give me back a tuple that contains Picard Enterprise D. I could have declared it the same way as I did up here, just by having it within parentheses separated by a comma, but this is sometimes a more readable format that sort of implies to the reader of your code that you are in fact associating a value with a key here, and that's your intent of creating that tuple. You would dereference it the same way you would any other tuple. Picard ship dot underscore 2 would extract the value from that key value pair because it's the second element and give you back Enterprise D. Whereas dot underscore 1, let's try it, would give me back the key, which is Picard. Gotta scroll back up to where we were. There we are. Another thing about tuples, they don't have to all be the same type. You can actually mix and match different types of data within a tuple. So here's an example where you have a string, an integer, and a Boolean all jammed into one tuple, and that's a perfectly okay thing to do. Comes in handy sometimes. So that's tuples. Moving on, take a little break if you need to. Let that sink in, review it. We're good? All right. Lists. Lists are a lot like tuples, but it's an actual collection object, so it has more stuff you can do to it. A little bit more heavyweight, but a little bit more flexible. So kind of like a tuple, you can declare a list. That's just a list of comma-separated values here. And under the hood, it's going to build a singly linked list to represent that information. So here we have a ship list value. That is a list of Enterprise Defiant, Voyager, Deep Space Nine. So 4 different ships from 4 different Star Trek series in this example. And the syntax of dealing with lists is different than a tuple. So for example, if I want to extract a value from that list, I can just use parenthesis and then the field number I want to extract. So now in this case, we're not starting with 1, we're starting with 0. Okay, so you got to remember that. Very easy to make bugs around this stuff. In this case, ship list 1 will go extract the 0-based element of the list at 1. So we go 0 is Enterprise, 1 is Defiant. Ship list 1 gives me back Defiant. Okay? I know, it's confusing, but it's something you just have to remember with Scala. Now, dot head will give you the first element of the list. Dot tail will give you all the remaining elements of the list after the head. Okay, so in other languages, tail might return the last element. That's not how it works here. Tail gives you actually a list, a sublist of the list that just excludes the first element. And sometimes that's useful if you're iterating through a list and you need to extract one item and then, keep working with the remainder of that list in the next iteration. Okay. Now, let's say I want to iterate through an entire list and do something to every value within it. That's something you need to do pretty often. So remember that range operator we introduced back when we talked about flow control? Well, same trick applies to lists. So we can say for ship in ship lists, and that will actually produce a range, an iterator that goes through every ship in the ship list and assigns it to the ship variable. And we can print out each ship one at a time that way. So this code here, again, the key is this little range operator here that will go through the ship list, extract each individual element into a new value called ship that we can then print out within this expression. So that will go through and print out each individual ship in our ship list. More fun with lists here. We can also use the map function to actually transform a list using some expression. So let's take a look at what's going on there. Let's say I have my ship list of ship names, Enterprise, Defiant, Voyager, Deep Space Nine. I can call .map to actually apply an expression, some function, to every element of that list one at a time. So in this case, I'm actually defining a little function inline that takes a string called ship and maps it to ship.reverse, which just reverses the characters in each string. So what that does is say I want to take this function that reverses a string and map that to the ship list and return a new list called backward ships that contains the backwards names of all the ships. Okay, so stare at that line for a little bit until it sinks in, and the output is exactly what we want. So we have a list of all the ships with their names backwards. Okay, so that's what the map function does. It just applies some function that transforms each element of the list into a new list. Okay, and we can go through and print out those results too, just using that same trick with the range operator there to print out the results. And sure enough, we get the backwards versions of each ship name printed out one at a time. Okay, with me so far? Okay, so that's mapping. That's the map function. Mapping, sound familiar? Map reduce, same concept, same exact concept. The only difference is that we're not actually doing this in a distributed manner. We're just using Scala's built-in operators on the list to actually map one list to another. Now, I said map reduce. Can't talk about map without reduce. And sure enough, there's a reduce method on list as well. So just like we can use map to apply a transformation to every individual element of a list, we can use the reduce function to actually combine contents of a list together. So here we're going to start with a number list. That's just a list of the numbers 1, 2, 3, 4, and 5. I can call reduce on that list with a function that tells how to combine these things together. So basically what reduce does is it goes through each list, and as it gets each pair of items, it will use the function we provide to combine them together. So basically we're saying as new values come in from the list, add them up. So as I get two values that are processed together, I'm going to add them up, take that result, add in the next value, take that result, add in the next value, and so on and so forth until we're done. So basically this is a way of saying I want to take the entire list, sum up all of its values, and give me back the result. And what that does is iterate through the list, one pair of values at a time. So it takes 1 plus 2, says that's 3. 3 plus 3 is 6. 3 plus 4, 6 plus 4 is 10. 10 plus 5 is 15. Using that reduce operator, that reduce function we provided, and sure enough, the answer we get back is 15. And we can print out that result. Sure enough, 15. And hey, that's MapReduce. You know, the only difference is that in a real MapReduce application, you would be using functions that actually work on a cluster. Same concept though. Filter also can be used, and you know, if you've looked at Spark or MapReduce before, that might also look familiar. You can actually use that to create a sublist based on some filter function you define. So in this example, we're going to say, I have a new list called I hate fives, and I'm going to take my number list that contains the numbers 1, 2, 3, 4, 5 and apply a filter that tests to make sure that x does not equal 5. So I have in here a little inline function, a function literal if you will, that takes an integer x and tests if x is not equal to 5. And that Boolean result of that function will determine whether or not that individual list element survives and gets passed into the resulting list. So what goes on here, we start with 1, 2, 3, 4, 5. We apply this filter function to it, which will allow everything but the 5 to pass through. And you can see that we end up with a list 1, 2, 3, 4 where 5 has been excluded. We can do the same thing again here. A little bit of a more compact syntax here that you often see. Same idea, but here we're using a little bit of a syntactical shortcut. You can actually say in a function literal underscore to just say whatever it is not equal to 3. So that is sort of implicitly removing this x transformed to x and just simplifying it down to, hey, I know I only have one parameter coming in. I want to take that parameter, whatever it is, and just compare it to 3. Okay, and you can see that works just as well. If I apply this filter function that makes sure that each element represented by that underscore is not equal to 3 is all that passes through, then I end up with 1, 2, 4, 5, where the 3 has been omitted. So, you know, you do see this a lot in Scala, where we have these, you know, people that want to save keystrokes at the expense of readability, but you need to understand that when you see it. Okay. Now, Spark, you know, has its own map, reduce, and filter operations that can actually happen in a distributed manner. The only difference is that we'll be not operating on list structures, but something we call RDDs, but we'll get to that later. But same exact concept. So if you understand how this map and reduce function and this filter function worked, hey, you understand MapReduce now, and you also understand a good part about how Spark works. It's all the same idea. It's actually not that complicated. A few more list tricks here. Let's say I want to concatenate two lists together. We have our 1, 2, 3, 4, 5 list, number list, and I want to concatenate a new list called more numbers that contains 6, 7, 8. The plus plus operator will combine two lists together, and that gives us back the combined list 1, 2, 3, 4, 5, 6, 7, 8. Okay. A few more tricks. Every list has a dot reverse method that will give you the reversed list, so 5, 4, 3, 2, 1. It has a dot sorted method that will return a sorted version of that list. So here I took my reversed list that was 5, 4, 3, 2, 1, called dot sorted on it, and that returns a new sorted list that's back to 1, 2, 3, 4, 5. Let's look at distinct. So let's say I take my number list and append itself, number list plus plus number list, and I get 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. If I just want the distinct values in that list, I can call dot distinct and just get back 1, 2, 3, 4, 5, because those are the numbers that only appear once. Okay. So we also have a dot max function that will find the maximum value in a list. Sum will sum them all up if they are numbers that can be summed. And I also have a dot contains function that can be used as a quick test to see if a list contains a given value. So I hate threes, where we filtered out the number 3, contains 3, will return false because it has everything but 3. All right, that's lists. I want to take a break here, let it sink in, because we're going to move on to maps now. All right, maps. Maps, just like maps in other languages, sometimes they're called dictionaries. Basically, they're a lookup table of given keys to values. So the way to declare a map in Scala is something like this. So let's say I want to create a map that maps starship captains to the ship they commanded. So here we have a map of Kirk maps to Enterprise. So we have this dash greater than sign syntax mapping keys to values here. Picard associated with Enterprise D, Cisco D69, Janeway to Voyager. And we can actually do a lookup very simply here by using this parenthesis key name here to extract the value associated with that key. So ship map Janeway returns Voyager. Okay, very easy to use. Now, one complexity is that when you're dealing with maps, you need to deal with missing keys, right? So what if I did like Archer, okay? That wasn't in my list of original captains, in my list of keys for this map. So what happens if I try to extract Archer? Well, that should generate an exception. So one way to protect against that is to make sure that the map actually contains the key you're looking for first. So if I do that test, I can say shipmap.contains Archer. That will return false because shipmap does not have a key for Archer. And at that point I could say, well, I know that key doesn't exist, so I'm not going to try to extract the value for that key because I know that would lead to an error. Another way you can deal with it is by using this try syntax. So, just like try exception blocks or try catch blocks in Java, similar concept there. What we're going to do is use this util.try function that's built into Scala to actually extract the value for Archer from shipmap. And what's going to happen is that's going to generate an exception because there is no key for Archer in shipmap. But instead of erroring out, we're going to wrap it in this util.try so it catches that exception. Get or else says, I want to actually get the value of this expression here, but if it generates an exception, here's my fallback value of unknown. And if I go ahead and execute that, you can see that when I try to do shipmap Archer, that does generate an exception. Get or else handles that exception and returns the string unknown in that case. So that's a safe way of accessing a map where you're not sure if the key is actually in it or not. All right, those are all the main data structures that we need to deal with Scala. There are others, and we'll maybe touch on one or two more of them as we go through the course. Obviously, there's a lot more to Scala than we've talked about here. We haven't even really gotten into object-oriented Scala and some of the more, mundane details of the language that might come up from time to time. But as new concepts come up through this course that you might need, I'll introduce them to you as we go. This is all you need to get started. So these are the basics of Scala. If you do want to learn more, there's a good book called Learning Scala by O'Reilly that I recommend. I don't get any money if you buy it or whatnot, but really good reference, and it does go into all those little details that I talked about if you want to learn more. But that's enough to get you started. I think that's enough for now. So let's just start to dive into some actual Spark streaming next, shall we? And congratulations, you now know Scala. Woohoo! So we've learned a little bit of Scala. Let's talk about Spark, and then we'll start to put it all together. So at a high level, what's Spark all about? Well, if you go to the Spark website, it describes itself as a fast and general engine for large-scale data processing. And, well, that's pretty much what Spark does. It is basically a framework that you can use for programming the distributed processing of large data sets. So it contains functions that let you import data from a distributed data store, like an HDFS file system or S3 or something like that. And it provides a mechanism for very simply and very efficiently processing that data. So, assigning functions that transform that data or perform various actions upon it. And it can do this on a cluster using the same code that you use to run it on your own desktop. So the same code can be run on your own desktop for development purposes, as well as on a real cluster of computers that can be scaled out as large as you want. So the whole power of horizontal scaling is available to you, where if you have a massive data processing job, all you need to do is throw more hardware at it until you can actually handle the whole thing. So that's kind of the whole idea behind Spark. It lets you do things you could never do on a single computer. And it is highly scalable. So the high-level architecture of Spark kind of looks like this. So basically you develop a driver program. So all the scripts that we're going to be writing in this course are driver programs. And they are built around one object called Spark context that sort of encapsulates the actual underlying hardware that you're running on. Now, on top of that, you are running some sort of a cluster manager, and there's one provided by Spark, or you can actually use it on top of a Hadoop cluster if you want, and use Hadoop Yarn as well. Also, Apache Mesos is an option too. And that cluster manager is then in turn responsible for distributing the work defined by your driver script among multiple nodes. So Every node that you run on, every machine, might have an executor process, which has its own cache and its own list of tasks. And it can split that data up to multiple executors. So if you have a massive data set, it might take one little chunk of it and put one chunk on each one of those different nodes on your cluster for parallel processing. And then your cluster manager figures out how to recombine all that data and pass it on to the next step if necessary. But the beautiful thing is that all this stuff on the right here just happens automagically for the most part. All you really concern yourself with as a Spark programmer is primarily the logic about how you're going to process this data. Spark and the cluster manager are then responsible for figuring out how do I distribute it in an efficient manner. Now, that's not to say you're totally off the hook for thinking about how it gets distributed, and we'll talk about tweaking these things later on, but for the most part, it just works. Why use Spark as opposed to something else? Well, a lot of people compare it to Hadoop MapReduce, and MapReduce was kind of the first technology that came out for doing distributed processing of data on a cluster. And Spark claims to run up to 100 times faster than MapReduce if you're running in memory, or 10x faster on disk. It is pretty fast. I mean, your mileage may vary, of course, and these are sort of best case scenarios, but Spark is generally preferred over MapReduce for that reason. It is generally a faster thing, and it's more modern, has a little bit more capabilities to it. In MapReduce, you'll find yourself writing a lot of things from scratch and kind of like wrapping your head around how to fit a problem into the MapReduce coding paradigm, whereas in Spark, it's generally a lot easier. The reason that it's so much faster is that Spark uses something called a directed acyclic graph, a DAG engine, to optimize its workflows. So one thing that's kind of neat about Spark is that nothing actually happens until you actually hit a command that says, I want to collect the results and do something with them. And once Spark sees an action like that, it will go back and figure out the optimal way to combine all of your previous code together and like come up with a plan that's optimal for actually producing the end result that you want. So it's a very different paradigm than how MapReduce code works, for example. And that's kind of the secret to its efficiency. A lot of people are using Spark in the wild, and I'm sure there's many more than just this list right now. There's a little website here at the bottom here you can look at if you want to see the latest list, and I'm sure a lot of big companies just aren't telling people how they're doing stuff internally. There's a lot of secrecy in the corporate world. But people who have fessed up include Amazon, eBay, NASA, TripAdvisor, Yahoo, and many, many others. I'm sure it's also used very widely in the financial industry as well. And pretty much anyone that has big data, I'm sure, is doing something with Spark these days. It's not really that hard. I mean, I think you'll be surprised at just how small these Spark driver scripts are that we're going to write. It's a very powerful language and a very concise language that we're going to be dealing with. And you can code in Python, Java, or Scala. Again, I'm recommending Scala because it's going to give you the most efficiency and probably the tightest code for dealing with Spark programs. But if you do want to stick with Java or Python, that's also an option. And Spark is really just based around one main concept, the resilient distributed data set. And this is basically an abstraction over a giant set of data. And you just take these RDDs and you transform them and you perform actions on them. And that's really all there is to programming in Spark. It's just a matter of trying to figure out the right strategy of how to get from point A to point B, where you have a set of input data and a desired set of results. But the actual code in between is generally surprisingly simple. Now, Spark itself consists of many components. So Spark Core kind of deals with the basics of dealing with RDDs and transforming them and collecting their results and tallying them and reducing things together. But there's also some libraries built on top of Spark to make some more complex operations even simpler. So one thing is Spark Streaming. That's actually a technology built on top of Spark that can handle little microbursts of data as they come in real time. So you can process a stream of data from a fleet of web servers, for example, or maybe a ton of sensors from an Internet of Things application as they come in 1 second at a time, and just keep updating your results as you go in real time. It just runs forever. Pretty cool stuff. Spark SQL allows a SQL-like interface to Spark, and you can even open up a little thing that looks like a database connection to Spark. So you can actually be using Spark SQL to run SQL-like queries on massively distributed data sets that you've processed using Spark, which is a pretty powerful thing sometimes. MLlib lets you do machine learning operations on massive data sets. It's a little bit limited in what it can do today, but it's always getting better. So if you need to do things like a linear regression or even recommend items based on user behavior, MLlib has built-in routines to do that automatically and distribute that across a cluster so you can deal with truly massive data sets and perform machine learning on them in a very efficient manner. Finally, GraphX We're not talking about the types of graphs that you see, in slide presentations where, revenue's going up and to the right or whatever. This is about graph theory, graph networks, right? So think about like, say, a social network where we have a bunch of individuals connected to each other in various ways. That's the kind of graph GraphX is talking about. And it provides a framework for getting information about the attributes and properties of that graph, and also a generalized mechanism called Pregel that we'll look at later in the course that will let you do pretty much anything you want to that graph in a very efficient and, again, distributed manner. So you could even throw it at, say, a massive social network data set and wrangle that into whatever information you need. So all more ways in that Spark is a very powerful technology. So why are we using Scala? It's probably not a language you know, and asking you to learn a new language is kind of a tall order, I realize. But again, Spark itself is written in Scala. So if you want to take advantage of the latest and greatest Spark features, Scala is the best choice. It's going to give you the best performance, and it's going to give you the best reliability. And it's also going to be the simplest code to look at when you're at the end of the day. There's not a whole lot of boilerplate that we need to add on to Scala code in Spark to get it to work. So it's very simple to work with once you know the basics. But it's really not as hard as you think. Another good thing is that if you have done Spark programming before in Python, you'll find that Scala code looks a lot like Python code in the context of a Spark job. So, look at these two examples here that do the same exact thing in Python and Scala. The syntax is slightly different. We have val qualifiers, whereas, in Python you don't need to declare that. And, we're using a list structure here, and the format for Lambda functions is slightly different, but by and large, it's going to look very familiar. So if you have done some Spark programming in the past with Python, going to Scala is not going to be too much of a leap, actually. So now we're going to go through a little bit more theory here before we go back to some code, so bear with me here. This is a very important concept with Spark, the resilient distributed data set. Basically the core object that you're going to be using throughout all of your Spark development. So it's an important concept to understand. Let's dive in a little bit. RDD, we're going to call them RDDs a lot in our course here and throughout our work, and it stands for Resilient Distributed Data Set. Basically it abstracts away all the complexity of trying to manage all the fault tolerance and distributed nature of the processing that happens with these objects. You can think of an RDD as basically an encapsulation around a very large data set that you can then apply transformations and actions to. And all you as a programmer needs to worry about is the functions that perform that transformation or what specific actions you want to perform on this data. You let the RDD abstract away all the complexity that Spark does for you of making sure that it's fault tolerant, resilient, making sure that if one node goes down in your cluster, it can still recover from that and pick up from where it left off. It makes sure that it's distributed, so it worries about all the details of how it actually splits up your data and farms it out to the nodes on a cluster. And fundamentally, it is a data set. So at the end of the day, an RDD is just a giant set of data, basically row after row after row of information, and that can just be lines of raw text or it can be key value information, as we'll see later on. So where do RDDs come from? Well, when you create a Spark driver script, you can create what's called a Spark context object. And if you're running just in the Spark shell, you get one automatically that's called SC. But when you're writing code, you'll explicitly write a Spark context, and you will tell this Spark context, okay, this is the kind of cluster I'm running on, this is the name of my job and whatnot. But once you have this Spark context, it is what creates RDDs for you. So basically, let's take a look at some examples. This first example here, we're basically taking a hard-coded list of integers, 1, 2, 3, 4, and using the parallelize method to create an RDD out of it. So that would actually be sc.parallelize if you were calling your Spark context sc, for example. Now that's not a terribly useful thing to do, because if you can actually hard-code a list of integers, well, that's not really big data to begin with now, is it? Why are you using Spark in the first place? But it can be useful for, setting up test cases or just developing your scripts with a small set of data initially. You can also, and this is more common, load up data from some file system, and it might be your local file system, or it could be a distributed file system, which is more likely in a real-world scenario. You might open this. In this example, we're just getting a big text file off of our hard drive, but you could also use S3N if you had it stored on Amazon S3, or HDFS if it was stored on a distributed HDFS file system on a Hadoop cluster instead of file. So if you have a big chunk of data somewhere sitting on a distributed file system, text file can let you do that. It can also integrate with Hive. Hive is basically another bit of the Hadoop ecosystem that lets you store big data in sort of a more structured way. And if you do have a Hive database, you can actually construct a Hive context given a Spark context, and then use that Hive context to issue SQL queries on your Hive data. And that will return back an RDD that you can then perform Spark operations on. And there are lots of other data sources that you can integrate with Spark and create RDDs from, including JDBC, Cassandra, HBase, Elasticsearch, JSON, CSV files, all sorts of different stuff. If there's a somewhat popular data store format out there, odds are there's a way already to integrate that with Spark and create an RDD from it. So once you have an RDD, what do you do with it? Well, there are basically two different things you can do. You can transform an RDD, basically apply some function to the data in an RDD to create a new RDD, or you can apply an action to it where you say, okay, I want to somehow do something to this RDD that reduces it down to the end results that I want to actually retrieve at the end. Let's talk about transformations first. So the most common operation you can do in an RDD is the map function. We'll look at examples of this later on, so just stick with the concepts for now. But what map does is apply a function to an entire RDD. So if you have an RDD full of data, and let's say you want to extract one field from it, or perform some parsing on it, or somehow, multiply everything that's in it, you would just pass in a function to the map function that says, this is how I want to transform every row of my RDD. So it'll go through your RDD one line at a time, and it will apply your function to each line and produce a new RDD that's been transformed. And under the hood, it will magically distribute that if necessary and deal with fault tolerance and whatnot. Flatmap, very similar concept. The difference there is that you don't necessarily have a one-to-one relationship between the rows of your RDD that you start with and the transformed RDD. With flatmap, you can look at an individual line and say, okay, I'm not going to actually output that at all to the new RDD I'm creating, or maybe I want to actually output multiple lines for each line in my new RDD. So if you don't have a one-to-one relationship between the rows, between the RDD you're starting from and the one you're transforming it into, flatmap is the one to use. The rest are pretty self-explanatory. Filter just takes a Boolean function that tells it, okay, I want to take out everything out of this RDD that doesn't fit some criteria. So that's a very good way to trim down an RDD initially and just pare it down to the data that you actually need. And the sooner you can do that, the better, because the less data you have to push around in Spark, the faster it will perform and the more reliable it will be. Distinct just returns distinct rows, so if you have duplicate rows in your RDD, that can get rid of them automatically. Sample creates a random sample from an RDD, also useful for testing. A lot of times you want to develop your script on your desktop and maybe take a little random sample of a larger data set so you can actually run it quickly on your desktop and iterate more quickly on your code. And finally, you can perform set operations on RDDs, unions, intersections, subtractions, and Cartesian products between any two RDDs and produce a resulting RDD from those operations. Let's look at an example of using the map transformation. So let's say again that we're just taking the hard-coded list 1, 2, 3, 4. So what we're doing here is we're taking our Spark context object, SC, and calling parallelize on it with a list, hard-coded list. And what this does is produce a new RDD that we're calling RDD, real creative, huh? And that RDD just contains 4 rows, 1, 2, 3, and 4. Now let's see how map works here. So getting into functional programming here a little bit with Scala, we're taking the RDD object and calling map on it, and the parameter we're passing in is actually a function. So this function here is just saying take as an input the value x and return the value x times x. So by passing in this function that squares every row in the RDD, we get back this squares RDD that's been transformed, and squares will contain the rows 1, 4, 9, and 16. So important concept here to grasp. Basically, you're passing in a function here to map that gets applied to every individual row in your RDD and creates a new RDD as the result. Okay, so we're seeing a couple of different functional programming paradigms here. One is the concept of having a little self-contained function being used as a parameter. And also notice that we're using vals here and not vars, which is also good practice for functional programming. Although map creates a new RDD, it doesn't modify the original RDD, so it returns a new one that can remain constant and immutable. All right, so just to reiterate that point, again, passing in this little function here of x and this funny little arrow with an equal sign, x times x, syntactically that's exactly the same thing as doing something like this, where if we had a separate function that we named square it that takes as an input an integer x parameter and returns an integer that is x times x, and then we could call rdd.map and pass in the name of that function. So this is just a more compact way of handling very simple transforms that can be done as a one-liner. Now if you do have a more complicated transformation you want to pass into map, it might make sense to actually split it out into its own function like we're doing here. But for simpler transformations like just squaring everything in an RDD, this syntax is going to be a lot simpler to use. Okay. Let's talk about actions that you can perform on RDD. So here's some of the more popular actions you can perform. There are certainly more that you can look up if you want to, but collect, that is what actually takes the results of an RDD and sucks it back down to your driver script. So at that point you can actually manipulate those results within Python, print them out, save them out somewhere, whatever you need to do. But remember, in Spark, nothing actually happens until you call an action on an RDD. When you call collect or one of these other actions, it will go back and try to figure out what's the optimal path for actually producing these results that I want. And at that point, it will construct a directed acyclic graph, execute it in the most optimal manner that it can on your cluster or on your desktop, whatever you're doing, and then return the results. So all these actions are what triggers something to actually happen in Spark. So again, collect just collects all of the data in the RDD and passes it back to your driver script where you can do stuff with it. Some other examples: count, if you just want to get a count of how many rows are in an RDD, that's a quick way to do that. Count by value will look at unique values in your RDD, each row, and give you back a count of how many times each value appears. So remember, an RDD can contain duplicate rows, that's perfectly fine. And if you do, you can use count by value to get a count of how many of each unique row value you have. Take will just take the first n results from an RDD. So if you just want to kind of take a little peek at what's in there for debugging purposes, that can be a useful thing to do. Just take, say, the first 10 rows of the RDD to make sure the format looks right and print it out. Common thing. Top, similar idea. And reduce, probably the more common thing to do with RDD. And this actually lets you combine together all the different values associated with a given key. And we'll go into that in more depth soon, but imagine you have key value pairs in your RDD and you want to reduce all the values for a given key together. Maybe you want to add them all up, maybe you want to multiply them together, maybe you want to smush them together in some way. Reduce is what will do that for you, and that can be a very powerful thing. So again, I want to repeat the point. Nothing actually happens in an RDD until you actually call an action on it. That is when your DAG, your directed acyclic graph, gets constructed. Spark figures out the optimal way to produce the results you want, and that's when things actually kick off and get executed on your cluster. So this can be a little bit confusing at times when you're debugging, right? You know, like you might have a bunch of transformations you're doing, like maps, for example, and you might have a print line in your script or something just to sort of like see what's going on at that point. Might not actually do what you expect because that map function didn't actually cause anything to get executed yet. Nothing actually gets executed until you later call an action like collect or reduce or count. And with that, you've got the basics of RDDs. It's going to sink in a lot more if we actually look at some examples. So up next, let's take a look at that ratings counter example that we made earlier in the course and try to understand it a little bit more in depth now that we understand these basic concepts of Spark, Scala, and RDDs. So now that we have some of the basics behind us, let's go back and take another look at that ratings counter program that we wrote back in Lecture 2, way back in the beginning of the course. We're going to break this down and try to understand a little bit more depth what's going on here. So if you open back up the Scala IDE, you should have this there still. And again, if you want to run it, you can go to the Run menu here, go to Run Configurations, make sure that ratings counter is selected here, hit Run, and off it will go again. And just to remind you what this script does, it's actually going through 100,000 real movie ratings and counting up the distribution of different rating scores. So you can see here we have 66,110 one-star ratings, 21,000 some odd 5-star ratings, etc., etc. So let's dive in and understand more about how this actually worked. Not a whole lot of code, so just keep this up and follow along with me and we'll go through it one line at a time. So let's dive into this code that counts up ratings by their rating value in a little bit more depth and understand what's going on at a deeper level, shall we? So let's take a look at the first few lines of code here. First thing we're doing is declaring what package this code lives under. So we just say package com.sundogsoftware.spark. Remember, that's the package name that we settled on while creating our project back in Lecture 2. And that's just a unique way of segregating off our code so it doesn't collide with other people's libraries. Next, we'll import the specific libraries that we need for this script. So we're going to import all the stuff from the Spark library that we need, specifically the Spark context object, and also we're going to import the log4j package because we're going to do some games with the log level. And that's actually the next line in the code there. I'm not going to go into too much depth on that, but we're just using log4j to say only print out error level messages. But the first bit of Spark code that we're going to run is this. So remember, the Spark context object is what we use to create our RDDs. So it's kind of the first thing that we need to make. So this is saying that we're going to create a new Spark context object. We're going to call it SC, which is an immutable Spark context object. And this local bracket star thing just means that we're going to be running it on our local machine. It's not going to be in a cluster at all, but this star indicates that we can actually use all of the CPUs, all the cores on our CPU, to actually distribute that locally if we need to. So if you do have a multi-core CPU running, it can actually still distribute it across those cores. And this is just a name for the Spark context itself. We're going to name it ratings counter, and that's just so that if we're looking in the Spark UI for progress on the job, we will know what to look it up under. So that will label this context in the UI. This job runs too quickly for us to actually do that, but later in the course we'll look at an example of doing that. So what's going on? First thing we do, we take that Spark context object we created and we call text file on it with a path to where the movie lens 100K ratings dataset lives. So the u.data file is what contains the actual ratings data, and it's going to import that one line at a time into a new RDD called lines. So lines is a dataset where every row contains one row of the input data that's in u.data. What does that actually look like? Well, here's a little sample of what's in that file. So the format here is basically user ID, movie ID, rating, and timestamp. So the way to interpret each line here is, for example, user ID 196, watched movie ID 242, rated at 3 stars at this time, and so on and so forth. Okay, so we're importing in our raw data that we're starting with here, and it lives in an RDD called lines at this point. Now the next thing we want to do, and this is generally good practice, is throw away all the information that we don't need. A lot of the time and resources that a Spark job requires, it depends on how much data it has to push around. So the sooner you can get rid of data that you don't need, the better. And that's what we're doing here. Basically, we're calling map on that lines RDD to transform it into a new RDD called ratings that parses out each line of the lines RDD and only extracts the field that we care about, that third field, which is the actual rating value itself. Remember, our end result is just the breakdown of how many times each rating occurs, so we don't really care about the users or the movies themselves or the timestamps. All we care about are those rating values. So let's take a look at what's going on here. We're calling the map function to transform that line's input RDD and passing it this function to transform it with. So basically this says take every individual line, call it X, convert it to a string, split it up into a list based on tab characters because I happen to know this file is tab delimited, and then extract field number 2 from that list. And remember, we start counting at 0, so field 0 would be the user ID, 1 would be the movie ID, and 2 is the rating. That's the one we care about. So basically this function gets applied to every line of the input file, and we get back a ratings RDD that will contain something like this, where only the rating survives. So now we have a ratings RDD where each row is just the actual rating value for each individual rating. So in this example, we start with this, we end up with this, just a list of 3, 3, 1, 2, 1, because those are the actual rating star values for each row of input data. With me so far? Okay, don't be afraid to pause and go back and rewatch things. This is all very important to understand. We're going through the real fundamentals of Spark programming here. So now what? Well, the end result we want is the count of each rating, how many times it occurs. And Spark has a handy function called count by value that will do that for you. Now remember, count by value is an action. So when we call this, it will actually cause Spark to go off, compute its directed acyclic graph, and actually start chugging away on all the data and distributing it if it can. And this is what we end up with. So count by value returns, takes an RDD, but it gives you back a Scala map object, where basically it maps identifiers, values, to how many times it occurred. And in this example, we're starting off with an RDD that just contains values of ratings themselves. Count by value will give us back a Scala map that we can then do whatever we want to, where it just maps values to how many times it occurs. So basically we now have at this point an RDD that we perform an action, count by value on, and returns Scala data in just a map format. For example, rating 3 occurred twice, rating 1 occurred 2 times, and rating 2 only occurred once in that data. Okay, makes sense? We have 2 3s, 2 1s, and 1 2. Now, the last thing we have to do is just display our results in a good way. So the first way we're going to do that, we're going to convert our result map to a sequence, which is something we can actually sort. And we're going to sort that by the first field. So this is just saying, take my results map, convert it to a sequence, and sort it by the actual rating value. And then we can take that resulting sequence, call for each on it to apply print line to each row. And that's what actually prints out each individual row of the results in sorted order. And our final results are rating 1 occurred twice, a rating of 2 occurred once, and a rating of 3 occurred twice in this very simplified example. Makes sense? It's not really that complicated, but it does illustrate just how simple it can be to perform big distributed operations with just a few lines of code in Spark. So that's pretty cool stuff. It's really just that easy. So if you need to watch that again, please do. If you want to go stare at the code some more, please do. I encourage you to do so. Play around with it. And let's talk about it in a little bit more depth as to what's really going on underneath the hood. We'll do that next. Let's talk a little bit about what's going on under the hood with that example we just ran of the histogram of ratings from movie ratings data. Good thing to understand what's actually happening under the hood, not just for academic reasons, but also because you want to make sure that you're structuring your Spark scripts in such a way that they will perform in an optimal manner. And having some idea of what's going on underneath the hood can help you do that. And we'll see as we get into more complicated examples later on how we can apply this knowledge. So let's take a look at that little ratings counter example that we ran in the previous lecture. So what actually happened when we called count by value on that RDD? That was kind of the last step in our script, and it actually was an action on an RDD, which caused Spark to go back and actually figure out an execution plan for how to actually get the results we asked for. So what happens there? Well, it keeps track of all the things that we've chained together from different RDDs and how they connect to each other. And based on that information, it constructs a directed acyclic graph. In this case, it might be a very simple one that looks a little bit like this. Basically, we start with a text file command that imports a bunch of raw data into an RDD. We then map that RDD to parse out the information that we care about, which is just the ratings themselves. And then finally, we call the count by value action to total up all of the different numbers of each rating type. So that's the execution plan. And you can see here a little representation of how that gets manifested. So we have, in this example, 5 different lines of ratings data, and these get piped down where they are mapped to just extract the actual ratings themselves, and finally we add them all up together. Now, an important thing to realize here is that with map there's a one-to-one relationship between each input and each output row of the RDDs. So we can actually keep everything partitioned in the same manner at that step, right? Because these are all just a bunch of parallel lines. We're just taking a bunch of data and transforming it. So that can all happen very easily in a distributed manner. But what happens when we call count by value? Well, we might have to shuffle things around here, okay? So this is where things get a little bit more complicated. You know, in this case, we have a couple of these different rows here getting combined together into that final result, and these two ones kind of like have to get moved around to this final result too. So this is what we call a shuffle operation in Spark, and that can actually cause Spark to have to push a bunch of data around on your cluster, and that can be a very expensive operation. So a lot of times when you're optimizing Spark jobs, you want to be thinking about how can I minimize shuffle operations, and how can I make sure things remain parallelizable when I'm mapping things. So once it has that execution plan, that's basically what Spark does. It looks for places where you need to shuffle data and uses those as ways to delineate stages. Okay, so what happens is Spark will then break this job up into, say, 2 stages, where the first stage is that text file where we read in the data and then we map it just to extract the data we need. That can all be run together in parallel, okay, as one stage. But then on this count by value command, things need to get shuffled, so that needs to be handled as a second stage, okay? So these stages are created based on chunks of processing that can be done in a parallel manner without shuffling things around again, okay? And when you actually run a Spark job, it will give you in the output, if it's actually being distributed, indications of what stage it's running, and that's what it's talking about. And then, once we have our stages, it will then split those stages up into tasks. So this is where things actually get distributed. Now notice that we have these sort of parallel processing, parallel lines of transformations going on here. Maybe it will break up these two on one node of your cluster, and these two into another node of the cluster, and this one onto yet another one. So the tasks just break up parallelizable tasks, if you will, for lack of a better word, into discrete pieces that can be processed individually and in parallel. Okay, makes sense? So we start with an execution plan. The execution plan is broken into stages based on things that can be processed together in parallel that don't have a shuffle involved. And then stages get broken up into tasks that are distributed to individual nodes on your cluster. Okay, that's all there is to it. And then it just goes and does it. So it's up to your cluster manager at that point to actually get the data where it needs to be and collect it all back to where it needs to be in the end in your driver script. And the machine starts running and you get back your results. So at a high level, that is how Spark works internally. And it's just good to understand that. Again, when we're trying to optimize things later on, we'll be talking about things like explicitly partitioning your data and trying to structure things in a way that reduces the amount of shuffles. So keep that in mind. All right, let's move on to another real-world example next. Let's talk about key value RDDs. Very common thing to deal with, so we want to understand how they work. Basically, any time that you have to aggregate information down to some key value, you're going to be using key value RDDs. For example, let's consider a case where we need to figure out the average number of friends broken down by age in some fake social network that we have. So let's imagine that we have a data set that's for each person has their age and how many friends they have, along with whatever else information we might have. Okay. Now, if I want to actually figure out the average number of friends broken down by age, I need to somehow aggregate all of the friend counts for every given age. So in this case, the key is the thing that we want to aggregate on, the age, and the values will be the things that we're aggregating, the friend counts. So we want to aggregate together all these friend counts broken down by age and end up with what's the average number of friends a 20-year-old has for the key 20, what's the average number of friends that a 33-year-old has for the key 33, and so on for all the other ages. Okay. So how does that work? Well, syntactically, all we need to do is represent values as not just a single value, but as a tuple of two values. So in our previous examples, we had RDDs where every row represented a line of input text or every row represented an integer or something. You can also represent a tuple. And if that tuple contains two objects, then Spark can treat that automatically as a key value pair. And there are some special things it can do with that sort of information. So let's look at this example here. In this case, we're taking an RDD that contains perhaps one bit of information per row and transforming it into a key value RDD. And all this transformation function is doing is mapping RDD where each line x gets transformed to the tuple x1. So that's creating a key value pair of x, the original value, that's the key, and the value 1 for each row. Okay? And that's it. There's nothing special beyond that. You now have a key value RDD just by the fact that you are storing tuples with two things in them. And you can actually store even more complicated structured data as well. If you can still have a tuple where you have some value as the key and some more complex tuple as the value. So you can nest information and structure it as complicated as you want, but at the end of the day, as long as you have at the top level two things, a key and a value object of some sort, that counts as a key value RDD. Now, what can you do when you have a key value RDD? A bunch of things that you couldn't normally do. One very common operation is reduce by key, and this allows you to provide any arbitrary function you want for combining values together and grouping them together by key. So in this example here, take a look at the syntax. We're actually taking a tuple xy here, okay, and transforming that to x plus y. Now this is a little bit confusing, so stay with me here. Xy here does not represent a key value pair. It actually represents two values that need to be combined together. So reduce by key is saying, okay, I want a function that will take two values for the same key and define how these things get combined together in my new RDD. So let's say that I just want to add up all of the total friend counts for everyone who's 20 years old. I might hit this for the key number 20. The key 20 never changes. That's going to be automatically transferred over to my new RDD, but what does change is the value, where I'm going to aggregate together all of the values for key 20. So this function says, given two values for the same key, how do I combine them together? In this case, I want to add them together, and that will take every value found for a given key and add them all up, two at a time, okay? Why is it two at a time? Well, remember, this might be distributed, so we can't just take everything all at once and add them all together in one big function. It has to do it piecemeal, one bit at a time. So we need to tell Spark, given a running total and some new value, how do I combine them together? And that's what this function does. It'll make more sense when we look at some code. We can also do group by key, and if you don't want to actually aggregate all these values together for a given key, you can group them all together into a big old list. And that's what group by key does. So if I just want to collect together all of the values seen for a given key, group by key will return an RDD that is just that. It will give you back key values where it gives you each unique key, and the values will be a list of all the values associated with that key. Okay. We can also do sort by key, which will just sort an RDD by its key values. Very straightforward. And you can also retrieve individual RDDs of just the keys or just the values of a key value RDD, and the keys and values functions will do that for you. Some other things you can do. You can actually do SQL-style joins if you have key-value pairs. I mean, if you think about it, a key-value RDD is kind of a lot like a NoSQL database, isn't it? And we can do some database-like things since we have some more structured data now. You can do joins of various flavors, and we'll look at some examples of that later in the course. A little bit too complicated to get into now, but just know that it is possible to do SQL-style joins when you have key-value RDDs to work with. One other thing, if you're just going to be mapping the values in a key value RDD and you're going to leave the keys alone, it's going to be more efficient to use the functions map values and flatmap values instead of just map and flatmap. Okay? So if you're going to map just the values of a key value RDD, use map values and flatmap values, it'll be simpler from a syntactic standpoint and also more efficient. So let's dive into an example to make this all real. I mean, it's nice to talk theory and all, but it doesn't sink in until you actually do it, right? So let's imagine, if you will, that we have some social network data to play with, and each row of information in our raw input data looks something like this. So we have a bunch of comma delimited rows of information that consist of a user ID number, the user's name, the user's age, and the user's number of friends. Okay, and you can probably tell from this fake data that I'm one of those weird Star Trek fans that you hear about and probably are best to avoid. So what we're trying to do, again, just to remind you of the purpose of this example, we're trying to find the average number of friends for a given age. So in this case, we have Will is a 33-year-old in our fictitious data, and so is Jean-Luc. And Will has 385 friends. He's super popular. Jean-Luc, he's a little bit socially aloof, so he only has 2. So we want to somehow figure out how to combine these two guys together because they both have the same age and figure out their average number of friends, and so on for the remaining people in our data set as well. So let's look at some code. How do we get started? Well, again, the first thing you want to do is parse out your input data and throw away the data you don't need. So that's what we're going to do with our parse line function here. Given a line of input data, we're going to split it up based on the comma characters that we find in it. And we will access fields number 2 and 3. And remember, that's actually the third and fourth fields because we start counting with 0 here. And we will transform that field number 2 to an integer and interpret that as the age. And field number 3 will also be interpreted as an integer, and we'll store that as the number of friends for this person. And what we'll return is a tuple, a key value pair, of an age and a number of friends for this person. Now notice we've completely discarded the user ID and the user name from that input data because it's irrelevant to the problem we're trying to solve. All we want to know is what's the average number of friends for a given age. Who these people are doesn't matter, right? So when we're done with this step, basically we take sc.text file and load in our raw data, and then we map using that function we just wrote, and it gives us out something like this. So from our input data, we end up with a key value RDD, where the keys are the ages for each individual and the values are the number of friends for each individual. So we haven't done anything to aggregate things together yet. All we've done is create a key value RDD in preparation for the operation we need to do. So now what happens? Well, things get a little bit fancy here. So take a look at that big scary line of code there. It's a little bit intimidating, but it is a common practice in Spark scripts to chain things together in this manner. So if you look at it, we're actually taking the RDD, the key value RDD of ages and number of friends. We're calling map values on it to just transform the values of each one. And then we're chaining together yet another operation on top of that with a dot reduce by key. So basically this is saying start with our key value RDD of individuals, ages, and number of friends. We're going to map that using this function here, and then take the resulting RDD from that step and apply reduce by key to it as well. So we're basically doing 2 steps in one here. Pretty common thing to see. But let's break it down into its components and talk about what's going on. So the first part of this statement is rdd.mapValues using a transformation function of x to x, 1. So all we're doing here is saying transform each number of friends to a tuple that contains the number of friends and the value 1. So what's the method to our madness here? Why am I doing that? Well, we need to end up with the average number of friends in the end, remember. And to compute an average, you need 2 numbers. You need the grand total and you need the number of instances, the number of things that you added up, and divide those two things to get the average. So thinking ahead a little bit, what I'm going to do is transform all of these key value pairs of age to number of friends to a slightly more complicated format here, where the key is still the age, but the value is now a tuple itself. That is the number of friends and the value 1. And you see what happens when I start to add these all together. So if I add together both fields of these tuples for each given key, I will end up with both the grand total of how many friends in total all the 33-year-olds in the world had, and I'll also end up with the number of 33-year-olds in the world, okay, because I add up all those ones for each individual that I saw. That's what I'm trying to do here. And that's what reduce by key does in this next clause of this expression. So that's going to take two of these values, okay? So remember, reduce by key, the x and y is not a key value pair, it's two different values. And in this case, the values are two different tuples, where the first value is the number of friends and the second is the number 1. I'm going to apply this function to add them together, where I just say the result will be the addition of the two number of friends coming in and the two number 1s that come in. Okay, so as we keep a running total over the entire data set, what we end up with is a grand total of how many friends in sum all the 33-year-olds in the world have, and how many 33-year-olds there are in our data set. And of course, it will do that for every unique key automatically. Makes sense? A little bit complicated. This is the most complicated thing we've done so far in the course. So if you do need to go back and stare at this slide some more, don't be afraid to do so. I won't judge. All right, next thing we need to do is actually use that information to compute the averages themselves. So remember, at this point we have key value pairs where the keys are the ages and the values are the grand totals of the number of friends and the number of people of that age. All we need to do now is divide those two to get the averages, and that's what this map values function does. It says for a given value, which in this case is one of these tuples, we're going to just take the first field divided by the second field to get our final result. So in this particular example for 33-year-olds, we might end up with 33, the age 33. We're going to take out the value and map it to just divide these two fields. 387 divided by 2 works out to 193.5, and we end up with a final result for 33-year-olds having an average number of friends of 193.5. Not sure what half a friend looks like in reality, but let's not go down that line of thought. It's a little bit disturbing. Finally, we need to collect our results, and remember, nothing happens until we actually call an action, so we're going to collect the results here into a plain old Scala object, and then we're going to sort it and apply the print line command to each individual entry, and we get the final results that way. So with that, let's go take a look at the actual code. So let's make it real. Let's actually run that friends by age script and actually run it on some data here and actually use Spark for it. So I've opened up two different folders here on my hard drive, and if you want to follow along, please do the same thing here. One is the C Spark Scala folder that I created earlier in the course, and that's kind of our directory that we're going to use for the course itself, all the data and scripts and projects that we're going to be running. And over here I have the course materials that I had downloaded all together earlier in the course, and that's in my Download Spark Scala folder. So first thing I need to do is get a copy of the data that we generated for this exercise, and that's going to be the fakefriends.csv file. Click on that and preview it. You can see that it has the format that I described in the previous lecture, where we basically have a user ID followed by a username, the user age, and the number of friends. And we've fabricated a bunch of different people at random using a library of fictitious names of various Star Trek and Deep Space Nine characters, because I'm a nerd. But again, all we really care about are the ages and number of friends. That's the information we're trying to aggregate, right? So let's go ahead and copy the fakefriends.csv file over into my project directory. All right. Now the script we're going to use is in the friendsbyage.scala, but we're going to have to import that into our package. So let's go ahead and open up the Scala IDE. Make sure your workspace is set to your workspace for this course. And up it should come. All right. Open up the Spark Scala course project, open up the source folder, and we're going to select the com.sundogsoftware.spark package, right-click on that, Select Import, General, File System, and then browse to our download directory. In my case, that's Downloads Spark Scala. And we're going to select the friendsbyage.scala script and import that into our package. There we have it. So now I can open up that package and double-click friendsbyage.scala and take a look at our code. And it's pretty much what we described in the previous lecture, but let's review again what's going on here, just for the sake of letting it sink in. We have our usual boilerplate stuff up here where we're declaring the package that we're in. We're importing the Spark libraries that we need and the log4j package that we need for this script. We are creating a friendsbyage object, and within that we have two functions. One is our main function, that is where all the action happens, and then we also have this parseLine function. And its job is to just take our input data and extract the information we actually care about. In that case, it's going to be the age and the number of friends for each individual in our input data. So again, we're going to take each line of raw input, split it up based on commas, because it is a comma-separated values file. Extract the age from field number 2, which is actually the third field. We start counting at 0. Convert it to an int. We extract the friends number from field number 3, which is the fourth field, convert it to an integer, and we return a tuple of the age and the number of friends for each individual. And this becomes our key value pair for the key value RDD that results from this operation. Okay. So putting it into action, we go to our main function. We set our logging level to error to reduce all the log spam, create our Spark context to run locally using every core, and we're going to name this context friendsbyage. We call text file on the Spark context to load up the fake friends.csv file we just copied in to a lines RDD. At this point, it's not a key value RDD, it's just an RDD where every value is a line of raw input. But then we apply our parseLine function to that RDD. We call lines.map, passing in the parseLine function as a parameter to map, and that will apply the parseLine function to every individual input row and give us back a key value RDD, where the RDD consists of two integers, which represent an age and a number of friends. So the key is our age, the value is the number of friends. And here's that big scary line again that we talked about previously, where we apply two steps in one. First thing we do is we take those key values of ages and number of friends, map them so that the values are not just a raw number of friends, but a tuple of the number of friends and the number 1. And that just allows us to add up both the total number of friends and the total number of people for a given age. And that's what reduce by key does. It says given two of these values, which are tuples of total number of friends and total number of people of a given age, we add them all together, one component at a time. So we add together every friend count and every number 1 for each individual to end up with our resulting totals by age RDD, which will contain one row for each unique age that we've seen and the grand total in a tuple of the total number of friends for that age and the total number of people we saw from that age by adding up all those ones that we created. Okay? And that gives us the numbers that we need to actually compute the averages. So by mapping those resulting values, by just dividing the first and second elements of each tuple, the total number of friends and total number of people, we end up with the average. And that goes into our averages by age RDD. We collect the results and we sort them and print out each line. Let's see if it works. So to do that, we need to create a run configuration for this particular class. Remember, we called this friendsbyage was the name of our object. So go to run configurations, and we're going to create a new Scala application. Just double click on that. We will call this friendsbyage. The project is correct, Spark Scala course, but the main class is going to be com.sundogsoftware.spark.friendsbyage. Okay. And now we can hit run and see what happens. Hey, it worked. So there you have it. Now you can't read anything into this data because it was all just randomly generated. This is not real data, but it could be. Maybe you're working at a big social network company and you have something similar. But to interpret this result, for example, the average 18-year-old in our fake data had 343 friends. The average 40-year-old had 250 friends. The average 57-year-old had 258 friends. It would be pretty interesting to see what that would look like with real data. but that shows you how to do it. And there you have it, a working key value RDD example. Feel free to play around with it, mess around with it, try to change the results, and get familiar with it. There you have it. So it's one thing to watch me write code and go through it, but it's another thing to do it yourself and get your hands on it. So I encourage you to do so. Here's a little challenge for you. Why don't you go back to that friends by age example and modify it to actually show the average number of friends by first name instead. Should be pretty straightforward. It's just a matter of extracting a different field from the source data and using that as your key. And obviously you're not going to convert names to integers, but the objective here is just to get your hands on this code and actually start modifying it yourself and get some confidence that you can actually go in there and fiddle with some Spark Scala code and actually make something work. So I encourage you to do so. See if you can go and do that. Find the average number of friends by first name as opposed to the age. And that would actually be an interesting thing to find out in the real world too. So give that a try, and I'll see you in the next lecture. Let's talk about the filter operation on RDDs and how you can use that to strip out information that you don't need from an RDD and save Spark from doing unnecessary processing. We're going to apply this to a real example using some real weather data. And the thing we're going to try to do is take a bunch of weather data from Europe and find the minimum temperature for a given location for an entire year, the year 1800 to be precise. So let's talk about how that works. Now, filter functions are pretty straightforward. You just pass in a function that returns a Boolean value, and that Boolean true or false value dictates whether or not a given row in an RDD gets retained or not. If it fails that condition, then that entry is discarded from the RDD. So let's say that our weather data has different kinds of information in it, and there's a field that indicates what kind of data a given line of input represents. It might have a minimum temperature for the day, it might have a maximum temperature for the day, and it might have a precipitation amount for the day. Now, all we're interested in finding in this example is the minimum temperature overall for an entire year for a given place, so we don't care about the maximum temperature lines, we don't care about the precipitation lines, we can throw those away. And this filter operation here is a way to do that. So let's imagine that we have an RDD that already has parsed out information about what's in this weather data. We could call a filter function that takes a given input line, checks whether the second field of it is equal to tmin, in the case that the second field is what indicates the data type. If it is, it keeps it. If not, it just gets discarded. And the resulting RDD that only contains tmin lines then gets put into the new min-temps RDD that we've created. So again, you use the filter function on an RDD to provide a Boolean function that dictates whether or not a given entry in an RDD gets retained or not. Let's make it real, look at some actual data. So we do have some actual real weather data from the year 1800 for a couple of locations. And this is the format that we have. The first is a weather station identifier, followed by a date, what kind of data this line represents, and the associated data with it. So for example, this weather identifier, I forget if it represents Paris or Prague, it's one of them, but it says that at this weather station, on January 1st, 1800, the maximum temperature was negative 7.5 degrees Celsius. Okay, so the data formats here is a little bit strange. It's actually tenths of a degree Celsius. And also for that same place on that same date, the minimum temperature was negative 14.8 degrees Celsius. And likewise, we have a precipitation line that we don't care about, because all we care about are minimum temperature lines. We have a maximum temperature for another weather station and a minimum temperature for another station all on that same day. Now in this example, again, we only care about minimum temperatures for the problem we're trying to solve, so we're going to take in all these lines of input data, we're going to parse them out, and then we're going to throw away everything that's not a tmin entry. So how does that work? Well, let's start by reading in the raw data and parsing it, making it more structured. So what we're going to do is take our Spark context and call a text file to import our comma-separated value list for the year 1800's weather data. And then we're going to apply this parse line function as a mapper on that raw data. So what does parse lines do? It splits it up into individual fields based on comma characters and parses it out. So the first field is the station ID. Field 2, which is actually the third field, is going to be the entry type. So that's going to be tmin, tmax, or precip. And then for the temperature, we'll extract that from the fourth field, field number 3, convert it to a floating point numerical value. Remember, that's tenths of a degree Celsius, so to convert it back to Celsius, we multiply times 0.1, and then to convert from Celsius to Fahrenheit, we'll multiply by 9/5 and add 32. So this reads in the temperature value and converts it to Fahrenheit for us. All right, so at this point, we're going to return a tuple that contains 3 values, the station ID, what kind of entry it is, and the temperature. So the next thing we want to do is discard all of the data that's not a minimum temperature. So to find the overall minimum temperature for a location throughout the entire year, we're going to look at the minimum of all the minimum temperatures reported for that location. So what we're going to do with this filter operation, like we looked at before, look at every input line, and if that second field, which indicates the data type, is equal to tmin, we'll keep it. Otherwise, we'll throw it away. So at this point, we have a new RDD called mintemps that contains parsed information, but only tmin data types. Now, we have an RDD that contains three things. We have the station identifier, tmin, and a temperature. That tmin is no longer meaningful, right? Because everything in the RDD has a tmin in it. So let's just get rid of it. Again, the less data that we have to deal with, the better. So that's what this next line does. We'll take that mintemps RDD we have now, apply this mapping function to it. That takes that tuple of 3 data points and converts it to a tuple of 2 data points. And you know what a tuple of 2 data points is? A key value RDD. So at this point, station temps is a key value RDD, where the key is the station identifier, which is just the location, Paris or Prague, whatever it is. And the value is the temperature, the minimum temperature seen for that day. Finally, we'll do a reduce by key operation. And so this is a little bit different than where we added things up or made averages. Instead, we're going to use the min operator to preserve the minimum value seen as we go through all of the minimum temperatures seen for a given station ID. So station temps, to remind you, is a list for every day in our data set for a given station ID and the minimum temperature. So we're going to aggregate everything together by station ID, that key value, and we're going to look at the minimum min temperature seen across all the minimum temperatures reported for that station throughout the year. So that's what this reduce function does. For 2 given tmin values for a given location, for a given key, it will preserve the minimum of those 2. And by doing this, it will find the minimum overall temperature reported for that station for the year. Finally, we just need to collect the results and print them out. So we will call collect to transform our RDD back into a Scala object that we can iterate through, which we do here after sorting it. And there are more compact ways of doing this here. I'm doing this in 3 different lines just for clarity, but we'll extract the first key value and assign that to the station ID. The temperature will be in the second one. And then we will format that temperature so that it only has 2 decimal places to the right. And print out the final results for each station that we run into and take a look what we have. So let's go and run it in the next lecture and see what we come up with. So instead of just talking about this code, let's actually run it. So as before, I have 2 windows open up here. One is my C Spark Scala folder, where I'm going to be keeping all the materials and projects for the course as we go. And then I have my Downloads Spark Scala folder here, which is where I downloaded all of the course materials to. So let's go to the 1800.csv file here. That is my actual weather data. That's real weather data from the year 1800 in a couple of cities in Europe. And you can click on that and kind of preview the contents. It's what I described earlier. You have a weather station identifier, a date, what kind of data it is, which might be Tmax, Tmin, or precipitation. And the actual temperatures in the case of Tmax and Tmin are represented as tenths of a degree centigrade. So let's go ahead and copy that and paste it into where I'm working from. All right. Now let's open up the Scala IDE. Again, make sure the workspace is set to where you just pasted that file into and where your other projects are. All right, now let's open up the project and the source folder and click on the package, com.sundogsoftware.spark. Right click on it and say import. Go to General File System, hit Next, and browse to where we downloaded the course materials, as usual. For me, that's under Downloads and Spark Scala. We're going to select the min temperatures.scala file here and hit Finish. And we can open up the package now and take a look at it. All right, let's close all the others at this point. Don't want things to get too messy. So this is the same code we talked about in the previous lecture. Let's take another look at it because it makes more sense when you see it all together sometimes. As usual, we start with the package name that we're going to be under and we import the things we need. You'll see we're actually importing this min function here as well as the usual suspects. We're going to create a min temperatures object that contains our Spark driver script. We have our main function where everything happens, and we also created a function called parseLine that does exactly what it says. It parses a line of raw input data from that 1800.csv file and transforms it into a tuple of station ID, entry type, and temperature. Station ID being where the weather measurement was taken, entry type being one of Tmin, Tmax, or precip, and in the case of Tmin or Tmax, we will extract a temperature field in Fahrenheit. And all this code does is split it up based on commas, extracts the station ID from the first field, the entry type from the third field, and the temperature from the fourth field, and then it converts that temperature while it's at it from tenths of a degree centigrade to Fahrenheit. All right, so let's dive in here. Set the log level to error so we don't get a bunch of log spams. Create our Spark context that runs on our local machine using every CPU core. We're going to name it min temperatures. All right, first things first, load up our actual raw data file, 1800.csv, into a lines RDD. Then we're going to map it using our parseLine function that will convert that into more structured data. That is a tuple on each line of station ID, entry type, and temperature. Next we're going to do is filter out anything that's not a minimum temperature, because again our goal here is to find the minimum temperature across an entire year of data for each given station ID. So we're going to pass in this filter function that takes in a given line, looks at the second field, which is the entry type again. If it's equal to Tmin, then it lives. If it's not equal to Tmin, it dies. So we end up with a min temps RDD that contains only Tmin entries. Next thing we do is strip out that middle entry type field because it's no longer meaningful. Everything in here is a Tmin, so why would we carry that Tmin data around everywhere? Again, you want to strip out all the data you can to minimize the amount of data that needs to be pushed around during a shuffle operation. So that's what this map function does. It just takes that tuple of 3 values and converts it to a tuple of 2 values. And guess what? That makes it a key value RDD, where the key is now the station ID and the value is the minimum temperature seen for every day in a given year. Okay, so at this point we have a station temps key value RDD that has keys of station IDs in string format and values of minimum temperatures seen for every day of the year for that station. Finally, we'll call reduce by key to find the minimum temperature for each station ID. So what this does is it takes that station temps key value RDD, looks at every minimum temperature reported for every day of the year for each station, and preserves the minimum found overall for that station. So as two different values, two different temperatures are compared to each other, we just take the minimum of the two. So what we end up with is the answer we want, this min temps by station RDD, which is just going to be keys of station IDs followed by the minimum temperature seen across the entire year for that station. We then collect the results, sort it, extract them, format them the way we want, and print them out. So let's go see if it actually runs. Go to the Run menu, create Run Configuration, double-click Scala Application, and we're going to name this min temperatures. And the main class is com.sundogsoftware.spark.minTemperatures. Let me double check that's the correct object name. I can't actually scroll up there, but I believe it is. Let's hit run and find out if it works. Well, it's doing something. Hey, there we have it. It works. So for this station ID, the minimum temperature reported was 7 degrees Fahrenheit, 7.7 to be precise. And for this other station ID, the minimum temperature found in the year 1800 was 5.36 degrees Fahrenheit. Now, as I said, this is Paris and Prague, as I recall, so they would be pretty similar. They're not that far apart, so that makes sense. That kind of passes our sanity check. And you should always, do that with your end results to make sure there's not a potential bug that you could have caught. All right, so that's our example of using filter and another example of using key value RDDs. Now, at this point in the course, I think you're about ready to actually start writing some code of your own, maybe start fiddling with this a little bit. So that's my challenge to you right now. What if you were to modify this script to instead find the maximum temperature found for a given station ID throughout the year? What changes would you make? Why don't you hit pause and go try that out? So remember, instead of Tmin, we're going to be looking for Tmax entries. And instead of trying to preserve the minimum temperature found, we'll be preserving the maximum temperatures found. So hit pause, go take a crack at that. Make sure you also look for, things where we're talking about minimum temperatures and change it to say maximum temperatures, things like that. But, a very simple way to get your feet wet with some Spark development. So give that a try. Hit pause, and when you're ready, we'll come back and take a look at how I did it. Ready? Okay, let's move on. So we're going to go back to the package here and right-click on it and import the max temperatures.scala from where we downloaded everything. Again, for me, that's under Downloads. Open up. Spark Scala. Max temperatures.scala. And we'll import that in. Let's double click on that. Take a look at what I did. Nothing too crazy here. All I did was change all the object name from min temperature to max temperature. The parsing works exactly the same way, but we're naming this thing max temperatures now, and now we are filtering out things that are not just Tmin, but only things that are Tmax. The other relevant change is instead of calling min here in our reduce by key operation, we're calling max to find the maximum temperature throughout the entire year for each station. And again, I just changed the wording here to reflect the results that we want. So let's go ahead and run that and see if it works. Compare that to what you've done, and hopefully you did about the same thing and got the same results. But if you want to check for sure, let's see if your end results are the same as mine. So let's go to run configurations, and we're going to create a new one called max temperatures. Class here is going to be com.sundogssoftware.spark.maxtemperatures, and we'll run that. And in this case, we end up with an answer of 90.14 degrees for both stations. And seems a little bit coincidental, but I checked that really is the correct result. So if you ended up with an answer of 90.14 for your code of finding the maximum temperature for each weather station in the year 1800, then you did it right. Congratulations. Good job. We'll do more and more hands-on stuff as we get through the course, but there you have it for now. You might ask yourself, why are there only 2 weather stations in here? Well, there wasn't a whole lot of good record keeping in the year 1800, it turns out. If you get data from later years, there'll be more and more information into it. So if you do want to track that data down and play with bigger data sets, feel free to do so. But otherwise, there you have it. Some practice filtering key and dealing with key value RDDs yet again with real weather data. Woohoo! So if you'd like to challenge yourself, here's an idea. Go back and modify this code to actually figure out what day had the most precipitation for each location that we have precipitation data for. And the general concept will be the same for the code. You're just going to parse out the data a little bit differently and treat it a little bit differently, right? So have at it. See if you can figure out what day had the most precipitation in the 1800.csv data file that we have. Give that a shot, and I'll see you in the next lecture. So we touched on this a little bit earlier, but let's go into more depth about the difference between the map and the flat map operation in Spark. And to illustrate this, we'll look at an example of counting up the occurrences of each word in a real book. So we'll do that right now. So to review, the map operation transforms one RDD into another using some function that you provide to it. And there's always this one-to-one mapping between the RDD you start with and the RDD you end up with. Every row in your RDD that you start with is going to result in one row in your transformed RDD when you're using map. So as an example, let's look at this. Let's say we start with a RDD that contains 4 lines of information, and each row of the RDD contains, a little snippet like the quick red. Next row contains fox jumped, then over the lazy, then brown dogs. Let's say we have this little snippet of code here that loads that up into a RDD called lines, and for some reason we want to create a highly distributed scalable job using Spark that converts things to rage caps. So we can pass in a function like this that will convert everything in that to uppercase and return that into a rage caps RDD. So map here in this example will take every single line of input data, convert it to uppercase, and return a new RDD where there is a one-to-one relationship between the number of input lines and the number of output lines. So we end up with the quick red fox jumped over the lazy brown dogs, but really, really loudly yelling at you, right? It's all capitals. Now, in contrast, flatmap can generate many lines from one input line, or 0 lines even. Sometimes you just might want to throw data away as it comes in. So let's look at this more interesting example. We start with the same input RDD called lines, but this time instead of converting it to rage caps, we're going to split it up into individual words. So we want to take an RDD of sentences or snippets of sentences and convert that into an RDD where each row contains a single word. So we end up with many more rows in our resulting RDD than we started with. So here's an example of how flatmap can do that. Now flatmap, instead of returning a single value in the function you pass into it, will return a list of values, and that list can contain any number of results or maybe even no results at all. So take a look at this. In this example, we're passing in this function, x gets transformed into x.split based on space characters. And what split does, if it's given a string, is it returns a list of strings that are delimited by the character you pass in. So basically this is saying I'm going to take whatever string you pass into me and give you back a list of strings that are separated by spaces. Okay? And then flatmap will take each element of that list that comes back and produce a new row out of it. So the resulting words RDD contains one row for every individual word, or more specifically every string that's separated by a space in the input data. Okay? So now we start off with 4 lines of data, but we end up with, well, however many words that we have in that data to begin with. So that's the main difference between map and flatmap. Map is a one-to-one relationship between the input data rows and the output data rows, whereas flatmap can have a one-to-many relationship, or a one-to-one relationship, or a one-to-none relationship, whatever is appropriate for what you're doing. And a quick note for people who are a little bit more advanced in Scala, you can also use the sum and none constructs in Scala to do a flat map as well. If you return sum and none, none will be interpreted as no values at all, kind of like returning an empty list. So there'll be examples of that later in the course. So to make it real, let's write a script that actually puts flat map into practice, and then it'll make a lot more sense. What we're going to do is count the words in a book, and just for copyright reasons, I'm going to provide the text of a book that I wrote, which is this book, but whatever. I'm giving you the text of it for free as part of the course as sort of an exercise in natural language data that we can mess with. So let's go ahead and write a script that uses flatmap to actually count the occurrences of each individual word found in this real book. Alright, so as before, I have 2 folders open up here on my desktop. One is the directory that we're working out of for the course, which for me is C Spark Scala, and then over here I have the folder that I downloaded all the course materials into, which for me is in my downloads folder under another Spark Scala folder. First thing to do, select the book.txt file, and if you preview it over here, you can see that it contains the text of a book I wrote that is completely unrelated to this course, but is just a source of a bunch of text data that we can play with. So let's go ahead and copy that and paste it into the C Spark Scala folder that we're working out of. Alright, next we're going to start up the Scala IDE. Make sure we're in the correct workspace, which should be the same folder that we're working from. And open up the Spark Scala course project, go under source, and the com.sundogsoftware.spark package, which contains all the code we've written so far in this course. So let's right click on that package and say import from the general file system. And now we'll select the course materials folder, which for me is going to be under downloads Spark Scala. Hit OK, and you should find in here wordcount.scala. Select that and import it into the project, and let's take a look at it. So let's double click on wordcount.scala and examine the code. Very simple. We're just trying to illustrate the use of flatmap instead of map, and it's going to be pretty much what we talked about in the slides here. So as usual, we have the usual code here for declaring our package name and importing the libraries that we need from Spark and log4j. We're going to call this object wordCount, and its main function sets the error level like we always do for logging, and then we create a Spark context, much like we've done before, again running locally in this example using all CPU cores, named wordCount. Now we're going to input the entire book into an RDD called input on this next line. And the way it's structured is that there's actually 1 paragraph per line. So every row of the input RDD is going to contain 1 paragraph of text from that book. But what we're trying to do is get a count of how many times each word appears in the book. So that's what we do here with flatmap. So just like in the slides, we're calling flatmap on the entire text of the book, where every row represents a paragraph, and passing in this function that splits those paragraphs up by space characters, giving us more or less a list of words that are in that paragraph. So this returns a list, and every element of that list becomes a new row in the words RDD. So flatmap is breaking every paragraph out into individual words and taking every word in that list and creating a new row in a new RDD that we're calling words. So now we can use our friend count by value to count up how many times each distinct word appears in that words RDD. and then we will just print out the results from that by applying print line to each element of the final word counts result that we got back from count by value, which is just a dictionary of words and how many times they occurred. So let's give it a try. Go to run configurations. We're going to make a new Scala application, and this is going to be called word count, and its main class is com.sundogsoftware.spark.wordCount. Let's run it and see what happens. Off it goes. So pretty cool. Hey, it actually worked. So, you can see through here, it's sort of a list of words that appeared. And for example, the word physical showed up 17 times in my book. The word commute only showed up once. What are some other popular words in here? Of course, that's a common word. 1,176 times in this book. But if you look at this, you can see that there's some issues with our results, right? So first of all, they're not sorted. It's not a very useful piece of output here because I can't really see what are the most common words very easily. Another thing is that there are punctuation included in these words. So we're only splitting on space characters. So for example, row comma is counted as a different word than just row or it might be a different word from row period, right? So that's an issue we should address. There's some sort of special Unicode thing going on here. I don't know. In Minimal, that's not being dealt with properly either. And the other thing too is we have different capitalizations. So for some reason, I have the word ideas in all caps. It's probably some section title, but that's going to be counted as a different word than lowercase ideas. So there's a lot of room for improvement in this script, and that's what we're going to do in the next couple of lectures, kind of explore ways to take this basic implementation of counting up the words in a book and making it into something more and more useful over time by making it a little bit more complex. So let's do that in our next lecture. So let's make that word count script even better. So if you remember from the last lecture, one of the big problems we had is that the words we were extracting out of the book weren't always words. Sometimes they had punctuation attached to them, and there was uppercase versus lowercase stuff going on. So we ended up with things where a word followed by a comma would be treated as a different word than a word followed by a period or a word followed by a space, because all we were doing before was breaking up strings of paragraphs by space characters and taking anything in between the spaces as a word. So we can do better. So there are natural language processing toolkits you can get. One's called NLTK, for example, that will automatically go out there and apply very complex algorithms for actually normalizing words and trying to figure out synonyms of words in different cases and things like that. But let's not go there just yet. Let's just do something a little bit better that's probably good enough for our purposes, and that's going to be using something called regular expressions. And you've probably come across regular expressions in some other programming you've done in other languages. It's basically a compact language for defining ways of splitting up strings into substrings using a set of compact rules. So this gives us a more robust means of identifying words within a string, taking that punctuation into account. So let's take a look at what that code looks like using Scala and Spark. So back to the Scala IDE here. We have up still our previous script where we just split out all of our paragraphs based on space characters and treated everything within the spaces as individual words. And, well, that produces okay results. It's not great. I mean, just looking at this right here, we have entrepreneurs followed by a comma being counted as its own word. Not okay. Parking with a question mark, that's going to be a different word from parking without a question mark. Let's at least fix that, shall we? So go up to the com.sundogsoftware.spark package, right-click on it, import from the general file system option there. And again, we'll browse to where we downloaded the course materials. For me, that is C downloads Spark Scala. And we should see a word count better.scala file. So let's select that and import it in. And take a look at that. So about the same amount of code, but this time we're using something called a regular expression. How does that work? So it's actually quite simple in Scala. What we're doing here is the same sort of basic work. We're setting up our log level, we're setting up a Spark context, we're reading in the book one paragraph per line, and then we're calling flatmap again to split up our paragraphs into individual words. But instead of just splitting on a space character, we're splitting on this regular expression. So if you call split with 2 backslashes, that indicates that I have what's called a regular expression. And there's entire books on regular expressions. If you're not familiar with them, I encourage you to go take a course on regular expressions or pick up an O'Reilly book on it. But short story is it gives you a syntax for more complicated ways of splitting up strings. And in this case, we're using the syntax uppercase W plus, which is just telling the regular expression, split this string up by words, and there could be more than one of them. So the uppercase W means I want words, however you interpret a word to be, Mr. Regular Expression Engine. And the plus means there can be one or more of them. So this returns back a list of words that takes punctuation into account, and returns back a new RDD of words that is a little bit more robust than the one we started with before. Now, the other thing we're going to do is normalize everything to lowercase. So if you see here in my original results, ideas and stick in uppercase would have been counted as different words than ideas or stick in lowercase, or even where the first letter was capitalized, say at the beginning of a sentence. So let's fix that too. We're going to convert everything to lowercase so that these get counted as the same words and case doesn't matter. So that's all this map function is doing. And now in this case, we do have a one-to-one relationship between the words that we extracted from each paragraph and the lowercase versions of each word. So we're going to use map instead of flatmap for this one. And from that point, we can do the same thing we did before, called count by value, to get the number of distinct occurrences of each word that we ended up with after it's been stripped out by words and converted to lowercase, and print out the results. So let's go ahead and run that, see what happens. Go up to run configurations, and we'll create a new Scala application. We're going to call this word count, caps lock, word count better. And the class is going to be com.sundogsoftware.spark.wordCountBetter. Let's run that and see if we do indeed get better results. Off it goes. And we're done. And look at that. Sure enough, everything's been converted to lowercase, which is a good thing. And I'm not seeing any weird punctuation either. I'm not even seeing any weird Unicode characters or anything. So this is looking a lot cleaner, just by using this little regular expression instead of a space character and normalizing everything to lowercase. So, in addition to, working on an example and making it better and better by iterating on it, this is also an example of where you really need to look at your output data and ask yourself, is this really the result that I expect or want? A lot of times your initial attempt to write an algorithm for solving a problem in Spark doesn't quite yield the right results in the end. And you really need to look at your results and ask yourself, does this make sense? Are there edge cases that I'm not dealing with? Is my data somehow unclean, right? I mean, data cleansing is often just as much, if not more work for a data scientist's job as actually processing the data. So what we're really doing here is cleaning up our input data before we process it with count by value. And the whole point of this lecture really is to stress how important that can be. You need to make sure you have good, clean data. There's not a lot of outliers in it that might mess you up, and we're doing the right thing here. So anyway, you can see things are looking pretty cool, pretty clean here. The word technical appeared 11 times. The word addresses appeared 7 times. Product 182 times. Wow, I talk about products a lot. In fact, the book is mostly about building products. So that's cool stuff. So, we're getting closer here for sure, but we're still not quite where we want to be. This would be a whole lot more useful if the results were sorted, right? If I could actually see what the most popular words were and the least popular words more easily. And if I were to just sort this as it is, though, it's going to sort it alphabetically by word. So how do I get it to sort by the word count instead? Well, there's a few tricks we can do for that. So let's explore that in our next lecture. So let's solve that last problem with our word count script and sort it in a useful way. We want to be able to see very easily what are the most popular words in my book and what are the least popular words in my book. Now, granted, we could just do this all within Scala as part of the final map that we get back from count by value, if we assume that there just aren't enough words in the English language for that to be a problem in terms of actually fitting on the memory of one machine. That might be an okay thing to do. But let's pretend, just for the sake of education, that there are so many different words in this book that I can't be sure it will fit in memory, and I actually want to do this on a cluster in a distributed manner. So how do we do that? Well, the problem with count by value is that it returns a Scala map back, where it maps words to their number of occurrences. Now, if we want to instead return an RDD that we can keep on the cluster, we basically have to reinvent how count by value works and return an RDD instead of a map. So that's what this little snippet of code here does. It says that we're going to take our RDD that where every row contains a lowercase normalized word, and we're going to do 2 things to it. First thing we're going to do is map each word to a key value pair. So we're going to take each individual word that we run across and convert it to a tuple, where the key is the word itself and the value is the number 1. So for example, if we come across the word product, it will convert that to a key value pair of product and the value 1. And now what we can do is use reduced by key to count up all the occurrences of each unique word. So reduced by key will take a look at all the values associated with a given key, in this case a given word, and combine them however we say. In this case, we're going to say add them all up together. So we're going to add up all the ones associated with each word. And by doing that, we end up with the final count of how many times each word occurs, and that ends up not in a Scala map, but in a new RDD called word counts. Okay? So that's how this little step 1 works. We're basically going to count up the occurrences of each word, but return it in an RDD, so we can do further distributed processing on it. So now what? Well, if we were just to sort things at this point, it would be sorted based on the words, and I don't really care about looking up alphabetically how many times each word occurs. I want to see the most popular ones on the top, least popular ones on the bottom, or vice versa. So to do that, let's flip these pairs around. So instead of having a key of word and a value of the count, let's make it the other way around. Make the first value of the tuple the count and the second value of the word. That way, when I sort these things together, it ends up sorted by the count instead of by the word alphanumerically. Okay? So then I can just use sort by key on these key value RDD that I have, and that will sort based on the key, which in this case is the numeric count occurrences of each word. That's all this does. So what we're doing here is we're taking that word counts key value RDD, which starts off being word and number of occurrences. This mapping function flips it around so that the second field becomes the first and the first becomes the second. And that just makes it count word instead of word count. And then we can call sort by key to sort things the way we want and display the results. So let's go take a look at the code and actually run it. So back to the Scala IDE here, you can see we're continuing to iterate on this problem. We started off with a very naive solution that just split up words based on the space character. We moved on to a better solution where we normalize that data a little bit better. We're more intelligent in how we're splitting things up into words, and we are normalizing them all to lowercase. And the last step in our journey here is to actually sort this in a useful manner. So let's go make that happen. Go ahead and click on the com.sundogsoftware.spark package, right click, and import from the file system, wherever we save the course materials. Oh, hey, it actually remembered it. That's cool. And you should see a word count better sorted.scala. Select that and import it. And let's open that up and take a look. So you can see here we've implemented the code that we had in the slide there. And things are the same up until this point. So we have our RDD here of lowercase words, where every row of the RDD is a normalized word from our book. And here again, we are going to transform each word into a key value pair, where the key is the word and the value is the number 1. And then we can use reduce by key on that result to add up all the occurrences of each word, add up all the ones, all the 1 values associated with each unique word. And that final result ends up in the word counts RDD, which we can continue to process on the cluster. And what we're going to do to sort that in the way we want is first flip them around so that the first value, the key, is the count, and the second value is the word itself. And then we can use sort by key to sort the resulting RDD by those key values, which are the counts. And then we can, at that point, sort by key returns things back to Scala, back to the driver script. That's an action. And we just have to iterate through each one and print them out. Now, to make it a little bit more readable, we actually want to print out word and then count in the end, not count in word. So we're going to flip it back to its original order as we're iterating through the results and printing them. So we'll extract the first field and save that into something called count. The second field, save that into the word value, and print out the results the way we want, which is just going to be substituting in the strings for word and count into our final result on each line. So let's go ahead and run that and see how it looks. And now the results will be a little bit more enlightening, shall we say. So go up to run configurations, create a new Scala application. What do we call this again? Word count better sorted. All right. Word count better sorted. And our main class, com.sundogsoftware.spark.word count better sorted. Let's run it, see what happens. Woohoo! All right, that's more like it, huh? Interesting, interesting, interesting. So the most popular word in my book is the word you. Wow, I must have you in mind. Even more popular than to or of or a or the and that. So all the usual suspects here for popular words in any given book. Let's scroll up a little bit and see when things get a little bit more interesting. Is in, that, yeah, whatever. All the most common words in the English language here, right? Business, probably the first kind of interesting word in the book, and it is indeed a book about business. Let's scroll up a little bit more. What do we find? Product shows up again as a popular word. And people, work, own, customers. So, just by looking at this result of the most popular words in the book, you can get a pretty good feel of what the book is really about. And actually, it's kind of enlightening to me to see what are the concepts or the words that are most frequent and most important to what I'm trying to convey in this book. So you can actually get some insights out of that data now, and that was kind of our goal. So that's pretty cool stuff. So there you have it. Our journey is complete for now for our word count example here. This is usually a very simple example that people use as sort of the hello world application of Spark, but we've kind of taken it to the next level here, and I hope you learned a little bit along the way. Mostly about the need to normalize your data and some ways to think creatively about getting the final result that you want and keeping it distributed. So there you have it. So there we have it, a pretty good example of doing a word count in my book there. If you do want to get your hands on it and start fiddling with it yourself, here's an idea of how to do that. How about introducing a stop list of words? Let's say you want to filter out all the common words in the English language like is, and, the, but, whatever you can think of, because that's not really going to tell you much about the content of the book itself. So see if you can use the filter operation and write a filter function that checks for a list of stop list words and filters those out from the actual processing as early on. So that's a little challenge for you if you're up for it. Either way, I'll see you in the next lecture. So at this point, I think you've learned enough and you have enough examples to actually go off on your own and actually write your own Spark script from scratch. So here's a little challenge for you. What I'm going to do is give you some sample data that represents some fake e-commerce data. And what I'm going to give you is a comma-separated value list, where each row of the input data represents some customer ID, some item ID, and the amount spent by that customer on that item. All I want you to do is create a simple script that adds up the amounts spent by each customer. So basically we're going to reduce down by customer ID how much each customer spent in total. Pretty simple. I'm starting you off easy here, but I want you to get some confidence in actually writing Spark scripts from scratch using Scala, because you're probably new to Spark and you're probably new to Scala as well. So as a high-level strategy, just to point you in the right direction, start off by parsing that input data, split it up based on those comma characters into individual fields in a list. Then you're going to want to map each one of those lines to key value pairs, where the keys are the customer IDs and the values are the dollar amounts. And then you can just use reduce by key to add up all the amounts spent by each customer ID, call collect, and print out the results when you're done. So at a high logical level, that's the approach you should go after. It's up to you to turn that into code. Be sure to look at the previous examples that we've looked at in this course. There's going to be a lot of useful examples there that you can emulate, and a couple of useful snippets that you might find handy here. Remember to split a line based on commas. You just use line.split with the character that you want to split it on. And remember that if you need to output a tuple, like say a key value pair, and you want to convert those values to a specific data type, you can use toInt and toFloat on the resulting fields to do so. So keep that in your back pocket there, and I'll get you started, set up the project for you. So let's go take a look at how you might get going, and then I'm going to turn you loose. So let me get you started on your assignment here. If you go to the place where you downloaded the course materials, you should see a customerorders.csv file, and if you click on that, you can see the format of it. Again, it is customer ID, item ID, and amount spent. You only need 2 of those fields for this assignment. Go ahead and copy that and paste it into where you are working from. For me, that is C Spark Scala. All right, so your data is in the right place. Remember, it is called customer-orders.csv when you're loading that file up. And go back to the Scala IDE. You should have a nice little library here of examples to look at. So I'd suggest reviewing these examples, understand how they work, and think about how it might apply to the problem at hand. Remember, what we're trying to do here is add up the amount spent by each customer. All right, so when you're ready to get started, just right-click on the package and say, instead of import, we're going to say new Scala object, give it a name, like, I don't know, purchase by customer, whatever you want to call it. And that will give you a big, scary, empty object to fill in. So again, look at these other earlier examples to get started. You know, obviously you're going to want to import the stuff you need. Is one of the first things you do. Add a main function, and what you do within that main function is what counts. So good luck. Have a go at it. In the next lecture, I'll show you my solution to the problem, and you can compare that to your solution. But do try this on your own. It's important to get some practice with this stuff. So go do your homework. See you in the next lecture. All right, did you do your homework? Hopefully at this point you have a working script that you wrote on your very own that actually counts up the amount spent by customer in our customerorders.csv file. So let's go ahead and take a look at how I did it and compare it to your approach. And if you did get stuck, that's okay. Take a look at my solution here, and maybe you can go back and give it another try without looking at my solution, just to get you started. Hopefully you saw the similarities between this problem and the ratings counter and the word count problems that we've already solved. A lot of inspiration from that could be had. So to take a look at how I did it, go ahead and right-click on the package and import my solution, which is in the file system. And if you go to your downloads for the course materials, come on, work with me here, you should see total spent by customer.scala, and that was my solution. Let's open that up and take a look. So you can see here that at a high level, I wrote a little function here that's used to map my input data into two fields, the two fields that I care about. So remember, what I'm trying to figure out is the total amount spent by customer. And our input data contains three fields, the customer ID, the item ID, and the purchase amount. I don't care about item IDs at all. That doesn't factor into my final result whatsoever. So all this mapping function is doing is taking an input line, splitting it up by commas, and then extracting the two fields I do care about into a key value pair, where the key is the customer ID from field 0, and the amount spent is the dollar amount from field 2. Okay? So that gets used down here in our main function. We do the usual thing to get rid of log spam and set up a Spark context like we always do. Then we load in our input data from the raw CSV file into an input RDD, and we apply that function we just wrote to convert that input data into key value pairs called mapped input, where again the key is at this point the customer ID and the value is the amount spent. At this point it's a simple matter of using reduce by key on the resulting RDD, where we tell it to add up all the individual prices together for a given customer. Remember, the key here is the customer, the value is the price. Reduce by key will add up all of the prices for a given customer given this addition function. And then we have an RDD that contains the results that we want. Total by customer, we're going to call it. We'll just collect it and then print out the results one line at a time. So let's go ahead and run that. Run configurations, Scala application, total spent by customer, com.sundogsoftware.spark.total spent by customer, and run it. And there we have it. This is all randomly generated fictitious data, so you can't really read much into it, but you can see it worked. We have a list of all the customer IDs and the amount each customer ID spent in total. And given the even distribution of the random data, they're all in roughly the same ballpark, so that looks about right. Very cool. Now, you're not done yet. Hopefully, maybe that was a little bit too easy for you. You know, if so, I'm going to challenge you a little bit further. So if you did have trouble with this example, go back and try it again after you've seen the actual code that you can refer to. So I do want you to try and get something running on a piece of code that you actually typed in yourself, okay? If nothing else, copy this file over. Just make sure that you have the capability of writing code from scratch and running it here. And once you have some comfort with what's going on so far, let's take it to the next level. What I want you to do is actually extend this to sort the results so we can see who the biggest spenders are and the lowest spenders. So a little hint, remember that word count example we did where we ended up sorting the results to show the most frequent words and the least frequent words in my book, sorted that way. Same concept applies here. So go back and study that example and figure out how you can apply that same technique to our purchase data, our e-commerce data. So I want to get things sorted so that I see my cheapest customers, and as I get toward the end of the list, my biggest spenders. So sort the final list by amount spent using those same techniques. And when you're ready, go off and do that and come back to the next lecture and I'll show you my solution and you can compare my solution to yours. So go do your homework again, and I'll see you in the next lecture. Okay, hopefully by this time you have successfully extended our little previous exercise to sort the results by amount spent. And we can actually take a look at our cheapest customers and our biggest spenders pretty easily. If not, tisk tisk, you should go do that before you look at my solution here. We're good? Okay. Let's go ahead and right-click on the package like we usually do, and we will import my solution from the file system, which is going to be called Total Spent by Customer Sorted. Hopefully you haven't peeked at it. All right, let's take a look at that. And you can see it is in fact applying the same general idea that we did in the word count example when we tried to sort that by the word frequency. So we've taken what we started with our total spent by customer Scala and just changed the last few lines of it. So up to this point, things are the same. You know, we've gone and parsed out our input data and split out the input into key value pairs where the keys are customers and the values are amounts spent. We reduced that by adding up all the amounts spent for each individual customer. And at this point, we have a total by customer RDD that contains key value pairs of customer IDs and how much they spent. So now we need to sort that the way we want. And we're going to do that same trick of flipping things around so that the thing we want to sort by is in our key. So this map function does just that. It takes our customer ID to amount spent pairs and flips it around to be amount spent and customer ID. So the new key is amount spent. Then we can call sort by key on that to sort by amount spent. And it's just a matter of collecting the results and printing them out. So let's give that a try. Give it a run. Run configuration. Yet another Scala application. This one being called Total Spent by Customer Sorted. And the class name is com.sundogsoftware.spark.total spent by customer sorted. Let's run it and make sure it works. Well, how about that? It seems to have done so. So I didn't actually go to the trouble of flipping the output order when I printed it. If you wanted to do that and you did, then bonus points for you. Congratulations. But I just kind of took the easiest approach here because I don't want to make it too hard for you. But you can see that it is in fact sorting by the amount spent, and our biggest spender in this fictitious data set is customer ID number 68, whoever that is. And I'm not sure if we have enough buffer in here to actually capture the cheapest, so we do. Whoever customer ID 45 is our cheapest customer who only spent about $3,300 in total. Well, it's actually a fair amount of money, but anyway, it's an illustrative example. So if you did get similar results and those are your cheapest and biggest spending customers, congratulations, you did it right. And if not, go back, compare your code to how I did it, try to see where you went wrong. But hopefully you can take a look at my implementation here and compare that to how you did it yourself and find any issues or use mine as a reference. If you have gotten this far, congratulations. You have now written Spark Scala code on your own successfully. So that's a pretty big milestone. Congratulations. Pat yourself on the back. So with that under your belt, and you should be feeling pretty good about it, let's move on to some more complicated examples and see what Spark is really capable of. We'll do that in the next section. So let's start doing some more interesting stuff with Spark and Scala. We're going to revisit the movie lens dataset that we started off the course with. And we're going to start with a simple example where we just try to find the most popular movie, the most rated movie in that dataset. But we're going to build on that to do more and more complex things and illustrate more and more features of Spark. So let's start our process now. So just to review the data format of the movie lens ratings data, the data file looks like this. It has a format where every line consists of a user ID, a movie ID, a rating, and a timestamp. So the way to interpret each row is user ID rated this movie, this rating at this time. Okay, so for example, user ID 196 watched movie 242, gave it 3 stars, and did it at whatever this timestamp represents. That's actually a epoch seconds format. There's a way to convert that to a real date, but it's not important because we're not using that data. So let's step back and think a bit. If I wanted to figure out the most popular movie, what do I need to figure out? All I need to figure out is how many times an individual movie was rated overall. I don't really care about the users, right? I can throw that away. I don't care about the times. I can throw that away. And I don't even care about the ratings themselves. All I care about is the fact that a movie was actually watched, that it actually appears in a given line. So that makes things a little bit simpler. So let's go look at the code and talk through it. So let's hop back in the Scala IDE and take a look at some code to find the most popular movie. So let's right-click on our package here and import from the class materials that you downloaded earlier. And we'll look for popularmovies.scala. Open that up. And we'll double-click that and take a look. So, as I said, this is a very simple example reminiscent of some of the stuff we've done earlier in the course, but we're going to keep building on this to do more and more interesting things. Ultimately, we're going to build movie recommendations using this data. But we got to start somewhere. So we have all the usual boilerplate stuff: import the packages we need, define our main functions at the logging level, build a Spark context. Nothing interesting too far. But here we go with the actual meat of the problem. First thing we're going to do is load up the u.data file, which contains the movie rating data itself. And remember, that contains user ID, movie ID, rating timestamp. But all I care is that a movie ID actually appears on that line. The only information that's actually relevant to me is the movie ID. So let's extract that with this map function. We're going to call map with this little inline function here, where we split up the data based on tab characters, because I know it's tab delimited. I take field number 1, which is the movie ID, and remember we start counting from 0 here, so it goes user ID, movie ID, rating timestamp. So movie ID is field 1. And we're actually making this into a key value pair, where the key is the movie ID and the value is the number 1. You can probably see where this is going, because this is similar to the other examples we've done where we do counts. So what we have at this point is a movies RDD that contains key value pairs of movie IDs and the value 1. And then we just call reduce by key to add up all the ones for each individual unique movie ID, and that gives us a count of how many times each movie appeared in the data set. Finally, we can just call sort by key to sort the results, collect them, and print them out. So, not too complicated. Let's go ahead and do it. Run configurations, Scala application, popular movies, com.sundogsoftware.spark.popular movies, and run. Bang. It's amazing how fast it is once it actually gets going. So there you have it. We have a list of the most popular, most viewed, most rated movies in our data set, and it turns out the winner is movie ID 50. But that's not very helpful now, is it? What does movie ID 50 mean? Well, it turns out there's a u.item file in the Movie Lens dataset that maps movie IDs to movie names and all sorts of other information about the movies. So to make this really useful and get some interesting data out of it, we're going to have to somehow merge that data in. So let's talk about how that works in the next lecture, and we'll learn what the most popular movie actually is. So let's talk about making the results of that most popular movie script more human readable. We learned that the most popular, or more specifically, the most rated movie in our data set was movie ID 50. But what the heck is movie ID 50? Well, it turns out there's a u.item file in the Movie Lens dataset that does map IDs to names and much more information as well. And we could just load up that table in memory and keep it in a big Scala map object or something, and use that to print out the results in a prettier format at the end within the driver program itself. Or if you wanted to pass that around to, different mapping functions or whatnot, or you could actually pass that in and have Spark automatically forward that map to all the executor nodes automatically. But let's imagine that this table is truly massive, and it's a little bit sketchy about fitting it into memory on just one machine. We also want to make sure that it's not transferred across the network more than once, so this is where broadcast variables come in. This gives us a means of taking a chunk of data and explicitly sending it to all of the nodes in our cluster so that it's there and ready for whenever it needs it. Now, the syntax for doing this is pretty straightforward. You just call broadcast on the Spark context object, and you can use that to ship off whatever data you want to all the different nodes in your cluster. And then within your driver script code, you just use .value on that object that is returned by the broadcast function to actually retrieve that information back and refer to it within your script. So by using this pattern, you can send arbitrary data across your entire cluster and make sure that it's available whenever it's needed without having to retransmit it all the time. Okay? So let's go take a look at the code for a better version of our most popular movie script and see how that works. So let's hop back to the Scala IDE, and to recap, in our previous lecture we created this script to find the most rated movie in the Movie Lens dataset that we downloaded earlier in the course. And we've learned that the most popular movie was movie ID 50 with 583 distinct ratings in the movie set. And of course, there's lots of movies that only got one rating, like 1494 is apparently a very obscure movie ID. But what does it all mean? How do we tie in that movie data? And how do we use broadcast variables to do it? So let's go ahead and import a more sophisticated version of this script. Right-click on the package, import, file system, and we're going to look for Popular Movie Nicer from the course materials and import that into our package. Double-click that, and let's take a look at how it works. All right, so first thing we need to add is the function that actually reads that u.item file that maps movie IDs to all of the metadata or information about those movies and loads it into a structure that we can use. So specifically, we're going to build up a map object in Scala that maps movie IDs to movie names. Okay, so to do that, we've written this little load movie name script. We know that there's some funky character encoding in this file because there's a lot of foreign movies with weird accents and stuff like that. So we're going to specifically say that we're going to use UTF-8 encoding and deal with it in a certain way. So if you ever have UTF encoding issues, this might be a nice little snippet of code to have handy for your Scala arsenal. But with that out of the way, we're going to just create a map object that maps integers to strings and initialize it as an empty map. Okay, that's what this line is doing here. And we will start off by opening up the u.item file. And this is all just using, standard Scala library stuff. We're not really doing Spark stuff here at this point. And we're going to get every individual line of the u.item file and iterate through it one line at a time. Okay. Now we know that this particular data is pipe delimited, so we're going to split each line by a pipe character, confirm that there is in fact data in that row that meets our criteria of not being a blank line, basically. And we will add to the movie names map this information here. So we take the first field, which represents the movie ID, and we map that to the second field, which is the movie name. Okay. Notice that we're converting that to an integer explicitly to save a little bit of space because we know that's an integer field, whereas fields 1 is left in its string form. And what we return is just a plain old Scala map object that maps movie IDs to movie names. Okay, with that out of the way, let's see what we're doing here. So, check this out. Usual stuff here, but once we kick things off, we're going to create a broadcast variable so that that map of IDs to movie names can be available to our entire cluster all at once. So we call sc.broadcast with whatever the load movie names function returns, which is that map of integer movie IDs to string names. And that gives us back a namedict object that has been broadcast to every node on the cluster, or will be when the time comes. Now, keep in mind, again, this data isn't so massive that this is necessarily required for this particular use case, but again, what you're trying to do is avoid retransmitting this data more than once, okay? So this is kind of a illustration of that general technique. There's more than one way to do it. All right, we'll load up our movie rating data itself. Everything here is the same as it was before. We just split out the data so that we end up with extract the movie IDs and the number 1, add up all the ones for each movie ID. And at this point, we have a movie counts RDD that maps movie IDs to how many times that movie ID was rated. Now things get a little bit different. While we're at it, let's sort things. And again, we're flipping things around so that we have count movie ID instead of movie ID count. We sort by key. And at this point, we have our original results of the counts and the movie IDs sorted by count. Okay, so the last item in our list will be the most popular movie, movie ID 50. And now, what we're going to do is actually do a mapping function to convert all of those movie IDs to their corresponding names. So that's what this little bit of code here is doing. We're calling map on the sorted movies RDD. And we're going to map x to namedict.value. So remember, namedict was our broadcast variable object. We're calling .value to actually retrieve what's inside of that broadcast variable, which is the map that we stuffed into it originally. Okay, so we're going to call it namedict.value to retrieve that dictionary, look up that movie ID, which is in this case the second field of the sorted movies RDD. And then we will print alongside that the count and then print out the results. So this should give us back a new set of results that consists of the string-based movie name followed by the movie count. Okay, and that should be a little bit more readable. Let's go ahead and run that and see how it works. Run configuration, Scala application. popular movies nicer, com.sundogsoftware.spark.pop. My ability to type decreases as the day goes on. Popular movies nicer. And let's run that. Drum roll, please. And it turns out the most popular movie was, not too surprisingly, Star Wars from 1977. Now remember, this data set goes back to 1998, so all the big blockbusters after that, like Titanic and whatnot, didn't exist yet. So as of 1998, Star Wars was the most rated movie of all time on the Movie Lens website, with Contact, Fargo, and Return of the Jedi not close behind. And if we go back and look at the more obscure titles, well, they are in fact obscure. Il Mostro, Cold-Blooded, Nemesis 2. Never heard of any of these. Probably why only one person rated them. So there you have it, an example of using broadcast variables to make sure that information is available to an entire cluster when needed. Now again, I want to stress that there are more than one way to do this. I could have just loaded up that map and applied it as I was printing out the results within the driver script itself. This is really only necessary when you need to have that data broadcast to every node on your cluster. So if you're performing some sort of distributed map operation or flat map operation that requires that data, you'll want to think about using a broadcast variable instead. And that's what we did here with this map function. We actually used map to do the conversion of movie IDs to movie names in a distributed manner instead of converting them as we were printing out the results. But either way would have worked in this example. Okay, I'm just trying to illustrate the concept of broadcast variables here. So I hope that makes sense. Go back and stare at the code a little bit more if not. Broadcast variables pretty easy to use, and they can be pretty powerful. So there you have it. Let's move on to another example. So things are going to get kind of fun right now. We're going to start dealing with a data set about superheroes and their connections to each other, believe it or not. And as before with the Movie Lens dataset, we're going to start off with some simple examples and work our way up to more interesting problems later in the course. But for now, I just want to introduce the data and how to play around with it. So believe it or not, someone actually went out and looked at every single Marvel comic book and kept track of all the superheroes that appear together within the same comic book. And what we're doing is we're treating those co-appearances within comic books as social connections. So the fact that, for example, the Hulk and Spider-Man appeared in the same comic might imply that they're friends, if you will. So we can build up these complicated graphs where we have these references of who appeared with who in different comic books. So in this example here, maybe the Hulk appeared with Iron Man and the Hulk appeared with Thor, but Thor only appeared with Iron Man. And maybe they were in different comic books, and maybe Spider-Man and the Hulk are connected by appearing in the same comic book, but let's pretend that the Spider-Man and Thor never actually appeared in the same comic book. Totally made up social graph here, but it gives you a very simple example of what a social graph looks like. And just like we can construct something like this in the context of superheroes who appeared with each other in the same comic books, you can also apply this to big social networks like Facebook or what have you. Same idea. Networks of friends look like this, and they can have complicated shapes and structures. So playing with this data can be pretty interesting. But for now, let's do something simple and try to figure out who the most popular superhero is based on this data that we have. Let's take a look at what the data looks like. So there's two files that come with this data set that we're going to work with. One is called marvelgraph.txt, which contains the actual social graph itself in kind of a strange format. And then there's marvelnames.txt, which just maps superhero IDs to their human readable names. Okay? So looking at marvelgraph.txt, every line is just this big stream of numbers. And the way to interpret it is the first number represents a given superhero, and all the subsequent numbers represents all the superheroes that appeared with that superhero in other comic books. So again, the first number is special, that's the hero that we're talking about, and it's followed by a list of all the heroes that appeared with that hero, okay? And to map those hero IDs to names, we can do that with the marvelnames.txt file. So for example, we can see that Spider-Man is 5306. And actually he appears with whoever 4395 is in this example. Spider-Man is pretty popular, but let's find out if he's actually the most popular. So pretty simple, straightforward problem here. Our high-level strategy will just be to parse in that input line, one line at a time. And since we don't really care about the actual individual connections for this problem, we just want to find out who's the most popular. All we care about is the total number of connections for each superhero. So we're going to look at each line of input data, extract the superhero ID, that's the first number there that we're talking about, and then just store the count, the total number of other superheroes that appear with that superhero. Now, remember, These can span multiple lines, so the same superhero ID might be broken up onto 2 or more different lines, so we need to combine them together somehow. And reduce by key will allow us to add up all the individual lines for a given superhero into one final result. From there, we use the same sorting trick that we've used before. We're just going to flip that around so that the key is the count of how many friends you have, and the value becomes the superhero ID. And then we can just call max on the resulting RDD to find who has the most friends. And friends, again, is a proxy for co-appearances in other comic books in this example. Then we can look up the name of the winner from Marvel text, marvelnames.txt, and display the result. So off to the code. Let's see how that works. Run it and find out who is the most popular Marvel superhero. Alright, so let's get our hands dirty with the Marvel superhero social network data. As before, I have 2 windows open up here. One is my working folder that I'm using for the course. This is where all of my projects and data for the course are going that I work from. And then I have my download folder where I downloaded the course materials for the entire course. So the 2 files we care about for data are Marvel Graph and marvelnames.txt. If we click on them and preview them, you'll see that they are, as I advertised. Marvel Graph, again, just a list of lines that have a bunch of numbers on them, where each number represents a superhero ID. The first number is the hero we're talking about, followed by a list of that hero's connections. And then we have marvelnames.txt, which is mapping hero IDs to their human readable names, where the names are enclosed in quotation marks. Okay, so let's go ahead and copy those into our working folder here under C Spark Scala, and fire up the Scala IDE, and we'll import the necessary code to figure out who is the most popular superhero. Alright, we'll do our usual dance. Open up the project, open up source, open up the package, right-click on the package, and import from the file system, from where we downloaded the course materials, most popular superhero.scala. And let's open that up and take a peek. Get rid of this other stuff. Alright, a little bit more complicated stuff going on here, kind of surprisingly so. A lot of it's because we're dealing with 2 different data files that have different formats that we have to handle. So let's skip down to the main function where things get interesting, and we'll kind of work back to the other functions here. Usual setup stuff. We're just going to set the log level and create our Spark context. Now we're going to read in the marvelnames.txt file. So the first thing we're going to do is build up an RDD that can map superhero IDs to superhero names. And this is yet another way of doing this sort of a conversion. You know, in other exercises we looked at building up a Scala map object that we just used to do that as we're displaying the end result, and that would work fine here as well. We've also looked at using broadcast variables to load up that map ahead of time and broadcast that to each individual node in our cluster, and that works too. But you can also build up an RDD, and that will automatically be available to every node in your cluster as well. So a third way of dealing with this sort of a problem here, just for illustration purposes. So to do this, we're going to call flatmap on the parse names with the parse names function that we defined above on this names RDD. So names contains, just to refresh what it looks like, marvelnames.txt looks like this. So every row is a number and a space, and then within quotation marks the name of that character. Okay. Now, maybe there's some invalid data in here somewhere. Maybe there are some empty names. Maybe there are some blank lines. In fact, I think there are. So we need to deal with all these different edge cases as well. And that's where flatmap comes in. So if there's a possibility of a line that we cannot successfully parse, we want to use something like flatmap so we have the option of returning nothing for a given line because it's not actually going to end up in our RDD. So that's why we're calling flatmap instead of map. And let's take a look at what parse names does. So remember, this is getting called by flatmap on the raw input data. The input is a string of the marvelnames.txt file. And the output is going to be an option, a Scala option, of a tuple of a superhero ID and the superhero name. Now, we haven't talked about options before. Basically, an option is a Scala construct for saying you could have data or you might not have data. In other languages, we have the concept of a null value or a nil value or something of that nature. Scala doesn't have that. Instead, it has the concept of an option that wraps basically a value. And you can have either an actual value returned as an option, and that is a sum value, which is a subclass of option, or you can return a none value, which is also a subclass of option. So by returning an option, you can return a sum, which actually contains data, or a none, which contains no data. And when you're using flatmap, what will happen is that if you return a sum object, it will say, okay, I'm going to actually construct a line in my new RDD based on what's inside that sum object. But if it returns none, it will say, okay, there's nothing actually to do here. I'm not going to create a new line at all in my resulting RDD. Okay, with me so far? Looking at the code makes a little bit more sense, so just take a close look here at what's going on. Now, a little tricky here in how I'm going to parse it. Again, if you look at the actual input data itself, what I want to do is extract that superhero ID and the name. And one way I can do that to kind of cheat a little bit is to treat the quotation mark character as the delimiter character. So if I delimit this string and split it up on quotation marks, what do I end up with? Well, this ends up being one field then, the ID followed by a space, and then the name itself, which is between the next two quotation marks, becomes our second field. Okay, so even though it doesn't really look like it's quote delimited data necessarily, by treating that quotation mark as a delimiter, I'm getting pretty close to what I want, and that's what I'm going to do here. So the first thing I'm doing is splitting the string based on a quotation mark, and that gives me back, hopefully, more than one field. So if I actually end up with a successfully parsed line that has an ID and a name, I'm going to have more than one field, and I can continue on. And what I will do is take out that first field value, which is the hero ID followed by a space, called trim to get rid of that space, and then convert that to an integer value. Okay, so that's basically plucking out the superhero ID and converting it to an integer. And then I will take the second field, which is what appears between the second set of quotation marks, and use that as the name. Okay, and that gets wrapped in a sum object, indicating that I did in fact have valid data to return for that line. Now, if I have a blank line or a line that's missing a name or something, or maybe the quotes are all messed up, I'll just return none. In that case, I won't have more than one field, and I'll return a none value, which tells flatmap, ignore this line, don't do anything with it, there's nothing here to see. Okay. So after this line, we end up with a new names RDD that is just a key value RDD that maps superhero IDs to their names. Might come in handy later, right? All right, let's load up the social graph itself. So the next thing we're going to do is load up the marvelgraph.txt file into a lines RDD, and now we're going to call map on it using this count co-occurrences function. So what we want to get, as we talked about in the slides, is a new RDD that maps hero IDs to how many connections they have. And remember, this can be split up on multiple lines, so we're going to have to reduce that later on. But for now, let's just convert each line of input to a hero ID and how many connections they have. You can see all we're doing here, we're using another regular expression, kind of like we did back in the word count example, but instead of W plus, we're using S plus. That lowercase s plus is a regular expression that means split it up based on white space. Whatever white space is. It might be multiple spaces, it might be tabs and spaces. I don't care. Just split it up on white space, please, and that's what it gives me back. So what I'm going to get back here is a list of strings that represent the superhero ID and all of the superheroes connected to that superhero. But all I care about is that first entry, the hero ID we're talking about, so that's element 0 converted to an integer, followed by the number of connections. So that's just going to be the total length of that list minus 1 to subtract off that first character ID. Okay? With me so far? Hope so. Don't be afraid to go back and rewatch things if you're losing me here, but it's pretty straightforward. All right, so at this point we have a pairings RDD that is key value pairs of hero IDs to numbers of connections. Since these can span multiple lines, we need to do a reduce by key to add them up in that case. So if we have more than one line for the same superhero ID, this reduce by key operation will combine them together by adding them. And that gives us our RDD of total friends by character. So what we have at this point is key value pairs of hero ID to the grand total number of connections that hero has. Now to sort it properly, we're just going to flip it and make the key the number of connections and the value of the hero ID. Now I could just sort that and print out the results, or I could, if this, all I'm really trying to find out is the person who has the most friends, right? So rather than sort it and print everything out, I'm just going to find the maximum value. And if you call max on a key value RDD, it will find the maximum value based on the key. So that's why we had to flip it there. So that will give us back the result of the most popular superhero. All we need to do at that point is call lookup on our names RDD to figure out the name of that person, and we can print it out. And there's where we actually print out the result with string substitution, where we put in the name of the result and the end result of how many co-appearances that hero had. So Wow, a lot of talking, a lot of code to talk about, but let's just run it and get our result. The suspense is killing me. Run. Run configurations. Scala application. Most popular superhero. com.sundogsoftware.spark.most popular superhero. Let's see what happens. And if we should get an answer real quickly, it is... Ta-da! And the winner is Captain America. I wouldn't have guessed that. I would have guessed someone like Spider-Man, but it turns out Captain America gets around. He shows up in a lot of comic books. It's a good guy. He deserves it, right? All right, so that's a simple example of using the Marvel dataset, and we're going to do some more interesting stuff with it next. We're going to figure out degrees of separation and find out who is the Kevin Bacon of the Marvel superhero universe. We'll do that next. So if you want to get your hands on with this code and fiddle with it, as always, I encourage you to do so. Here's an idea. Instead of just printing out the most popular superhero, print out the top 10 most popular, and maybe the top 10 least popular. Give that a try. So let's do something a lot more complicated with that superhero social network data. What we're going to do is find the degrees of separation between any two superheroes. And to do that, we're going to introduce a concept called breadth-first search, which is a computer science algorithm, and illustrate how you can use Apache Spark to implement what might not seem at first to be something that lends itself to distributed processing. But through some creative thinking, you can take even complex algorithms like this and make a Spark application out of them. So maybe you've heard the story that the actor Kevin Bacon is 6 degrees away from any other actor in Hollywood. That is, if you look at the people that Kevin Bacon has appeared with in other films and the people that those people appeared with in other films and so on and so forth, everyone's within 6 degrees of Kevin Bacon. And I can tell you, having worked at imdb.com, that's actually not true. The number is much smaller than 6. People are really, really well connected, more so than you might think. The same is true of the superheroes in our superhero social network. You might be surprised at just how closely everyone's connected to, say, Superman. And to get a little feeling of what I mean by degrees of separation, let's take a look at this sample social network here again. So in this example, the Hulk and Spider-Man are 1 degrees of separation apart from each other because they have a direct connection. But for example, Iron Man is 2 degrees of separation from Spider-Man because we have to go through the Hulk to find Iron Man. So for example, to make it more concrete even, the Hulk and Spider-Man may have appeared in the same comic book, but let's say that Spider-Man and Iron Man never did. But Iron Man and the Hulk did, therefore they're 2 degrees of separation apart. Now take Thor, for example. If we take this path, we might say that he's 3 degrees of separation, but we always talk about the shortest path. So in the case of Thor, he would be 2 degrees of separation because they are connected by one person, the Hulk. Okay, 2 steps to get to Thor. So how do we do that? Well, we need to use a search algorithm called breadth-first search. So what we have here is basically a network, a graph in computer science terms. So imagine every one of these circles represents a superhero in our social graph. And these lines represent the connections between them, you know, the people that appear together in the same comic books in this example. So let's pretend this is what a social graph or a piece of the social graph looks like in our social hero super network. It illustrates different superheroes as circles. The lines represent connections between the superheroes. And the number in the middle, in this case infinity, represents the distance from any given superhero that we start with. So let's say, for example, we want to start with superhero S. Maybe that represents Spider-Man. What we want to end up with is a graph that indicates how many degrees separated from Spider-Man, from node S, is every other node in this graph. So to do that, we need some sort of approach, some strategy. So let's start off with a couple of basic ideas here. First of all, we're going to come up with the idea of maintaining the state of a given node, and it can be one of 3 colors. Now, white means that a node is completely unexplored by our algorithm, so we're starting off with everything being white as our initial state because nothing has been explored yet. Now we have other colors, gray meaning that it needs to be explored, and black meaning that it has been fully explored. Okay, so the color represents the state of each superhero as we search through this graph. White means it hasn't been touched at all, gray means it needs to be touched, and black means we're done with it. And inside each one, we're going to keep track of the degrees of separation from some given character that we started with. Okay, that's pretty much all there is to it. So let's see how that works. So again, our initial state, we're going to start off saying we want to measure everyone's degrees of separation to this node, node S. Maybe it's Spider-Man, who knows. So to do that, we're going to color this first node gray, meaning that it needs to be explored, And the initial degrees of separation will be 0, because Spider-Man is 0 degrees away from Spider-Man, because Spider-Man is Spider-Man. Make sense so far? So what that gray indicates is that we need to explore all the connections of this node. So we'll do that next. So by reaching out on the tendrils of that gray node, we're going to color these new connections gray, meaning that I need to explore them as well. And in the process, I'm going to increment the degree count from 0 to 1 and store that in this new exploration here. So we've increased 0 to 1, and we've propagated that out to all the connections of the original node. Now we've colored that original node black, meaning that we're done with it now. We've already explored its connections, and now these two nodes are gray, meaning that they need to be explored further. Now if we had a situation where there was already a number in one of these connections, we would maintain the lowest connection count, kind of like we showed before with the Hulk and or Spider-Man and Thor, for example, being connected through the Hulk. So we always maintain the shortest distance that we find, okay, and the darkest color. So if we then go off to split out this node that was gray, we are now going from 1 to 2 in our depth, and we will go out to its connections, make them a 2 because we're incrementing that, and color them gray. We need to do the same for this connection over here, and that gets explored out, and a 2 goes there. And now that we're done with these two nodes, they get colored black, so we know we're done with them. So that's another iteration of the BFS algorithm. Basically, we keep iterating through this process of exploring connections, coloring them gray, incrementing the degree of separation count, and then marking the node black that we actually processed. And we just do this over and over and over again until we're done. So this is another iteration done now. Now these all need to be explored, all 3 of these nodes. So we'll see how that works here. These get branched out, and we propagate out the next level of 3 out to there. This guy doesn't have any connection, so he's just going to turn black. We're done with that branch. And finally, we'll explore any unexplored connections of these guys. There aren't any, so they end up going black as well. And that is our final graph for degrees of separation from node S. So the way to interpret this, if you look at any given node, it already has the answer in there of how many degrees of separation am I from S. And you can see we are 1 degree from between S and W, but from T to W, for example, it is 2. And again, we preserve the shortest value there. You know, you could actually do it through 3 hops if you really wanted to, but 2 is the shortest path. And that's what breadth first search does. That's how it works. You know, that's actually a pretty fancy pants computer science algorithm that they ask you on job interviews at big fancy computer sciencey companies, right? So you now understand breadth first search. Congratulations. Not that complicated. So how do we translate that into a Spark problem? Well, that's the challenge, right? But for now, it's important that you understand the algorithm. So if you need to go back and rewatch what we've done so far, please go back and do so, and we'll move on with implementing this in Spark in our next lecture. So let's get back to talking about how to implement breadth first search in Spark. And as usual, there's more than one way to do it. I'm kind of describe the hard way of doing it just for educational purposes, but later in this course we'll come back and see how the GraphX library in Spark can actually make this a little bit easier. But for now, let's do it from first principles. So the first thing we need to do is transform all of this input data of our social graph of superheroes into the format that we need for our BFS algorithm. And if you remember right, every node in our algorithm had a count of distance from some other person we're interested in. It had a color indicating whether that node has been explored or not, or if it needs to be explored. And it also had a list of connections that we need to branch out from. So whenever we parse a line like this that indicates superhero ID 5983 is connected to these 4 other superheroes, we're going to transform that into a new data structure, kind of like this. So we're going to have sort of a tuple that includes tuples. It's okay to do that. Tuples can be nested and have more complex structure to them. So in this output tuple that we're going to put into our RDD for this data, the first entry in the list will be the superhero ID that we're talking about, followed by another tuple that indicates the connections to that superhero. Next entry will indicate the degrees of separation from the person we care about. And initially we're going to set that to 9999 just to represent infinity. Okay, really it should be infinity, but infinity isn't really a number, so we'll use 9999 as a proxy. And finally, the color of this node, which initially will be white, meaning that it is unexplored entirely. Okay, so that gives us to a data representation that's more aligned with the pretty pictures that we saw in the previous lecture. Here's the code that will do that. So we'll look at this in more depth shortly, but basically we'll split out all the different superhero IDs in each line of the input, extract the first one as the hero ID that we're dealing with, and then we will construct an array buffer. This is how we do that in Scala, and build up that list of connections to the superhero ID. So notice I'm using a variable here, a mutable object here, because I need to keep adding stuff to it and changing it as I go. We will set the color initially to white and the distance to infinity, 9999. Now, if this happens to be the character that we're starting from, say it is Spider-Man and I'm trying to measure degrees of separation from Spider-Man, then that's a special case. That's going to be gray, meaning that I want to explore that further, and my distance, the initial distance, will be 0 because Spider-Man is Spider-Man. And I will just convert that to the tuple that I want using the toArray object on my array buffer to actually convert that mutable array buffer to an immutable array. Okay, so that's what's going on here. Then I need to iteratively process the RDD just like we did in those slides before, where we go through one step at a time, branching out on all the gray nodes, coloring those nodes black, and then updating the distance on those gray nodes accordingly. So we just go through looking for gray nodes to expand. When we're done, we color that black, and we keep updating the distance as we expand our way out through the social graph. So the way we do this is by using a mapper and a reducer, a map function and a reduce function in Spark. So the mapper is responsible for creating new nodes for each connection of a given gray node. So as we go through the RDD of all of our nodes, when we find a gray node, we're going to bust that out into new nodes. So we're going to use flatmap to do that because we're going to end up with potentially more nodes than we started with, right? And at the same time, that mapper will make sure that we change the color from gray to black as we do that, and the original node we started with will be preserved and copied back into the results. The reducer is responsible for tying it all back together. So it will combine back together all the nodes for a given superhero ID, preserving as we go the shortest distance that it finds and the darkest color. And it also preserves the list of connections from the original node that we output from the mapping stage, so we don't lose any information. So that's all well and good, but how do we know when we're done? Any individual executor on our cluster might run across the character that we're looking for, so somehow it needs to signal to everybody else back to the driver script that we actually found the guy that we're after. So to do that, we're going to use something called an accumulator. And an accumulator is basically a shared object across the entire Spark cluster that maintains a count of something or some sort of a state. And it just allows all your executors to increment a shared variable across the whole cluster in a safe, thread-safe way. Okay, so syntactically, how does it work? We can set something up like this. We can set up a var hit counter, and we're going to say it's a long accumulator, meaning that it wraps a long integer value, and we can give it a name like hit counter or Bob or Fred, whatever you want. And what that will do is set up a shared accumulator value that every executor can increment it together at a safe rate with an initial value of 0 by default. So what we're going to do each iteration, if we run across the character that we're trying to find, we'll increment that hit counter accumulator. So all the executors will say, okay, increment that value from 0 to something else, if I run across this person. And then the driver script can check this accumulator value through each iteration and say, okay, well, if that hit counter accumulator is greater than 0, then I know I found the person. And in fact, that hit accumulator will actually contain the number of times that that superhero was encountered. It might be more than one. It might have been reached from several different directions potentially. So that's how we're going to message back to the driver script that we actually found the person we're after using an accumulator. Now the accumulator syntax actually changed in Spark 2.0. So if you're using an earlier version, the syntax is a little bit different. So keep that in mind. But we're going to do this the Spark 2.0 way. So with that, let's go off to the code and actually run it and get some reward for all this theory that we've been talking about and see it in action. So let's look at some code for actually implementing breadth-first search in Scala and Spark, and actually use that to figure out the degrees of separation between any two Marvel superheroes. So we'll do our usual routine here. I've opened up the Spark IDE already. We're going to right-click on the package and import from the file system, from the directory that you downloaded the course materials to. And we're going to select the degrees of separation.scala file and import that. Let's open that up, and we can take a look. Now we've already installed the data that we need, the Marvel names and Marvel graph.txt files from the previous exercise of finding the most popular superheroes, so those should already be in your Spark Scala folder that you're working from. Now again, there's more than one way to do this. Later on in the course, we're going to come back and solve the same problem using the GraphX library, using a lot less code, but there's some value in doing it the hard way, so we can see how you can actually take a complex problem like BFS and do it within the context of Spark. So let's just walk through what's going on here. The usual boilerplate stuff, a few more imports than we've had before. For example, we're using the accumulator class because we're going to, again, use that accumulator object to signal across the cluster if necessary when we found the person we're looking for as we traverse our way through the graph, the social graph of superheroes. We're also importing the array buffer class from the mutable Scala collection. And that's to construct dynamically the array of connections that we're going to stuff into our little data structure that defines each node of our social graph. So let's see what's going on. All right, so we declare the superhero IDs of who we're starting from, in this case Spider-Man, who is 5306, and who we're trying to find the degrees of separation to. And I chose a very obscure character called Adam 3031. I've never heard of him either, but who knows? Maybe there'll be a Marvel superhero movie about him someday too. But I had to pick someone pretty obscure, actually, to find someone who wasn't directly connected to Spider-Man already. So just to find an example of someone who's more than 1 or 2 degrees apart, it's pretty challenging. And same is true of Kevin Bacon, by the way. Let's declare our accumulator here, and you can see here we've actually declared our hit counter accumulator as an option, because that way we can initially set it to none and actually construct it later on inside of our main class when it's appropriate to do so. So initially, this is basically a null value, but we will create it later as an accumulator that wraps an integer value. Okay, so that's all that syntax is telling you there. We'll also declare some custom data types. This is something we haven't seen before in Scala. So just like you can have structures or classes in other languages, you can declare custom types in Scala. And in this case, we're going to say that a tuple that contains an array of integers, or superhero IDs, and an integer, which is the distance, and a string that represents the color, is just going to be referred to as the type BFS data. So this is basically a structure that contains an array of connections, a distance, and a color. So everything that embodies the data associated with a given node in our social graph. And then we can declare the node itself as a structure that is an int of the hero ID that we're concerned with, and the BFS data structure associated with it. So a BFS node contains all the information in one of those little circles that we saw in the previous slides. It's a node that represents a certain superhero that contains a list of all their connections, a distance from who we're measuring the degrees of separation from, and the color, which again indicates the status of that node and whether or not it's been processed or needs to be processed. Now, we looked at this code a little bit earlier on the slides. This is what converts a line of raw input data into our node structure. So you can see here we're actually returning this BFS node object and going through extracting the hero ID, extracting the connections, building up an array buffer with those connections, setting the default color to white, the default distance to infinity, unless we're the person we're starting from, Spider-Man, in which case we'll set it to gray, meaning that we need to explore this node, and the distance in that case will be 0 because there is 0 distance between Spider-Man and himself. When we're done, we return the resulting BFS node structure, which is just going to be the hero ID and the data here, which is the array of connections, distance, and color. Okay. Let's skip ahead to the main function here, and we'll go back to these other functions as needed. So you can see there's quite a bit of code here to talk about, so bear with me. Let's skip to the interesting part. We declare our hit counter once we're inside the main function, where it's safe to do so. So we initialize that accumulator with a value of 0. And that will be available to the entire cluster at that point. We then call the create starting RDD function, which just reads in that initial file of data and converts it for us. So let's go find that function. Create starting RDD, all it does is create an RDD of raw input data from the marvelgraph.txt file, and then applies our convert to BFS function to it in its mapper function. So that converts our raw data to these BFS node structures. Okay. Moving on. Next thing we do is we're going to actually iterate as many as 10 times through the graph. And it turns out that 10 is more than enough to find anyone who is actually connected within the social graph. So 10 is kind of a arbitrary number, an upper bound on the number of iterations that we'll do. We'll print out which one we're on. So our first time through, we're going to start with just that one gray node of Spider-Man and expand that out. So how does that work? Well, the first thing we're going to do is create new vertices, new nodes, based on the connections of the gray nodes. And that's what BFS map does. So we're calling flatmap on the RDD that represents the entire social graph at this stage with the BFS map function. And what does that do? Let's take a look. So basically it blows out the node into all of its child nodes. So remember, we're going to look for gray nodes here. Just skipping ahead a little bit here. If you want to like study the... Don't really have time to go into all the nitty-gritty of the individual Scala syntax here. It's pretty well documented and pretty self-explanatory, okay? But we're just basically extracting all the individual bits of data from a BFS node. So given one input of a BFS node, we will potentially return an array of other BFS nodes that represent all that node's children and the original node to pass on to the next iteration. So we create this array buffer of BFS nodes to fill up as our results. If we find a gray node that comes through, we're going to blow that out. And all we will do is increment the distance, set the new color to gray for these new nodes that we're creating. If we happen across the target character that we're looking for, we're going to increment the hit counter accumulator, right? So if we do find Adam 3031, we're going to say hit counter, add 1 to that, and that's going to signal back to our driver script, hey, we're done, we found the guy we were looking for. Otherwise, we'll create a new gray node for that connection, add that to our results, and color the node that we started with black. Okay, and again, if you need to go back and watch the animation of how the BFS algorithm works, that'll make more sense. We also add in the original node back in, otherwise we will lose all the connections of the original node in our structure. So we end up with new nodes for all of the blown out gray nodes, which is then turned black, and then we preserve the original node, the original black node as well. And that all gets sent down to the reducer. So if we go back to our main function, we can see here that after that mapping stage, we will have set our accumulator if we found the guy we're looking for, so we're going to check for that. If so, we'll say, hey, we found the guy. Woohoo, we're done. Otherwise, we're going to call reduce by key on BFS reduce. And what that will do is combine back together all of the nodes associated with a given superhero ID and combine them into one. And in the process of doing so, we will retain the darkest color and the minimum distance found. And this handles various edge cases where we might end up with different stories about what the path length would be. We want to make sure that we maintain the shortest path in that case and the darkest color. And that's all that this reducer does. Basically, it marries back together the original black node that we output from the mapper and all those connection nodes as well. Okay. So we keep on doing this until we either find the person we're looking for or we hit 10 iterations, one or the other. And that's it. Let's see if it actually works, shall we? Go up to run configurations, Scala application, degrees of separation, com.sundogsoftware.spark.degrees of separation, and off we go. And we are doing BFS on some real social network data, and there we have it. So you can see here, even with an obscure character like Adam 3031 or whatever it was, all it took was 2 iterations to come across that guy. So in looking through Spider-Man's connection, Spider-Man actually co-appeared with 8,330 other superhero characters. Can you believe that? Did you even know there were that many Marvel characters in existence? Spider-Man's appeared with almost all of them. There's that many characters and there's that many comic books out there. Very analogous to the movie world, it turns out. So all it took was one more step to actually find a connection of Spider-Man that also co-appeared with Adam 3031. And you'll actually be very hard-pressed to find anyone beyond a distance of 2 in this social network. Anyway, there you have it. Now, if you want to play with this some more, I definitely encourage you to do so. Play with different characters. See if you actually can find someone who's more obscure. I will warn you, however, if you go trolling through the list of hero names, the higher numbered ones don't actually appear at all in the data. So a little bit of a throw. That might throw you off a little bit there. But for the lower numbered ones, you know, below like 6,000 or so, those are all legitimate characters. And good luck finding someone who is more than 2 degrees of separation from Spider-Man. If you find one, let us know. And there you have it. BFS and Spark, just an example of doing something more complicated in Spark from the ground up. So it shows you the power of Spark if you think a little bit creatively. So with that, let's move on to another super interesting problem, this time building upon the movie lens data. And we're going to talk about doing movie recommendations next. So as promised before, we're going to do some more interesting stuff with our movie ratings data from the movie lens dataset. And let's actually compute movies that are similar to each other. This is a component of something called item-based collaborative filtering. fancy sounding thing, but you'll see the concept's not as hard as it sounds. And along the way, we'll introduce the concept of caching your RDDs and persisting them, something you need to remember to do for best performance if you're going to use the results of an RDD more than once. So, what do we mean by item-based collaborative filtering? Well, it's an algorithm that's used for movie recommendations or recommending any kinds of items, really. Basically, the idea is we try to find relationships between items, in this case between movies, based on customer behavior or user behavior. So if we see two movies that users tend to rate together similarly, then we might say there might be some sort of connection between these two movies. And if you like one movie, maybe you'll like these other movies that are connected to it through that user behavior data. So using that technique, we can build up features like this one on the Movie Lens website, where they have their own recommender system, and the same basic idea can be used to recommend anything on any website you can think of. It's used in e-commerce, for example, in a lot of different places. Let's go into how it actually works. So basically what we do is we start off by finding every pair of movies that were watched together by the same person. So any movie that was watched with another movie by the same person goes into a big old bucket of movies that were watched together by the same individuals. And then what we do is we take all the users who watched both movies and we compare their ratings to each other. And using those rating vectors that are associated with each movie pair, we can then try to compute how similar are these two movies to each other. And that's just one way of doing it. There's like countless ways of doing recommendations. This is just one algorithm that works well in some situations. So it'll make more sense with an example here. So let's say, for example, this lovely lady here watched Star Wars and The Empire Strikes Back, and she loved them both, gave them both 5 stars, okay? So already we know that these two movies were watched together by the same person at some point. Now let's say this edgy-looking guy here with Mr. Mohawk also watched Star Wars and The Empire Strikes Back and also loved them both. Both got 5 stars. Now by comparing the behavior of these two different people who watched both of these movies, we can say, okay, well, people tend to rate these two movies in the same way, and they tend to watch them together. There might be a lot of people who watched these two movies and thought the same of both. So that might tell you maybe these two movies are similar to each other. Now, given that information, if we know that Star Wars is similar to The Empire Strikes Back, let's say Mr. Hipster Mustache Man here comes along, and for some bizarre reason, he lives in this strange universe where he watched The Empire Strikes Back but was completely unaware of the existence of the first movie of Star Wars. But we can help this man. We know that through the behavior of these other two people that these two movies have a connection. They've been rated similarly by many people, and we can use that relationship to say, okay, if you like The Empire Strikes Back, you'll probably also like Star Wars, and given that you've never seen it before, that might be a really good recommendation for a movie for you to watch next. So that's all there is to item-based collaborative filtering. It sounds very complicated, but it's not that hard to wrap your head around. Basically, we look at people who viewed the same pairs of movies and rated them similarly. So if a given pair of movies has a similar set of ratings from many users, we can say, okay, these two movies are probably similar to each other. And it's important to point out, though, it doesn't necessarily mean that these are good movies, right? If both of these people saw both of these movies and hated them, gave them 1 star, they would still be considered similar to each other and similarly bad, right? So you have to be careful of that when you're interpreting these results. You don't want to end up recommending bad movies to people, and we'll talk about that more later. So how do we make this into a Spark problem? Well, here's our general strategy. And again, this is an example of taking a complex algorithm that doesn't seem to lend itself to Spark initially, but framing it as a Spark problem that we can attack with mappers and reducing functions and use that to actually distribute this out to a cluster and deal with massive data sets. So here's the approach. We're going to start by mapping the input ratings data set into this structure here, where we have a key of user ID and a tuple for the value of movie ID and rating. So we have these movie rating pairs associated with every user. So for every movie viewed by a user, we're going to have that movie and the rating for that user. And then we're going to blow that out to find every movie pair rated by the same user. And we can do what's called a self-join operation. Remember, you can do these database operations on key value RDDs, join being one of them. If we join on itself, we end up with a list of the user ID and every movie rating pair that they actually watched. So that gives us back every possible combination of movie ID 1, movie ID 2, for every permutation of movies that that user watched. Okay, so this blows out really quickly. You know, this is where the big data comes in, because once you start doing this factorial stuff, things can get out of hand pretty quickly. Okay. Now, to try to rein that massive amount of data in, because we're looking at every possible combination of movies that were watched together by every person, it's a lot of information. We're going to filter out any duplicate information at this point. So movie ID 1, movie ID 2 is going to be the same as movie ID 2, movie ID 1. So in cases where we have the same movies just in the opposite direction, we'll filter out one of those cases. Cases where we end up with the same movie in both sides of the pair, we can get rid of that as well. And that just narrows down our data a bit. Now the next step we're going to do is treat the movie pairs themselves as the key, because what we're trying to find is similarities between pairs of movies. Okay? We want to try to evaluate, is this movie similar to this other movie or not? So to get to that point, we need to make these movie ID pairs the actual key, and the value will be the ratings associated with those movie pairs. So every pair of movies that was rated by the same user will end up in one of these rows where we have a movie pair and a rating pair from that user's behavior. And we can then use group by key to munge together all of the ratings found for this pair of movies across the entire user set. So at this point we have a pair of movies, we have all of the ratings from everybody who watched these two movies together, and we can compare the vectors of ratings data for these two movies together and use that to measure the similarity between those two movies. So at that point we have our results. We can measure how similar are these two movies to each other based on user behavior, and sort them, save them, or display the results, whatever you want to do. So in this particular example, we're going to introduce a new concept called caching, or persisting your RDDs. And as we go through the code, you'll see that we're going to produce an RDD of our final results and query it more than once. Anytime you do that, if you're performing more than one action on the same RDD, you need to explicitly tell Spark to cache that RDD so it doesn't go off and try to recreate it from scratch the second time around. Otherwise it might. Whenever you call an action, remember, it goes off and builds up that directed acyclic graph and figures out how to run everything and actually kicks it off. So if you create an RDD, run one action on it, and then another action on that same RDD, it might go off and recreate it again. To prevent that, we have this cache function or persist function that you can use to make sure that it keeps a copy of that RDD around so that if you need it later on in the script again, it can go back to that copy of it instead of recreating it all from scratch. Okay? What's the difference between cache and persist? It's pretty subtle, actually. Persist gives you the option to cache it to disk instead of just to memory. So if you want to deal with, if you're worried about fault tolerance and nodes failing on you and being able to recover from that as quickly as possible, persist might be a better choice, but obviously it requires more resources to get to that state, so a little bit of a trade-off there. I use cache myself more often than not, but you can use persist if you're paranoid. And with that, let's take a look at the code and actually run it and start to get some interesting results. Okay, let's look at some code to actually generate similar movies based on user behavior data, real user behavior data. And to make it even more interesting, this time we're not going to just run it within the IDE, we're actually going to export a jar file for this class and run it for reals from the command line, which is closer to how you would do it in a production environment. So let's get started. I've opened up the Scala IDE. We're going to right-click on the package as usual and import from the file system from the directory we downloaded the course contents into. This time we're going to look for moviesimilarities.scala and import that in, open it up. All right. Now, if you consider what's going on here, we're actually finding similar movies using the techniques of item-based collaborative filtering here. Not that much code when you think about it for what it's doing. Anyway, we have the usual suspects up here. This time we're got a few more imports that we need for some of the things that we're doing inside of our similarity function that we'll look at later. And let's just jump down to the main function and kind of work from there. Alright, so we're going to run on every core available locally. Now I do want to start to mention in more depth here that if I'm specifying within the script that I'm running locally, that will override any other configuration. So now that we're getting closer to actually running things on a real cluster and in a real production environment, I want you to start thinking about that. You might want to just create a Spark context with no configuration initially and actually let the configuration on the cluster itself take care of that. Because if you run this on a cluster, it's not going to actually use the cluster if that bit of code is in there. So be aware of that. First thing we're going to do, load up a map of movie names so that we can later associate movie names with movie IDs. And we're just going to do this within Scala itself. So let's take a look at what load movie names does. All this does is do a little bit of code here to make sure we can handle character encoding issues, things with weird accents and stuff like that that might not be able to be converted to ASCII easily. These just tell Scala how to handle those different situations. All right, so we're going to create a Scala map object that maps integer movie IDs to strings. We're going to load up the u.item file from the movie lens dataset and parse that one line at a time. It is pipe delimited, so we will split based on pipes. If we have, in fact, more than one field, then we will add to our movie names map an entry that maps that given integer movie ID to that given movie name. All right, and that gives us back a map we can use later on for turning movie IDs into movie names when we display our final results. We've talked about a lot of different ways of doing these types of lookup tables, but if you're sure that information can fit securely within the memory of one of your nodes, specifically your driver scripts node, your master node, this is really the most efficient and simplest way to do it. All right, with that out of the way, we're going to load up the ratings data itself. And like we talked about in the slides, we're going to convert that to this structure here, where we're going to create a new RDD of key value pairs where the key is the user ID and the value is a tuple of movie ID and rating. Okay, so for every line, we're going to have a key of the user ID and a value that is a tuple of the movie ID and rating associated with what that user watched. All right, now we're going to blow that out, and we're going to do what's called a self-join operation here. We're taking that ratings RDD and doing a join with itself, and what that gives us back is basically every permutation of combinations of movies. So we get back every combination of two movies that user watched together. So if this user watched movies A, B, and C, I'll get back a pair for AB, a pair for AC, a pair for BA, a pair for CA, etc., etc., even AA and BB and CC. All right, because what we want to end up with is every possible pair of movies so we can later evaluate how these two movies are similar to each other. That's our end goal here that we're shooting toward. Okay. Now we're going to filter out duplicate pairs. So the pair AB and BA are really the same pair of movies. One of those can be eliminated. The pair AA is useless, so we can get rid of that. So that's what this filter duplicates filter function does. We're going to take that joined ratings RDD and filter it based on filter duplicates. Let's take a look at what that does. Here it is. Basically, it only returns a value in the case where movie 1 is less than movie 2. So let's say we have A, B, and BA. Only one of those combinations will survive because only one of those cases has a movie ID less than the other. And also the case where they're equal to each other, we have two of the same movie, that won't pass this filter function either. So we're just left with one direction of every possible movie combination where the movie 1 is less than movie 2 is the case that survives. So that actually filters out a ton of information, which saves us a lot of work. Okay, next we're going to key everything by movie pairs. So at this point we have an RDD that has user IDs to this list of these movie rating pairs. But what we really want in the end is similarities between movie pairs. So the key we want to end up with is a movie pair itself. All right, so we do this unique joined ratings map function using the make pairs function. Let's see what make pairs does. It's up here. Very simple, it just rewrites the data. So coming in, we have a user rating pair, and we've defined some more custom Scala types here. We're describing a user rating pair as an integer user ID followed by a movie rating and a movie rating, a tuple of movie rating, where a movie rating itself is an integer movie ID and a rating. Okay, so the output here, instead of being a user rating pair, will be a movie pair and the associated rating pair. So movie A, movie B, and then the rating for movie A and movie B. And that again is just setting things up for how we want it in the end. Next, we'll do group by key. So that will collect together all the rating pairs associated for a given movie pair. So for movies A and B, we'll go out and collect all the different ratings for that pair of movies from all the users out there in our data set. Okay, and at this point, we can actually start to measure similarity between these two movies because we have a pair of movies and we have all of the rating pairs from all the different users that watched both movies. We can see how similar the ratings were across the entire user base. So that's what we're going to do now. We're actually going to call map values because all we care about is the values that we're going to manipulate and turn into a similarity score. So We will take the values for each movie pair, which is a vector of ratings for each movie, and call compute cosine similarity on it. So let's see how that works. This is just one of many similarity metrics out there. So in the field of machine learning and data science, there are many ways of computing the similarity between two vectors of information. In this case, the vectors are movie ratings for two movies. And if you can think about this sort of in a trigonometry or geometric sense, imagine you have, a multi-dimensional space of movie ratings, and basically the ratings for movie A and the ratings for movie B are going in two different directions. The cosine between the angles of these ratings in a higher dimensional space measures how close they are to each other. So it's just one way of measuring how similar are these two sets of ratings to each other. So I don't want to get into the math too much, but suffice it to say, this computes the cosine similarity metric between those two movies based on the user ratings. And at that point, it's just a matter of sorting and displaying the results. But wait, look at this. We actually called cache on that value because we're going to use this RDD more than once. That movie pair similarities RDD contains our final results of how similar are any given pair of movies to each other. So we have the entire set of all movies that were viewed together by one or more people, and we have the entire set of similarity scores for every one of those cases. So that's a very useful thing. We're going to use it more than once. So to avoid going back and recreating that again, we're going to cache those results so we can use it multiple times. All right, next thing we're going to do is go through all the results. So we're going to look for similarities to a specific movie that's passed in as a command line argument. So we're going to use arg0 from the main function, which is just going to be a movie ID that we pass in as a command line parameter. Okay? Convert that to an integer, and that's the movie we're looking for similarities to. So what we're going to do is filter out that movie pair similarities RDD just for similarities that contain that movie. Okay, so that's what this little bit of code is doing here. We're getting back the filtered results RDD that are all the movie pairs that contain the movie that we're interested in. Now, what's going on here? We're going to map those such that each result is mapped to x2 and x1. So we're flipping things around again so that the similarity score comes first as the key and the actual pair is the value. So then we can call sort by key to get the most similar movies on the top. And we'll take the top 10 and print them out. One other thing that I kind of glossed over here is this bit here. We have a couple of thresholds here, and that's important. So not only are we filtering out anything that's not relevant to the movie at hand, we're also filtering out results that aren't above a certain score threshold. Those might be spurious, and they have a certain co-occurrence threshold. So we want to make sure that only movies that were watched by at least 50 different people count. Otherwise, we get these spurious relationships that aren't really statistically significant. And yes, that's a bit of a magic number. Yes, it needs to be tuned, but that's how we're going to sort of enforce a minimum quality bar in our results. So let's go ahead and figure out how to run it. Now we need to pass in a command line argument, which kind of implies we want to run this on a command line. Now I could actually do this within the Scala IDE, and it would work if I set things up properly, but let's take you on a step toward our journey of actually running things for real, just like you would in the real world. So normally you would use a system called SBT that we'll talk about more to actually produce your final packages, but we can do it just by exporting a jar file for now. So we have this package here, and we just want to export this package to a jar that we can then run from the command line using the Spark submit command. So to do that, all we have to do is right-click on the package and say export, and we're going to say we want a Java jar file. Remember, Scala compiles down to Java bytecode, so at the end of the day, it's indistinguishable from a Java jar file. It is a Java jar file is what we end up with, even though it's Scala code. We can stick with all the defaults here. We don't care about any of this stuff, and we're just going to export that one package. So we are kind of getting all these other examples as part of the deal. We'll pass as a command line parameter which actual class we're interested in running. And let's save that to our course folder, which for me was C Spark Scala, inside the Spark Scala course folder, okay? So I've already done this before, but I'll just overwrite it. That's read-only, but that's where you want to save it, okay? And once you have that there, you can hit finish. And we can actually go run it. So spark up a command window. Yes, you can make changes. I'm going to cd to my course folder, which is C Spark Scala. And inside there is my Spark Scala course folder. So follow along with me here, if you will. Now this is where I'm going to actually run the code from, and this is where I saved my moviesims.jar file. So to actually run this for reals using Spark's built-in cluster manager, I am going to use the spark-submit command, and this is the same command you would use on a real cluster, okay? Same technique. What we're going to do is pass in a few parameters here. First of all, we need to specify what class we want to run, and in our case it's com.sundogsoftware.spark.movieSimilarities, just like you would do if you were doing a run configuration from within the IDE. We also need to pass in the jar file that we're actually running, which is moviesims.jar. And remember, we need a command line parameter for which movie we're interested in. Now, I happen to know that movie ID 50 is Star Wars, so let's just type in 50 as an example and see what happens. So there we are, running Spark from the command line using Spark Submit. And Spark Submit is a powerful script. It can actually manage a lot of things for running on an entire cluster for you, integrating with Hadoop Yarn, and figuring out how to best distribute your application. So whenever you're running on a real cluster, you will be using this Spark Submit command, not running from within the IDE. Anyway, off it goes. It's running off its computations, and that was actually surprisingly quick. If you actually watch the Python version of this course, you know that took about 15 minutes to complete, whereas with Scala, we only waited a few seconds. So Scala can be substantially faster than Python for the same problem in Spark. Anyway, the results look pretty good here, huh? So we have top result is The Empire Strikes Back, followed by Return of the Jedi. Makes complete sense. Raiders of the Lost Ark, you know, another kind of adventure-y movie. And thinking within the context of 1998, there weren't a whole lot of big blockbuster science fiction films that existed at all back then, right? So the remaining results may not look that great, but they're actually reasonable choices for someone who liked Star Wars in the late 1990s, right? 20,000 Leagues Under the Sea, kind of a science fiction-y thing. And a bunch of, you know, sort of more cerebral movies that might apply to people who like science fiction. I don't know. So there you have it. Similar movies using Spark and Scala actually run from the Spark Submit command, which you could just do on a cluster if you wanted to. So that's pretty good progress. With that, let's talk about some ways you might get your hands dirty with this code and extend it and work with it and get more familiar with it. So we created some similar movies, and looking at the example of Star Wars, the results weren't bad. They weren't great, but they were okay, right? Let's see if you can actually do a better job. So I encourage you to dive in there and start fiddling around with it again, just to get more practice with using Scala and with using Spark. So here's some ideas of how you might extend that activity to actually make those results even better. One thing you might want to do is discard bad ratings altogether. Do that as early as you can. Like, filter out any bad ratings from the data. Because do we really want to recommend poorly rated movies? Probably not. Like I said before in the explanation of the slides of how this whole algorithm works, two movies can be similar if they're similarly bad to each other, but that doesn't mean they make a good recommendation. So perhaps enforcing some minimum threshold on the review score would be a good idea. Or maybe even weighting things based on the review score. How's that for an idea too? There's also different similarity metrics you can choose. We use the cosine similarity metric, but if you look up some of these other ones, there are other ways to do it too, and maybe some work better than others. It's worth experimenting with, and a good way to practice implementing some different algorithms in Scala. You might also try playing with those thresholds for the minimum number of people that rated the same pair of movies, or for the minimum score that we want for a similarity score in the end. Perhaps looking at some movies other than Star Wars, we'll discover that those thresholds might be too high, or maybe they're too low. Maybe there's not enough of a quality threshold being applied there. You could even invent a whole new similarity metric that takes the number of co-raters into account. So instead of having a hard threshold on how many people need to rate a pair of movies for it to be considered, perhaps that's just part of the metric of how similar they are. Maybe we just bake that number into the similarity score somehow. And if you really want to get ambitious, there's more information in u.items besides the movie names. There's also information there about the movie genres. And perhaps filtering things or working that into the similarity metric somehow would be a good idea. Or perhaps we can give a boost to the final results if two movies are in the same genre. It makes sense that science fiction movies would be similar to other science fiction movies, and if you see a science fiction movie that comes back as similar to some drama movie or, you know, a rom-com or something, you probably want that to have a very high similarity score before you really consider that to be a similar movie. Otherwise, it might just be some spurious relationship. So here's a few ideas of how to make the results better, and there's really a whole art to this. I mean, I devoted most of my professional career to solving this problem, and it's definitely not an easy problem to solve, but it's a fun one. So go tinker with the code and see where you get. And if you do come across a interesting twist on the algorithm that produces really good results, we want to hear about it. So go have some fun with it. All right, this next section is going to be about running Spark jobs on a real cluster. And there are many ways of doing that. Obviously, you can't just spark up the Spark IDE, no pun intended, and run that on a cluster, because you're probably not going to have access to a UI and all that good stuff. So we need a way of actually running these scripts from a command line and in a way that they can actually be distributed using a cluster manager of some sort, such as Spark's built-in cluster manager or Hadoop's Yarn. So let's talk about that packaging process first, and how do I package and deploy my Scala Spark driver scripts to a cluster? Well, we did that in the previous lecture. We had an example of actually running our movie similarity script using the Spark submit command. And let's talk about that in a little bit more depth and what was going on there. So in order to prepare a script for being run with Spark submit as opposed to within the IDE when you're developing and debugging, you have to make sure, first of all, that there aren't any hard-coded paths in that script to your local file system. And that's something we're kind of guilty of throughout this course so far. We've been putting in these relative paths to the Scala project that we're actually running from within the Scala IDE. But in the real world, you want to make sure that your data is coming from some distributed, reliable file system that is accessible to every node on your cluster. That might be an HDFS file system on a Hadoop cluster, or Amazon S3, or something else. But you want to make sure that your scripts are not assuming that your data resides somewhere locally on your hard drive, because that will not scale. Then you just have to package up that script into a jar file somehow. The Scala IDE makes that easy because we can just select the package and say export to jar. And once we have that jar file, we just need to copy that wherever it needs to be, where we're going to actually end up running it, either locally at first to test it out or on your actual cluster on your master node, and use the Spark submit command to actually execute that driver script. Now, what's special about Spark submit versus running in the IDE? Well, a few things. First of all, Spark submit wraps the entire process of kicking off your script and maintaining it, so it can actually integrate with a cluster manager and figure out, okay, how do I distribute the script out to the entire cluster? How do I integrate with the cluster manager to actually make sure that my job is actually distributed and reliable? How do I make sure my RDDs are really R&D, reliable and distributed, right? It also has some mechanisms in it for managing dependencies. So there's a -- jars option, for example, where you can specify paths to any jar files for other Scala packages or Java packages that your code might depend on that isn't part of the core Scala or Spark packages themselves. So for example, you might have an add-on library for integrating Spark with some other system like Kafka or Flume or something like that. You might need a series of jar files to actually enable that functionality in your script, and you can use the -- jars option to actually say, okay, here's where you can find that jar file. Make sure that's added to my dependencies for this script. You can also tell it to automatically distribute a set of files alongside your script. So if you use the -- files option, if you have some small data file, that might be a reasonable way to make sure that it's available to every node on your cluster. So let's go and try it out again. We did do this before, but let's go through it a little bit more slowly and using a different script and refresh ourselves on how Spark Submit works. So let's go ahead and look at using Spark Submit again as opposed to running from the IDE. Another thing that's good about Spark Submit is that it's something you can run from a command line, right? So you can actually kick off this script periodically using a cron job on an actual Linux cluster or Nagios, whatever you use to actually schedule jobs in a real production system. So you can't really do that with an IDE, right, in a graphical user interface. You need to be able to actually execute these commands from a command line prompt from an OS level thing. The other good thing too is that by packaging things into a jar file that's just Java bytecode, we can run this script on any operating system that supports Java. So I can develop on Windows like I'm doing here, upload that jar file to a Linux cluster and use Spark Submit on that Linux cluster, and it will work just fine. Okay, so that's kind of cool too. So as before, let's right-click on our package here and select Export. And what we're going to do is package up our popular movie script as something that we can run from Spark Submit. So I want to select a Java jar file. And again, don't get confused, even though we're writing Scala code, ultimately it's Java in the end. So we're going to do a Java jar file. And we're going to export all of our source code. And let's save this inside the folder that we're working at for this course, C Spark Scala, inside the Spark Scala course file. And let's call it popularmovies.jar. Now this is actually identical to the moviesims.jar file that we generated earlier because this particular Scala package contains all of the objects that we've created so far. So we're going to pass in as an argument to Spark Submit which object I actually want to execute. And later on we'll talk about using another tool called SBT that will let you skip that step even and only package up what you need. But for now, let's do this. And we'll hit finish. So now I should have a popular movies.jar file inside that file. So let's spark up a command prompt here. And I will cd to see Spark Scala, which is my course folder. And you can see I have my Spark Scala course folder inside of that. Go into there and take a look. We do have a popular movies.jar file. Now to execute that, I'm just going to do this from the command line. And again, I could actually copy this popular movies.jar file to the master node of a cluster, run Spark Submit, and it would actually run on the cluster. But for now, let's do it on our local desktop. Spark-submit. --class com.sundogsoftware.spark.popular movies, and the name of the jar file itself, popularmovies.jar. And again, if I had any dependencies, I could use the jars option to specify those. If I had files that I had to distribute alongside it, I could use files for that. But let's just see how this works. And it actually executed and gave me all the results, so there you have it. And as before, the most popular movie is movie ID 50, which is Star Wars. Cool. If we scroll up, well, I don't have enough buffer to really see it, but Spark Submit did all the work of actually splitting that job up across the cores of my computer. So it actually did distribute that as best as it could by creating up to 4 different processes on the 4 cores of my CPU. And again, if you were to run that on a real cluster that was configured properly under Hadoop or Hadoop Yarn, or even using Scala's built-in cluster manager, Spark Submit could have just under the hood distributed that to the entire cluster. There would be nothing else you would have to do to make that happen. So there you have it, using Spark Submit. So let's go on to a more advanced way of actually packaging up your Scala Spark scripts called SBT. We'll do that next. So what happens if you have a very complex Spark driver script that actually has a lot of third-party dependencies that aren't part of the core Spark distribution? Or maybe you have a bunch of add-on packages you need to manage. Well, SBT is a technology you can use to actually package up all of those dependencies into a self-contained jar file that you can just move around to your cluster and run with one very simple line of code. So if you're familiar with the Maven for Java, you can think of SBT as Maven for Scala. It's basically a dependency management tool. So like I said, if you get into more complex scripts where you have a bunch of third-party dependencies, and this is pretty easy to do because sometimes your dependencies have dependencies and whatnot. For example, if you're trying to use the Cassandra database connector from DataStax with a Scala script, maybe you need to integrate an output to a Cassandra database, that's going to pick up this whole tree of dependencies that the Cassandra connector package depends on. So not only do you need to deal with having the Cassandra connector library installed on your cluster, you also need to make sure that all the dependencies of that library and all their dependencies are installed as well. So it gets to become a very complex problem if you have enough of these things in one place. SBT manages that for you. So all it is a very simple way of packaging up an application for Spark using Scala and automatically pulling in all of your dependencies and making sure that all the dependencies for your dependencies are in place as well. And it puts it all into one big, nice, neat jar package that you can then just copy to your cluster and run. So to use SBT, it requires a very specific directory structure that you actually create your packages from within. So you need to create a directory structure that looks like this. You basically need a project folder and a source folder alongside each other. And under your source folder, you will have a main folder and a Scala folder. And that's where your actual driver script source code will go. So you have to set that up by hand. But once you actually do that, actually running SBT is quite simple. The other thing you need to do is add this little extra step here for a Spark and Scala. You need an assembly.sbt file inside the project folder, and it just needs to be something of this format. Now the details of this command line will probably change over time. This is what works right now with the SBT 0.13.11 release, but SBT assembly is just what exposes the means for actually exposing the command for running SBT to create a self-contained jar file that contains everything you need in one place. The next thing you need is an SBT build file, and this is where you specify what your script depends on. And SBT will then be responsible for getting that chain of dependencies and making sure everything's in place. So we need to specify the name of our class that we're going to be running with, give it a version number, and we'll call it 1.0. Organization, from your package name, and the Scala version that your code depends on, which in our case will be 2.10.6 right now. Then you need to specify any library dependencies that your script has. And since this is a Spark script, we do depend on the Spark core packages. So this line says I need the entire set of libraries for Spark core, or else my script can't work. Now here's some more interesting pieces here. You also specify the version of Spark that you're depending on. In my case, it's going to be 1.6.1. 1.6.2 is already available as of recording this, so that will probably be different by the time you actually run this stuff. And important here is that I'm saying it's provided. So if I already know that these libraries are going to be pre-installed on my cluster, I can say in this build file, they're already provided, they're already there. I don't need to actually package these up in my final jar file. And as it turns out, we're going to be running this on an elastic MapReduce cluster using Amazon Web Services, and I know that that comes with all of the core Spark libraries pre-installed, so there's no need to actually package those as part of my script. But if you did have dependencies that weren't part of a standard installation, that's where you would put them. So here's an example of putting in Kafka as a dependency. Kafka is basically a technology for streaming large amounts of data from a distributed fleet, say log files from a giant web server or something. So if I had to do something like that, I could say, okay, from the org.apache.spark repository, I need the Spark streaming Kafka package that works with Spark 1.6.1. And by adding that into my library dependencies, SBT would know that I need to go and retrieve that package, make it part of my jar file, and also retrieve any dependencies that that package may have, which it turns out there are quite a few. Okay, now in this case, again, make sure I'm using the correct Spark version number that I will have deployed on the system that I'm running it on. And note that I did not put provided on that line because it's not actually pre-installed. I really do need to include this within my final package. Once you have all those bits in place, all you do is go up to the top directory and run sbt assembly, and it will automatically go create your jar file that contains any dependencies you might need within it. And you'll find that output jar file inside your target folder that gets created inside the Scala folder that's specific to the Scala version that you're working with. At that point, you can take that jar file and just run it. So what's really cool is since you gave it the name of the class you actually care about as part of the build file, you can just say spark submit, type in the jar file, and everything else just happens. You don't even need to specify the class name. You won't need any jars dependency options because those are already contained in the jar file. So just by saying spark submit, file name of the jar file, you're done. That's all you need to do. Just make sure your jar file is copied to where you're going to run it from, and use Spark Submit to kick it off, and that's all you need to do. So it makes life a lot easier when you're actually deploying stuff. And remember, time is money when you're on a cluster, so by making the process of actually running this on a cluster as simple and painless as possible, that's going to save you money in the end. So let's try it out. We have a new version of our movie similarity script that we're going to actually run on a real cluster, so let's take a look at that real quick and package it up using SBT. All right, let's actually package something up using SBT for real, and we're going to actually deploy this to an actual cluster and run it later in the course. So first things first, if you don't have SBT installed, head over to the scala-sbt.org website here, and you'll see a big friendly download button. And you can download that for Windows or whatever platform you need to deal with. And I'm not going to waste your time going through the installation of this on Windows. It's just your standard Windows installer. So go ahead and take care of that if you need to right now. Hit pause. I'll still be here waiting for you. Done. All right. The other thing we are going to be doing is actually packaging up a 1 million ratings version of our movie similarity script. So that's going to be kind of the end game of our course here. What we want to do is actually create movie similarities using 1 million movie ratings on an actual cluster. Now, you don't have to actually download the data, but if you do want to look at it, if you go to grouplens.org under datasets, just like we did for the 100,000 rating dataset, there's also a 1 million rating dataset. A little bit newer from 2003. And if you want to click on the readme.txt file here that comes with the dataset, it gives you more information about the file formats. They are a little bit different. So, for example, the ratings data themselves is in a ratings.dat file now, and it's actually separated by these double colon characters. So a little bit of a different format there. The movie data itself is also a different format. It's in movies.dat. And again, it is separated by these double colon characters. So our script will have to take that into account. So let's take a look at the actual script we're going to package up. If you go to the Scala IDE and you import the movie similarities 1m.scala file from the course materials, we've done that a million times, I'm not going to walk through it again, you'll see it looks a lot like our movie similarity script with a few key differences. So, for example, we have modified our mappers that parse out the information to take into account the new file names and new delimiters that we have. So we're looking for movies.dat now and a colon delimiter here, a little bit different. We also need to think about where these files are going to be when we're actually running on a cluster. So you'll see I'm actually saying I'm going to load this up from movies.dat right alongside whatever directory I'm running from. So the way my strategy here is to make sure that movies.dat is distributed next to my Spark driver script. And I'm going to load that up as part of the driver script and make sure that it's in the directory that I'm actually going to run from before I start. Now, movies.dat is small enough that I can get away with that, but when we're dealing with a million ratings, you know, we're getting into big data here. Maybe we want to make sure that that's someplace distributed and more redundant. So if you scroll down a bit, you can see that we're also going to be loading the ratings.dat file from S3. So this S3N prefix says, instead of loading from a local file system, I'm going to go to Amazon's S3 service, which is a big distributed file store, and look for the Sundog Spark bucket and load it in the data from there. So this way I can make sure that the ratings data itself is accessible to every node on the cluster, because S3 is available to every node on my Amazon Elastic MapReduce cluster. And it also ensures that that data is in a place that can handle the size of it and can store it redundantly. Okay? So a little bit closer to a real world scenario here. If you're on a Hadoop cluster, that might be an HDFS link instead of S3N, for example. That would work just as well. All right, the rest of it's going to be pretty familiar. There are a few other differences here that we'll talk about a little bit later. For example, how we're using a hash partitioner here. That's an important step. One other thing worth noting too is that we're not actually specifying local star when we're creating the configuration for this script. So instead, we want the pre-existing configuration on the cluster to take over. So when we set up an Elastic MapReduce cluster, it will come pre-configured to take the best advantage of the cluster at hand. So it will know how many nodes it has available to it and how to split that up. Now, if I forgot to do that and I actually left that local bracket star bracket in the Spark conf, it wouldn't actually take advantage of the cluster. That would override any setting on the cluster itself and actually just run on that one machine. So important to remember that step. So I haven't actually specified how this Spark context is going to be run. I'm going to fall back on the configuration files on the cluster itself. The only thing I'm going to set is the application name itself. So I'm going to create a Spark conf folder on that conf object, Spark conf object rather, set the app name on it, and then create my Spark context using that Spark configuration object explicitly. Okay, so a little bit different way of setting up your Spark context when you're running for real on a cluster. With that, let's package it up using SBT. Pretty simple stuff. So if we go to the downloads folder for the course, you'll see an SBT folder where I've kind of set everything up for you already. So that's pretty cool, huh? Let's just copy that somewhere that we can work from. I have a handy dandy E drive. I'm just going to copy it there. And if we open that up, you can see that I've already created a build.sbt file here. If you open that up, you can take a look at it. And we've specified the name of the object as movie similarities 1M. You gave it version 1.0. It's under the com.sundog software organization. Depends on Scala 2.10. And its only dependencies are Spark core. We're not actually using any fancy third-party dependencies. And we're going to specify that we're going to be using Spark 1.6.1, and these Spark core libraries are already provided on the cluster itself. Now, if I did have weird third-party dependencies, this is where I would add them in, and SBT would handle making sure that they were available and part of the package. The other thing that is in here for you already is under the project folder, an assembly.sbt folder file. And again, this may change from SBT version to SBT version, but for this particular version of SBT, this is the magical incantation that needs to be there. So this will just add access to the SBT assembly command that I can use to actually make my final jar file. And you can see I have a source folder that I've created there as well. That already contains a main folder and a Scala folder. And under source main Scala is where I put the driver script itself that I want to package up and ultimately run. Okay? So the rest is kind of magic. Since we're actually creating just based on this one Scala folder, SBT will understand that the main function in that object is what I actually want to run. And I don't need to actually explicitly specify that when I actually run Spark Submit anymore. So let's spark up a command prompt and actually create that assembly. I will switch to my E drive and CD to that SBT folder that I created. Take a look. Yep, everything's there. And from this level, all I have to do is type in SBT assembly, just like that. And if I've properly set up my build.sbt and SBT assembly, it will go and find that driver script and package it up. So it's going off, making sure there's no dependencies that it needs to retrieve. And ultimately, it will create a jar file. SBT is a pretty complicated package, so even for simple tasks, it can take a little bit of time to finish. Looks like we're about done. There we go. So, what did it do? Well, if we go back to our SBT folder here and we go, ooh, there's now a target folder. Let's open that up, and under there there'll be a Scala 2.10 folder, since I specified Scala 2.10 as my dependency. And there is the final jar file. So that is the jar file that I actually need to distribute to my cluster. And that is my Spark driver script that I can run from a real cluster. And we're going to do that next and see how it works. So the moment we've been waiting for, we're going to actually run our 1 million movie rating script on a real cluster using Amazon's Elastic MapReduce service and Hadoop. Lots of buzzwords there. Let's talk about it a little bit more before we actually do it. Let's talk about how distributed Spark actually works. So the same scripts you've been using to run these Spark jobs locally on your own PC can be used on a cluster without much modification. So it's kind of up to Spark Submit and Spark itself to figure out what cluster manager you're running on top of, and that might be Spark's built-in cluster manager, it could be Hadoop's Yarn, it could be Mesos, and integrate with that to actually distribute the work of all your mappers and reducers as well as it can across the cluster that you have available to you. So basically, the Spark driver script is running on your master node, your driver, okay, and that communicates with your cluster manager to actually distribute out the work that's in that driver script to different executor nodes, workers, okay? And the cluster manager is then responsible for dealing with failures of individual nodes and collecting the results back together to get back to your driver script when it's done. Now, a few other Spark Submit parameters we should talk about. And first, I should note that on a lot of clusters, a lot of these settings are going to be pre-configured for you automatically. So if you don't specify anything in your script explicitly for what the master is going to be, or if it's not being specified on the command line, there is also a configuration file within Spark that can be set up to set all of these things for you automatically. And for example, if you set up a cluster on Amazon Elastic MapReduce, a lot of these things will be set up for you in an optimal manner already. But sometimes you run into issues where things don't complete, you run out of resources, things start timing out, and you need to tweak these things a little bit to get things to run more reliably. So you need to know they exist. The first option we want to talk about is -- master, and that's not something you can tweak. It's just has to be set to the right thing for what kind of a cluster you have. So if you're running on a Hadoop cluster and you want to take advantage of Hadoop's Yarn cluster manager, that would be set to Yarn. If you want to use Spark's standalone cluster, you would set that to the host name and port of your master node on your Spark cluster. Mesos works similarly. And again, if you have a Spark conf or anything in your script itself that overrides that, it will ignore what's on the command line. So the hierarchy is whatever's in your script, whatever's on the command line, and whatever's in the configuration files for Spark. So never forget to double check your scripts to make sure that you're not hard coding a given master. For example, if you have that local bracket star, that will override the master option here. And if you were to run that script on a cluster, it wouldn't take advantage of the full cluster. As for managing the usage of resources on your cluster, there are options for that as well. Num executors will specify how many executor nodes you want to use. And by default, that's only 2. So if you're running on a larger cluster that has more than 2 nodes, you'll want to increase that setting. Again, usually that will be set for you by somebody else, by the administration, but something to be aware of and make sure that that is in fact set somewhere. Executor memory manages how much memory is available to each executor, and of course you want to make sure that that does not exceed the physical memory available to each individual executor node. If you're running on a cluster in the cloud, those are often virtual machines that have less memory than you might think. So make sure you are aware of the memory available to your script on each executor. And you can also limit the total executor cores. If you have multi-cores on your virtual nodes, then you might want to tweak that to actually put an upper limit on how many cores your script can consume. Okay, Amazon Elastic MapReduce. So that's what we're going to use in this course. It's a quick and easy way to spin up a Hadoop cluster, and you can actually tell it to pre-install Spark on it for you as well, with everything automatically configured. So very easy way to get started and run your script on a real cluster where you just rent time and pay for what you need. And that's kind of the whole premise of Amazon Web Services. You just rent time and pay for the computing resources that you actually need for whatever you're doing. So you're charged basically by the hour instance, how much time you're spending on how many computers of a given type, and you're also charged for any network I/O and any storage space and any storage I/O as well. So you pay for what you use. And usually it's not a whole lot. I think I spent about $30 in actually putting this course together in terms of AWS charges. But do be careful. I do recommend just watching me do this for now, unless you've got some corporate account or something where it's not your money on the line. Because if you mess up, it's very easy to forget to terminate your cluster when you're done. And if you do that, your cluster will just keep on running forever, even though you're not using it. And you're going to be billed for all that time. And you might not even realize it until you see a credit card charge for $1,000. I don't want that to happen to you. I don't want to be responsible for that. So, if you do want to fiddle around with EMR, remember to terminate your clusters when you're done. If you don't, your bank account's not going to like you, and you're not going to like me. So just don't go there, okay? So with that, let's talk about actually running on a cluster. I talked about a few of these points already, but again, what EMR sets up for you is a Hadoop cluster, and you can run Spark on top of the Yarn component of Hadoop. So people kind of conflate Hadoop and Hadoop Yarn sometimes. I hear a lot of people talk about how Spark is faster than Hadoop, but it's not really one or the other, okay? What they really mean is Spark is faster than MapReduce, which is a way of running distributed jobs on Hadoop. But Hadoop itself is just a technology for managing a cluster. And one component of Hadoop is Yarn, the cluster manager, which Spark can run on top of just fine. Okay, so remember there's different pieces. There's a Spark driver, there's a cluster manager, and then there's, the actual hardware itself. Hadoop is just filling in that little middle piece for you. So Hadoop and Spark are not mutually exclusive, which is a common misconception. Okay. One other thing I want to point out too in terms of best practices, because running on a real cluster is expensive, these are expensive resources that you're dealing with here potentially, you always want to make sure you're doing your development and testing locally on your own PC first, okay, or some desktop computer or some single computer that you have access to that doesn't cost a lot of money. And a way to do that often is to use a subset of your data just to develop with. So if you're dealing with a big data set that you can only manage on a cluster, consider using just a piece of that data set to develop and test with, and that way you're more likely to have a successful run when you're actually renting time on the cluster itself. You really want to minimize the amount of time you're working on the cluster, if possible. Okay, so in terms of getting set up, you need to start off by creating an Amazon Web Services account, and I'll just assume you can figure out how to do that, since again, I just want you to watch me do this right now. The next step will be to create an EC2 key pair so that you have the ability to actually log into your cluster once you've spun it up in a secure manner. And you'll need a way of logging into that actual virtual machine at some point using something like PuTTY on Windows. You need some sort of a terminal to be able to connect to these machines and actually run your script and download the things you need to them. So let's get started and actually see how it works. So let's do this. Let's actually generate movie similarities based on 1 million user movie ratings. And do it for real. So just follow along here and I'll show you how it works using Amazon's Elastic MapReduce service. Now to get things set up, I've already loaded some stuff into Amazon's S3 service, which is basically a distributed file store that you rent space on, right? So kind of like HDFS, but it's the Amazon version of it, one way to think about it. So I've already created what's called a bucket in S3 called sundog-spark, and I've uploaded a few things I'm going to need. One is the movie similarities 1m.jar file. And this is the same thing that I generated using SBT earlier in the course. I just gave it a slightly different file name. So that is my self-contained Spark driver script bundled up into a jar file. Okay, so that's going to be on S3, so I can quickly copy it onto my cluster once I've spun up my cluster to run it on. The other thing I've done is I've moved the Movie Lens 1 million rating dataset in here as well. So I've created a ml-1m folder here on my Sundog-Spark S3 bucket. And that's going to make sure that this distributed file system of S3 that contains my 1 million movie ratings is also accessible to my entire cluster. And inside that we have the different files that make up the dataset. Ratings.dat is the actual movie ratings themselves, and movies.dat is all the metadata associated with the actual movies. So our strategy, if you recall, is going to be to run that jar file from the master node of our cluster, and it's going to have movies.dat located alongside it, so it can actually build up that lookup table of movie IDs to movie names when it's outputting the results. But all the cluster needs is the ratings data. So let's go and set things up, make a cluster. What you're going to do is go to aws.amazon.com, just like this. And if you don't have an account already, you would create one, obviously, but I already have one, so I'm just going to sign into the console. And remember, too, this is real money we're spending here now, so don't do this yourself unless you're comfortable with that. All right, once we get into the console here, we're going to select EMR, the Managed Hadoop Framework. And even though it says Hadoop and MapReduce, it also has Spark as part of it. So that's going to be our target here. We want to create a cluster. And we'll call it, I don't know, Movie Sims 1M Test. How about that? Now, logging, if you want to actually put the log somewhere so you can diagnose what went wrong if something goes wrong, you can do that too. You'd want to keep track of that path so you could actually retrieve those logs in the event of a failure. I'm just going to turn that off because I happen to know this script works. And the other thing we need to do is select Spark for the actual software configuration. So we're going to run with Spark 1.6.2 on Hadoop 2.7 Yarn. So cool stuff. And we are just going to stick with the default hardware configuration. So if you wanted to use different instance types, which have different hardware capabilities, different amounts of memory, CPU power, and whatever, you can do that there and select how many you want to use. I know 3 is more than enough for what I'm doing, so I'll just leave that at 3. Keep in mind this makes a big impact on how much this job costs. So you are charged by the instance hour, and there are different rates for different classes of hardware. So the more beefy computers you use, the more they cost, and it can get expensive pretty quickly. Now, you need some way of actually connecting to your nodes once you create them, and to do that you need an EC2 key pair, and this will give you a private key and a public key you can use to log into these instances once they're created. Now, I already have one, so I'm going to use my Sundog EC2 key pair, but if I need to make a new one, just click on this little link here and it will tell you how to do it. So basically, if you go to the EC2 console, back from the Amazon AWS console, you'll see an option there for key pairs where you can create a new key pair. You create one, and what it will give you back is a PEM file. And down here, it actually tells you the further steps you have to do to convert that into a PPK file that can be used on Windows under PuTTY. If you're using Mac or Linux, then you can follow these instructions instead and just use the PEM file they give you directly. But for PuTTY, there is one additional step where you need to actually run a utility called PuTTYGen to convert the PEM file that you get back from Amazon into the PPK file that PuTTY expects. So just follow these instructions and you can get the credentials that you need to log in. And once you've created that key pair and save that PPK file somewhere safe where you're not going to lose it because there's no way to get it back after you've gotten that initial download, you can just specify that in the drop down here. Okay, so moving on. I've got everything set up properly. I'm going to go ahead and create the cluster. And it'll take about, 10 or 15 minutes for Amazon to actually go out there and find some available hardware and get it all spun up and configured and booted up for you. So we're going to sit here, and you can see right now it says it's in the process of provisioning 1 master node and 2 core nodes for our cluster that we're going to run our job on. And through the magic of video editing, we will come back when that's done. So hang on. Okay, so after about 5 or 10 minutes, we see that we now have our master and core machines in the running state here, and my cluster is just waiting for me to do something. So cool, my cluster is ready. So let's do something with it. To do that, first I need to connect to it somehow. So you can see here, under the master public DNS, it gives me the externally available address of the master node that I'm going to run my script from. And if I click on this SSH link, it will tell you exactly how to connect to it. So for Windows, you can use something called like PuTTY for a terminal program. That's what I'm using. And if you need to install it, there's a handy dandy download link there for you. And it tells you exactly how to connect using that. If you're on Mac or Linux, they have instructions for you as well. But I am on Windows, so what we're going to do is copy that address so I can quickly get it in there. And open up PuTTY. type that in for the host name. And then I need to specify my PPK file, my private key, to actually log into that. So remember, I specified while I was setting up the cluster that I was going to use the Sundog EC2 key, and that's where I saved that file there. So now I should be able to just hit open, and there we are, logged into our master node. Now, depending on your security settings, you might actually get a timeout at this point. So if you're trying to figure out why you can't connect, and no matter what you try with your firewall settings or whatever, you still can't get through, odds are it's blocked on the server side. So if you do run into that, quick tip, you can click on the security group here for the master node. And once you're in there, you can click on the inbound rules here and make sure you have an SSH port open. So in this case, I had to actually manually add a SSH TCP port to port 22 to the IP address that I'm connecting from. So if you are having trouble connecting, that's probably what you need to do. But let's go back to where we were, back to the EMR console. And anyway, we are now logged in, so now we can start doing some fun stuff. So first things first, let's see where we are. We should have a little home directory here under the Hadoop user. First thing we need to do is copy over our actual driver script in the jar file that we created using SBT earlier. So let's go ahead and copy that over from S3. EMR, any AWS EC2 node has a set of utilities built in called AWS that you can use to actually copy stuff from S3 and other stuff. So I can type in AWS S3 CP, let's see, S3 / sundog dash, I can't type, sundog dash spark. And what did I call the file again? Movie similarities 1m.jar. Movie similarities 1m.jar here. All right, and you can see that worked. The other thing I need is the movies.dat file, so I can actually construct the lookup table of movie IDs to / names. And again, I put that in the ml-1m subfolder. So let's copy that over as well. AWS S3 copy S3 / sundog dash spark / ml-1m / movies.dat to the local directory. So there we have it. All right, I've expanded the window a little bit here so we can see our results better. And all I need to do now is type in spark-submit, the name of the jar file, movie similarities 1m.jar. And if you remember right, this script requires a command line parameter of the movie ID we're interested in finding similarities for. So I happen to know that Star Wars is 260 in the 1 million data set. Let's kick it off. All right, so we see a few introductory info messages here, and one of the first things the script does is turn off anything but error messages. So we shouldn't see anything else other than progress messages as it actually breaks this up and spreads it out to the cluster. So we're basically waiting for it to get that first action command and create the DAG. It just loaded the movie names, and it is now spreading it out. So right now, as we speak, we are actually computing similar movies for Star Wars using 1 million ratings on a little cluster of 3 machines. Pretty cool stuff. We're already in stage 2. Now remember, the stages are broken up by areas of the DAG that are split up by data shuffle operations. And those stages in turn are broken up into tasks. So you can see right now here in stage 2, we're chugging through 32 tasks. There'll be another stage after this with 100 for the 100 partitions that we set up. And in about 5 minutes or so, this will be done. It doesn't take all that long, kind of the power of a cluster. Chugging through 1 million ratings in every possible permutation of every possible pair of movies and then filtering out the results we want. It's doing a lot of work, but it will do it fairly quickly. So let's come back in 5 minutes here and I'll show you the results. All right, we're almost done here. There it is. Awesome. So we have the top similar movies for Star Wars Episode 4 A New Hope based on 1 million real movie ratings, and this data set's a little bit newer from 2003, so again, we're not going to see any current movies, but the results look pretty darn reasonable. We have Star Wars Episode 5 Empire Strikes Back, Raiders of the Lost Ark, Return of the Jedi. Kind of interesting that Raiders of the Lost Ark was rated higher than Return of the Jedi, but you know, to be honest, I think I might have enjoyed Raiders of the Lost Ark more than Return of the Jedi, so that maybe isn't as crazy as it sounds. And the original Indiana Jones movie, all very good recommendations for someone who enjoyed Star Wars. And then we start getting into other big movies that were good. The Terminator, Matrix, there's some pretty good ones in here. Back to the Future, Princess Bride, all appeals to sort of that geeky demographic, huh? Very cool. Hey, Monty Python and the Holy Grail even. These are actually pretty darn reasonable recommendations. Cool, and there you have it. So that's movie recommendations, similar movies to Star Wars, using 1 million movie ratings, run on an actual cluster using Hadoop, Yarn, and Apache Spark. That's what it's all about. Now, last step. Do not forget to terminate the cluster when you're done. So I'm going to exit out of this, but that's not enough. And I need to go back to the EMR dashboard. And in my cluster, hit terminate. Yes, I'm sure I'm done with it. Now, if you don't do that, the bill's going to keep on running for you. You know, that cluster is still running, and even though you're not doing anything with it, you're still going to be billed for the time on that cluster for that all 3 of those computers, or even more if you set up more. So again, if you're doing this on your own dime and actually following along, please remember to terminate your cluster when you're done. I really don't want to hear about it if you get a bill for $1,000 at the end of the month from Amazon, okay, as opposed to 10, which is about what this cost. All right, make sure that that terminates successfully, and then it's safe to close out of it. But with that, woohoo, congratulations. That's kind of the culmination of what we've been doing here. We actually ran a real big Spark, big data job on a real cluster successfully and got some really useful results out of it. So cool stuff. Let's talk in a little bit more depth about troubleshooting Spark jobs and some of the finer points of running and tuning things. So when we ran that movie similarities script on the cluster, there were a few things we changed. We changed the format of the input file because that changed for the 1 million ratings data set. We changed how the context was set up so that we could override all of the settings for Spark Submit and actually run it properly on a cluster. But there was one other thing we did that I kind of glossed over. And if you go down to the main section here, you can see it here, this little thing here. We actually added this .partition by new hash partitioner 100 to our movie pairs RDD here. And, well, what the heck's going on there? Well, it turns out that's actually a fairly important thing to know about partitioning when you're running large jobs on a cluster. So let's have a little chat about that, shall we? So let's talk about partitioning. Turns out Spark isn't always going to do exactly the right thing for you. So sometimes you need to give it a little bit of a hint of how to best distribute the data that you have. That's what partitioning is all about. So it turns out that our movie similarity script runs pretty efficiently on Scala. If you were on Python, though, it might struggle to keep up with it. And we actually have to do a little bit of tuning of the script to get it to run reliably. That's where partition by comes in. So for one thing, that self-join operation we did was pretty expensive. Spark can't necessarily partition that ideally on its own. And there's also a group by operation that's going to further take the results of all those movie pairs and group them all together at one point in the script. That also needs to be efficiently distributed. So by using the partition by operator on an RDD, we can say explicitly, I want you to take this operation and break it up into this many tasks. So remember, Spark actually breaks down your script, the DAG if you will, based on stages between where it needs to shuffle data, and each stage is broken up into individual tasks that are distributed to each node of your cluster, each executor that you have. So you want to make sure that you always have at least as many partitions as you have executors. That way it can split up the job efficiently. Now there are a certain list of commands you can do, operations on RDDs, that will benefit from partitioning, and here's the list. Join, cogroup, group with, join, blah, blah, blah. Group by key and reduce by key are very common, okay? So you want to make sure that things are properly partitioned before going in there. And another important point is that once you specify a partitioning on an RDD, that partitioning will be preserved in the result of that RDD operation too. So if I do a group by key on a partitioned RDD, the result that I get back will be partitioned in the same way. And that's an important optimization because remember, stages are broken up by the need to shuffle data. So if I have the same number of tasks in each step of my operations here, I don't need to shuffle between those two. So it can actually reduce the number of shuffles that you have to do in your script, and that's an important optimization. So anytime you can partition and preserve that partitioning through a chain of commands, that will help your script run even faster. So how to choose the right partition size? Well, it's a little bit of guesswork to be honest, but like I said, you basically want to make sure that you at least have as many partitions as you will have executors on your cluster. And you might not know ahead of time how big your cluster will be, so you just kind of have to make an educated guess sometimes. Now you don't want to have too many partitions because that can actually result in too much shuffling of the data if you have to split it up into too many different tasks that run in parallel. You know, distributed computing is not perfectly efficient. So more distribution, more parallelism isn't always better. There's usually a sweet spot to be found. But you want to have at least as many partitions as you have executors, otherwise you're going to have these executors and these resources on your cluster just sitting idle, and that wouldn't be good either. So make sure you have at least as many partitions as you have the capacity for executors on your cluster. 100 is usually a reasonable place to start if you don't want to think about it too much. That's indicative of, a reasonably sized cluster, and that will give you pretty good parallelism in most use cases. And that's what we did here. So if we go back and look at the actual code for our 1 million ratings movie similarity script, you can see that we have this movie pairs RDD that we're going to do a group by key operation on here. And group by key is one of those operations that benefits from partitioning. So to make sure that's well distributed, we're taking this unique joined ratings RDD, mapping it, and taking the result of that and partitioning it into 100 partitions. So the syntax here is partition by, and then you pass in a partitioner object, which we create. Hash partitioner is the one you'll typically use, and 100 means I want 100 partitions. So pretty easy to use in Scala. And the resulting RDD will also have 100 partitions, and that will get filtered down into group by key, which will now have a nice partitioned RDD to deal with, and it can do that very efficiently and in a very quick distributed manner. And part of that is why that script was able to complete as quickly as it did. If you think about it, we crunched 1 million ratings and created similar movies for every movie in the entire database in just a few minutes on that cluster. It's pretty impressive, but tricks like this are how you achieve that sort of speed. All right, so in our next lecture, let's talk a little bit more about the specifics of running on a cluster and things to watch out for, and kind of reiterate some of the best practices there. So in our excitement to actually run that 1 million rating script, I kind of just did it and let you watch what I did, but let's get it in writing on some slides here just to review what we did that was special about running a script on a cluster as opposed to running it locally on your desktop. So the main thing that we did was we made sure to use an empty default Spark conf object in our script. There's sort of this hierarchy of configuration settings where one will override the other. And if anything is in your script where you're hard coding a setting into your Spark conf object, that's going to take precedence over everything else. So if you left, a master of local in your Spark conf in the script, that's going to override everything else on your cluster, and your script will just run locally on your master node. That's not what you want, right? So remember to leave that empty. The next layer is going to be the actual command parameters to Spark submit. And if you specify something on the command line, that will override the configuration files for Spark itself. Now the nice thing about something like Elastic MapReduce or a properly configured Hadoop cluster that has Spark pre-installed is that you're likely to have the optimal configuration settings already in the configuration files for Spark itself. So when you spin up an EMR cluster, you don't have to tell it to run on Yarn and Hadoop and all that stuff. You don't have to tell it what other machines are available in your cluster. It just knows. And usually that's how it will work for you. But if you do need to override things, you can still do so on the Spark submit command line. So for example, you might have a really challenging job that has really big partitions for some reason, and maybe your cluster is actually struggling to keep up with it because it's exceeding the memory usage of an individual executor. So if you're not distributing your data well enough, and that can be a result of poor partitioning or just not having enough machines in your cluster, you can start to get executors failing because they're running out of memory. You're just asking them to do too much for an individual process. So for an example, you might end up passing in -- executor memory, 1 gigabyte or something as a parameter to your script when you launch it. And that will tell Spark submit, I actually want you to make sure you have at least 1 gigabyte of RAM allocated to each executor and distribute out things accordingly. Now, that will override anything in your configuration, but if you had an executor memory setting hard-coded in your script, that command line option would do nothing. So just remember that hierarchy. What's in your script takes precedence over the Spark submit command line, which takes precedence over the configuration files of Spark itself. Now, another thing that you might need to specify is the master. Now, one nice thing again about Elastic MapReduce is that this comes pre-configured, but if you do need to specify that by hand, you can tell Spark submit explicitly what to use for its master. And if you say yarn, that tells it I'm just going to be running on top of the yarn cluster manager that's part of Hadoop, or it might be Mesos, or it might be a specific node that represents the master node of Spark's built-in cluster manager. Okay, so again, this will usually be set up for you ahead of time as part of the configuration, but if it looks like things aren't being distributed properly, you might need to set that. All right, so master is used to actually specify the master node of your cluster manager or the cluster manager that you're running on top of. All right, some other best practices here. If you have scripts and data someplace and you don't have a permanent cluster that's running all the time, make sure that you upload those someplace where you can quickly download them to your cluster once you've started spinning it up. Remember, time is money on Elastic MapReduce, so you want to be able to download the scripts and data that your script needs as quickly as possible. I did that by uploading my scripts and the lookup file to Amazon's S3 service, and then I could quickly use the AWS S3 command on my master node to copy those into place so I could actually run them from my master node. Obviously, you want to make sure that your data itself is also someplace accessible in some distributed file store. So I put the actual movie ratings data itself, the 1 million movie rating data set, on S3 as well. And I refer to that using S3N within my script to actually read that data from S3. Now, in the real world, you might be using HDFS or something instead. Whatever, whatever distributed file system you want to use, fine by me. All right, and once you have that all in place, all you need to do is figure out how to log into the master node of your cluster once it's been spun up. And we walk through how to do that with EMR. It's just right there in the dashboard for you, and you can use PuTTY to connect. Copy over the jar file that you want to execute, and along with any files that you need to support that jar file, run Spark Submit with it, and off it goes. And the most important thing, if you're actually running on a shared cluster where you're actually renting time like Amazon Elastic MapReduce, remember to terminate your cluster when you're done. You are being billed by the hour, by the machine, and also for any storage space that you consume. So if you forget and you leave your cluster running and you don't terminate it when you're done, and you don't stick around to make sure that it actually terminated, your bank account could be in for a very, very rude awakening at the end of the month, because AWS bills you monthly, and I can assure you running a large cluster for a month can get very, very expensive. So if you are fiddling around with this on your own, I cannot stress enough, always make sure you've terminated your cluster when you're done with it, and don't create a cluster that's too big. AWS actually has some safeguards in place to prevent you from creating a cluster that's too expensive without special permission. So there's really only so much damage you can do, but over the course of a month, it can still add up to something pretty substantial. So please be conscious of actually what resources you're using on something like EMR. Okay, let's move on. So let's talk about troubleshooting Spark jobs. What happens when something goes wrong or you think something might just be stuck? Well, to be honest, it's a little bit of a dark art. You don't always have a whole lot of understanding about how Spark is actually distributing your application or why things are failing exactly. Oftentimes the messages are rather cryptic. But one tool in our arsenal is the Spark UI. The Spark master node will actually fire up a web server for you that provides a little glimpse into what's actually going on inside your script at all times. So you can see what stage it's on and how it's distributing things all in real time, which can be kind of useful. Now, the downside is that if you're using something like Amazon's Elastic MapReduce, actually connecting to that UI is extremely difficult. It's not impossible. They actually give you instructions in the EMR dashboard on how to connect to your master, but it involves creating an SSH tunnel to your master node from your desktop and also configuring a proxy server from within your web browser. So it's a real big pain in the butt. And in practice, I find it's just as easy to just look at the log messages as they're scrolling by while my job is running. Often that will give you some insight into what's going on anyway. But if you're running locally and testing things out, or you're running on a cluster that you do have direct access to on the network, the Spark UI can be pretty useful. So let's take a look at how it actually works in an example running on our desktop. So let's take a quick tour of the Spark UI. What I'm going to do is run that movie similarities script on my desktop here that processes the 100K ratings data set locally. And that'll run for about a minute, which is just enough time for me to spark up the UI and show it to you. So again, we're going to connect to port 4040 on the host that you're running on from a web browser. So in this case, I'm running on my local host. The IP address of your own machine is always 127.0.0.1. So by directing my web browser to http://127.0.0.1:4040, that will connect me to the Spark UI once Spark is actually running. So with that, let's kick off our movie similarities job. And we'll refresh 127.0.0.1:4040. Now, before that job finishes, I'm going to go ahead and open up all these different tabs here so we can take a look at them, because it only runs for about a minute. And you can see that we have on the jobs page here details of everything that we're running here. You can actually drill into individual jobs and get more information about what they're doing, how much time they're taking, and how much garbage collection time is taking. So you can use this information for tuning your job and figuring out if you need to partition things better. DAG visualization, that's pretty cool, huh? You can actually see the DAG here and how it's been split up for this particular stage. in a graphical manner. That's pretty hot. That's kind of a recent thing. You can actually go into individual stages as well, so you can see how Spark actually broke up the job into individual stages here, and you can visualize those stages independently too. So this is great for optimizing your script. Do you have more stages than you think you need? Remember, stages represent points at which Spark needs to shuffle data. So the more stages you have, the more data is being shuffled around and the least efficient your job is running. So there could be opportunities to explicitly partition things to avoid shuffling and reduce the number of stages. And by studying what's going on here, that can be a useful way of figuring it out. The environment tab gives you some just general troubleshooting information about the environment itself. So, if you have any questions about, do I have the right Java version installed? Do I have the right Scala version installed on my cluster? This will give you the answer. And this tells you that I'm running on Scala version 2.10, for example, Java 1.8. If you're running into weird compatibility issues where things work fine on your desktop, but they don't work at all on your cluster, well, that might be why, and this will tell you why. Information about the Spark job itself. Also useful things, the path for Java. So again, if you're having trouble with dependencies and trying to figure out why a certain library isn't loading, that might tell you why. And more general information about the configuration of Java on your machine. Also, we have the executors tab here. That's actually telling you how many executors are actually running. And since I'm running on my local desktop, it's not too surprising that I just have one executor, but actually it's a little bit surprising because I thought I told it to use every core. So for whatever reason, Spark decided that it didn't actually need more than one executor to complete this job. Now, if you were running on a cluster and you were looking at this and you saw only one executor, well, that would be a sign of trouble, right? That would probably mean that things aren't configured right on your cluster. Maybe you left something in the configuration on in the script itself to run locally or restrict the number of executors, and that would need to be taken out, for example. So that's the Spark UI in a nutshell, and the job's already completed, so let's kick it off again. As soon as the job's done, it shuts down that web server. But we're back up in action now here. So just click around, kind of play around, and I don't know, that DAG visualization I think is pretty hot. So anyway, if you want more insight into what's going on, the Spark UI is there for you, and it can tell you a lot more about how your job is actually being executed and constructed into a DAG. So the Spark UI is just one piece of the troubleshooting pie. As we said, logs can also be really helpful, and oftentimes you can just look at the output that's scrolling by as your job runs on the master node to see what's going on. If something's failing, you'll probably say, something timed out or a heartbeat failed or something like that, and that's a good sign that your cluster just isn't big enough, or maybe you didn't partition your job well enough. Go back to those partitioning slides we went through and see if there are opportunities to explicitly partition some of the operations you're doing, like joins or group bys, to make your job run more efficiently. If not, you might just need to throw more hardware at the problem. Sometimes a job is just too complicated for a small cluster to handle. And if you're seeing things time out consistently or lose heartbeats and keep losing and trying to respin up executors, that's a good sign that you just have a capacity problem and you need to throw more hardware at it. You need a bigger cluster, okay? Now, how do you actually look at the logs if you want to, if you're capturing them? Well, if you're running on top of yarn, you can just use the yarn logs command with the application ID that you were running with, and that will retrieve them all for you. Thing is, on a cluster, those logs are all going to be distributed amongst all the different executor nodes, so reassembling them requires a little bit of work. Now on EMR, you also have the option of dumping those logs to an S3 bucket, so you can get them all together there as well. So when you're spinning up your cluster, there's an option that's actually checked off by default to actually save the logs to S3, and it gives you a default path that it saves them to. So you can just copy and paste that path somewhere and go check for them later. So again, the main thing you want to watch for, the thing that most commonly comes up is that you just don't have enough capacity. And again, if you see a lot of timeouts, a lot of heartbeat failures, you might need more capacity, you might need more memory per executor. That's worth a shot too. You might just be running out of memory. And or you might just need to partition your job better by partitioning. So try all three things. In order of cost, right? Partitioning is going to be the easiest thing to do. Allocating more memory per executor is probably the second easiest thing to do, and actually adding more capacity should probably be your last resort, right? All right, one other thing besides troubleshooting I want to cover is managing dependencies on a cluster. So always remember that your executors aren't necessarily running on the same box as your driver script. So if your executor knows that things are actually running your mapping functions and whatnot, require data that actually physically resides on the disk of your master node or your desktop, that's not going to work. You're going to find that will fail pretty darn quickly. So remember to use the techniques that we covered earlier in the course, like using broadcast variables if you need to share data across RDD partitions. Or make sure that any dependencies you have are loaded ahead of time on each node. If, for example, you might have some dependency that's not preloaded. And one thing you can do, the standard thing to do, is to use SBT to actually bundle all of those dependent packages into your jar. You can also use the --jars option on Spark Submit to make sure that any jar files that contain code libraries that your script depends on is automatically distributed along with your script to the entire cluster. But really, you should just avoid using obscure packages in the first place. If you are using some weird Scala or Java package just because you're too lazy to write 2 lines of code, well, the hassle it takes of actually distributing that dependency to your cluster is very quickly going to negate the benefit of using it. So whenever possible, try to just use the core language features of Scala whenever you can, and the core of Spark. Obviously, sometimes it's unavoidable if you need to connect to a specialized data store or system, but try to keep those dependencies to a minimum as a good best practice. And that's my tips for running on a cluster, so good luck with that. Next, we'll talk about some more powerful Spark technologies built on top of Spark Core and how those work. So let's talk about Spark SQL, very important component of Spark. In fact, you could say it's kind of taken over. Pretty much all of Spark is moving toward data frames and data sets. So let's talk about what these things are. So the whole point of Spark SQL and its associated technologies is dealing with structured data. So up till now, we've been dealing with these RDDs that can contain pretty much anything. You can just stuff whatever you want into a row of an RDD. But with data frames and data sets, you can actually wrap structured data in Spark and Scala. And there are some advantages to doing that. It lets Spark represent things more compactly and more efficiently, and also lets it optimize better. So what is a data frame? Well, a data frame is basically an RDD of row objects. That's really all it is. And a row can, in turn, contain any number of columns of information that may be of whatever type you want. So it's starting to look a little bit more like a database, right? We have these rows of information with discrete columns of given types of data. So we're starting to move from sort of a blobby RDD to a more structured representation of our data. And the good thing is that you can actually treat this like a SQL database. Once you have a data frame, you can actually run SQL queries on it using actual SQL commands. It has an actual schema, and this lets Spark represent it more efficiently. And it also has the advantage of being able to write out to database formats and also import data directly from database formats. So if you can connect to a JSON database or a JDBC database of some sort, you can interoperate very easily with Spark and Spark SQL. Now, we also talk about data sets. So what's the difference between a data set and a data frame? Well, a data frame is really a data set. It's a data set of row objects. A data set, more generally, is a set of structured data. Not necessarily a row, but it could be a specific type in Scala. So for example, let's say I have a case class in Scala of a person that might consist of a string name and an integer age and so on and so forth. I can have a data set of person objects. And the advantage of that is that Scala and Spark will know upfront at compile time what's in that data set. So if there's any errors that pop up while trying to optimize that, you'll hear about that when you're compiling as opposed to later on when you're running it. And that can be important because by the time you're actually running this code, you might be on a cluster where time is money. So catching these errors a little bit earlier is a good thing. It also lets it do a little bit better optimization as well. And you can also convert RDDs to data sets very simply. There's a toDs function. And if you have a known type inside your RDD, you can use that to convert it into a nice structured data set for you. So data sets really are the new hotness. I can't stress this enough. We've kind of learned a lot about using RDDs up to this point in the course, and that's a very important fundamental thing to have under your belt with Spark. But the trend is more and more to use data sets instead of RDDs wherever possible. Now, it doesn't always make sense. You don't always have structured data, and not everything can be thought of in terms of SQL or as of a database. So if you're just doing straightforward transformations of data, maybe data sets aren't appropriate. But for a lot of data analysis tasks, data sets are going to be the API of choice going forward. They're really taking over. And it also is important for interoperability because it is also seeping its way into other aspects of Spark. MLlib is moving toward a data frame-based API. Spark Streaming is moving towards something called structured streaming that also relies on data sets. So as we look forward, data sets are going to become more and more important to Spark over time. How's it work? Well, one important difference is that you're going to create a Spark session object instead of a Spark context object when you're dealing with Spark SQL and data frames and data sets. And this Spark session wraps a Spark context and also a SQL context. So you can actually get at those underlying components, but it's sort of a one-stop shop for any processing you need to do. You can get back a Spark session and actually run SQL commands on it directly. And remember to stop that session when you're done. It's just like opening a database connection from a programming standpoint. And there's some cool stuff you can do with data frames. So you can not only just run SQL queries on them directly, but you can also do SQL-like things programmatically. So for example, you can call .show to display the top 20 results in a data frame just for debugging purposes. .select, just like a select statement in SQL, pull out some specific column that you want to look at. Filter, you can actually do syntax like this, which is kind of weird, but cool. You can say, for example, my result data frame, extract some specific column and test whether that's greater than some number. So you can actually put in little expressions here and it will just work. You can do a group by just like you could in SQL. You can do things like mean and other, average and arithmetic expressions as well. So it's a very powerful group of commands and functions that have been added on top of what you can normally do. And you can also express this just using plain old SQL commands as well if you're more comfortable with that. You can also get back a RDD from a data frame. So if you want to do the sort of old school techniques like mapping and things like that, or a flat map, you can extract the RDD out of a data frame and do that as well. Another cool thing is once you are using Spark SQL, you can actually open up a SQL connection and treat Spark just like any other database. So if you actually take a data frame and cache the results, you can just let it sit there, and you can actually open up a server that will let you connect to it. And if you're actually using the Databricks Community Edition, you can actually do that within a notebook as well. Pretty cool stuff. User-defined functions, another cool aspect of Spark SQL. You can actually define your own functions and put them in your own SQL context. So, for example, let's say we want to define a function that will square something. We can just say val square equals this little inline function, x gets mapped to x times x. And we can do something like this to actually add a new column to our data frame. Let's say we have one column in there called value. This code will add a new column called square using our user-defined function to take the value and square it. And you could also do the same thing in a SQL query. So once you define a user-defined function, you can actually use that within your SQL going forward. So it's also very extensible. So it's all very hand-wavy up to this point. It's going to make a lot more sense when we actually dive in and do it. So let's go ahead and dive into a few examples. Like I said, data frames and data sets are increasingly important to Spark, so I want to spend a little bit of extra time on this. What we're going to do is go back to our fake social network data, and we're going to do a couple of things with it. First, we're going to do some queries on that data using straight-up SQL commands, so treat it just like it's a database and see how that works. Then we're going to go back and actually use data sets without SQL and just query those using commands on the data set itself and see how that works. A little bit more efficient. And finally, as an example of how you can actually use data sets as an alternative to RDDs, we'll go back to our most popular movies example and rewrite it using data sets instead of RDDs and see how much simpler that is. And in theory, it should be a lot faster as well. So let's get our hands dirty and dive in. All right, let's take a look at Spark SQL in action, get down to the nitty-gritty of how it actually works. So I've gone ahead and imported the sparksql.scala file from the course materials into my project. You've seen me do that enough times. I don't think I have to go through the details again. So go ahead and pause and continue when you've got that up and running here. And let's take a little look. So we've imported the spark.sql package here into our driver script along with everything else. And what we're going to do is load up that old fake friends.csv data that we used earlier in the course. And instead of actually analyzing that using RDD functions, we're going to analyze it using SQL. So we're going to convert that to a structured format into a data set that we can actually issue SQL commands on. Pretty neat stuff. So the first thing we're going to do is set up a Spark session object. And this is different than we've set things up before. Usually we've used Spark contexts, but by using a Spark session, we get back an object that we can actually do SQL commands on and actually deal with data sets instead of RDDs. So the syntax here is we're going to create a Spark session using a builder method, specify the app name, master of local on every core like we usually do. This next line is specific to Windows. There's actually a bug, unfortunately, in Spark 2.0.0 where you have to explicitly set a directory for temporary data on Spark SQL on Windows. So if you're not on Windows, leave that line off, comment it out, okay? But if you are on Windows, you won't be able to run without it. Go make sure you do have a C temp folder on your hard drive first. If you don't, go ahead and create that right now, please. And finally, we'll call get or create to actually create our Spark session or get an existing one if we're recovering from a failure. So that's kind of cool. You know, if we actually have some sort of a problem that comes up, it can automatically recover from where we left off using get or create. Next thing we're going to do is actually load up our data here. And since our data is unstructured, it's just a CSV file, we have to first structure that before we can actually convert it into a data set. Now, if we did have structured data, let's say that our friend's data was in an actual database or in a JSON file, for example, we could load that up directly and actually create a data set out of it right away. For example, we could say spark.read.json given a JSON file name, and that will give us back an actual data set as opposed to just an RDD. But since our data is unstructured, we have to first impart structure upon it before we can do data set stuff with it. So we'll do that with this mapper function. And all this does, if we go up here, it maps every input line of that RDD to a person object. So that person object is defined by this case class here. And case class, again, is a Scala construct for basically creating a very simple class that has accessors built into it and constructors built in for it. It's a little bit magical because the names of all these parameters actually map to actual column names in the data. So by mapping our string into these person objects, we end up with named columns in our resulting RDD. So we know that we have an integer that is named ID as one column. We have a string with the name of name as another column. We have an age integer column, and then we have a numFriends integer column. Okay, so by calling this mapper that creates person objects based on the comma delimited values that we extract, we end up with this structured data that we can then create a data set out of. Now, a little bit of voodoo here. You have to do this import spark.implicits._ line in order for Spark to be able to convert a structured RDD into a data set. So anytime where we're actually going to be inferring the schema of something, we need to make sure that we're importing spark.implicits. Otherwise, you'll see these weird cryptic errors, and you'll wonder what the heck is going on. But if you're ever in a situation where you're calling .2ds and it just doesn't compile and you know it should, you're probably forgetting this line here. But with that in place, we can do this. And take a look. Schema people here actually ends up being a data set of person objects. So here we finally have an actual data set. And the beauty of that, again, is that we can actually treat it just like a SQL database. And what's even more beautiful is that Spark has special optimization logic for things like this, where it can actually do a better job of optimizing your task on a cluster. So at this point, let's print out the schema, take a look at what it actually inferred it to be. And now things get really interesting. We can call create or replace temp view to actually convert the contents of this data set into what looks like a SQL table, and that table name will be people in this example. So at this point, we basically have a little SQL database sitting in memory inside of Spark, distributed, potentially on a cluster that could be huge. And we're just going to refer to it like we would any other SQL database under a table name called people. And check this out. We can now create a data frame of results by just calling spark.sql. Remember, Spark is our Spark session object that we created up here. And we can call .sql with plain old SQL, like any old SQL you can dream up, including user-defined functions, anything. Huh? So we're going to say select star from people, where people is what we created our temporary view, our little table from schema people, where age is greater than or equal to 13 and age is less than or equal to 19. So what we're going to get back is the results of this SQL query, which will be a data frame of all the teenagers in our input data from that data set. Pretty neat. We'll collect the results and print them out. So let's, and then when we're done, remember to call stop on the session object. You should think about this just the same way as opening up a database connection in any other language and stopping it when you're done. So let's go ahead and run that. I already created a run configuration for it. If you need to do so, please go and set one up that looks like this. Project, given your project name, and the main class should be com.sun.software.spark.sparksql, just like that. And let's go ahead and run it and see if it works. And sure enough, it did. Pretty cool stuff. So here's that part where we said print schema, and you can see here that's actually outputting how it converted that RDD into a data set. And that data set structure has ID, name, age, and numFriends of given types, integer, string, integer, and integer. So Spark is going to use that information to send information around in the most compact manner possible and also optimize that SQL query as well as it can as well. And that SQL query that we ran gives us back all of the people that are teenagers in our data set. So these are all, remember, user IDs, names, ages, and number of friends. All these ages should be between 13 and 19, and sure enough they are. It worked. Pretty cool stuff. So that is Spark SQL in a nutshell. But there's more than one way to do it. So in our next lecture, let's show how we can do the same thing without actually incurring the cost of parsing actual SQL commands. We'll do that next. So you don't have to use SQL with Spark SQL necessarily. You can also just call functions directly without actually relying on the SQL syntax itself. And that can be a little bit more efficient. So let's see how that works. Let's take that same set of data, the fake friends data, and analyze it a different way. So I've gone ahead and imported the dataframes.scala file here into my project. Go ahead and hit pause and take care of that if you need to. And let's take a look here. Again, I'm importing the SQL package from Spark. And a lot of this looks the same, so we're starting off just like we did in the previous example where we create a Spark session using the name Spark SQL, every core of the computer, and this little hack that we need on Windows in order to get around a bug in Spark 2.0. So again, make sure you have a C temp folder on your hard drive, and if you're not on Windows, remember to take that line out. All right, so just like before, we're going to load up our fakefriends.csv comma separated value data and use this mapper to convert it into a structured piece of data where it consists of an RDD of person objects. And then, like before, we're going to call 2ds on it, which can take advantage of spark.implicits to actually convert that RDD into an actual data set where it knows what the actual format of the data is at compile time. And we're going to cache that data set because we're going to do more than one thing to it. So we want to make sure we don't have to reconstruct that every time. Okay, so let's see how that works. We'll print the schema like we did before, make sure that it's still correctly inferred the structure of our data and the types of that data. And we'll have some fun with it. So let's start by selecting the name column. So remember, this data set is just like a database at this point, and I can do SQL-like operations on it. But instead of actually calling spark.sql select name from, some temporary view that I created, I'm going to operate on the data set directly here and call people, which is, again, a data set of person objects, dot select the name column, which again was inferred from our case class up here. Just by the virtue of it being called name up here, it was able to infer that column number 2 is called name and contains string data. And we'll call show, which is just a way to quickly show the top 20 results in that data set. So a little handy thing for debugging purposes. Okay. Next thing we'll do is filter out anyone over the age of 21. So we just want underage people. Let's print those out like we did before. So we'll call people on our data set, call filter, and we can actually put an expression in there where we can say people age, that means the age column, less than 21. So it might surprise you that that syntax actually compiles, but it does. Scala's kind of cool that way. We can actually just pass in this expression and it will do the right thing. It will actually filter out anyone with an age of less than 21. It's a very natural syntax that just works and show the top 20 results of that operation. We can also do group by operations like you would in SQL as well. So what this is going to do is group up the entire data set by age and count out the number of every age occurrence in there. So that will give us the total number of 18-year-olds, the total number of 19-year-olds, and so on and so forth, and then show the top 20 results. Now you might remember we've actually had to jump through some hoops to do this before without using data sets. So to do this just using straight up RDDs and maps and reduce operations, that can be kind of a tricky thing to do, but very simple using data sets. So we just do group by age and count and we're done. Print that out. Finally, let's show how we can actually manipulate an existing column. So what we're going to do here is select the name column and actually take people.age, add 10 years to it, and show the results. So what we're going to do here is select out the name column and select out the age column, adding 10 as we go, and show those results as we go. Okay, so we're not actually changing the people data set itself, but we're going to extract it in such a way that we're artificially adding 10 years to everyone's age as we print out the results. So pretty interesting. You can do stuff like that as well. When we're done, we'll call stop on our session object, and that will tell Spark that we can stop what we're doing. So let's go ahead and run it. Go to the Run menu and Run Configurations. I already set one up, so go ahead and set one up yourself that looks like this. Data frames with the project name and the com.sundogsoftware.spark.dataframes class name. Let's run that and walk through what comes out of it. All right, pretty quick. Let's start at the top and see what we got. So we started off with the same schema, and sure enough, it worked again. So we have our structured data here in our data set with an integer ID, a string name, an integer age, and an integer number of friends on each. Those are all of our columns for every row of our data in our data set. All right, the first thing we did up here was select the name column, and sure enough, that worked. So this is just printing out the first 20 rows in our data set, just pulling out the name. We then did this example of filtering out anyone over the age of 21 with this pretty neat syntax here that's very easy to read, and sure enough, it did work. Everyone that comes out of that operation has an age of less than 21. We then did that group by operation, and you can see it had to work a little bit harder for that one. But we got the answers we want, so here we are, 8 31-year-olds in the data, 17 26-year-olds, and so on and so forth. If we wanted to, we could have tacked an order by in that command as well to get that ordered by age. So just like you would do order by in a SQL command, there's an order by command, order by function as well that you can call in a data set. And our final example here, where we added 10 to everyone's age on the way out, we ended up making everyone 10 years older in our resulting data set here. And here's an example of the results of that. So Wei Yun may have started off at 59 years old, but in our resulting data set that we printed out the results of, he ended up being 69. Poor guy. And there you have it. So those are some examples of what you can do. There are other functions you can do as well in Spark SQL too. Pretty much if there's a SQL command, there's probably a corresponding function that you can use as well. So it's sort of up to you if you want to issue SQL commands or do it in this style. I prefer this style because, you know, it just seems a little bit more direct to what you're trying to do. Seems a little bit more efficient to me. So there you have it. Let's do some more stuff with Spark SQL because, again, datasets is a very important feature of Spark 2.0, and it's going to become even more important going forward. So let's soldier on. So remember I said datasets are kind of taking over Spark, and you should be using datasets instead of RDDs anytime it makes sense because it is a faster implementation. It can actually optimize SQL queries a little bit better than it can with plain old RDD operations. And it can also represent data more efficiently when things are represented in a structured format. So as an example, let's go back to that most popular movies example we did a while ago in the course. And instead of using RDDs, we're going to use a data set to actually get the answer that we want, to find the most popular movies out of the movie lens data. So let's take a look at how that works. I've gone ahead and imported the popular movies datasets.scala script into my project. So hit pause and go take care of that if you'd like to follow along. And I certainly encourage you to do so. So let's take a look. So the first part of this script is actually unchanged from the popular movies.scala example. We just have this little function here that loads up the movie ID to movie names map. Nothing new there, so let's not talk about that too much. And now, remember, we're trying to deal with structured data now. We're dealing with data sets, so we need to define the structure of that data. So here we're defining a movie case class that only contains one thing, the movie ID. So remember, all we're doing is trying to count up the grand total number of times each movie was rated. And to do that, the only information we really need is the movie ID. We can map that to movie names at the end when we're printing out the final results. We don't care about the ratings. We don't care about the timestamps. We don't care about each individual user. All we care about is the movie ID for this problem. So let's plow ahead here. We're going to create a Spark session, just like we did in the past two examples, instead of a Spark context. That will let us do SQL operations more easily. We're going to call this popular movies, local every core. Remember again, this config line is only needed on Windows, and you do need to have a C temp folder on Windows for this to work. You need that line with Windows. It won't work without it. If you're not on Windows, it won't work with it. So if you're not on Windows, remember to get rid of that line. And once we have our Spark session object, what we're going to do here is load up our u.data, the movie ratings data from the movie lens data set. Doing it the old-fashioned way through the Spark context here because that is unstructured. But again, if we had JSON data or an actual database to import this data from in a natively structured format, we could do this straight into a data set without this intermediate step. You know, we could just say spark.read.json, for example, to suck in JSON data. But since this isn't structured, we're going to have to structure it ourselves before we can turn it into a data set. That's what we're doing here. We're calling map on that raw data, What we're going to do is take that tab delimited data, extract the second field, which is the movie ID, and convert that to an integer. So we're going to create a new movie object based on that movie case class, passing it in the movie ID that we extract from each line of that input data. So what we're left with is an RDD called lines, which is an RDD of movie objects, okay? And each movie object just contains a single column, the movie ID. So we can import spark.implicits. That will allow us to convert that lines RDD into a movies data set. So at this point, we've converted our RDD to a data set of movie objects. And with that data set, we can do SQL-ish things. So here's where things get interesting. Now remember back when we solved this problem with RDDs, we had to kind of jump through some hoops. We had to first map things to movie IDs and the value number 1. So we had key value RDDs. And then we used a reduce operation to actually count up all of those counts for each individual movie. But we can do that just using a SQL styles query here, right here. So this is a much more simple one-liner sort of a thing here. We don't have to do any like crazy stuff of mapping things to key values where the value is 1 and doing a reduce. We can just do things in a more intuitive SQL format here. So let's take a look at what's going on here. We're taking our movies data set and we're going to group it by movie ID. So that does a group by movie ID and a count. So what that's going to do is add a new column to my data set called count. That is the count of how many times each unique movie ID appears, which is exactly what we want. And it's just a very, very intuitive, very natural, very common thing to do in SQL. But using map and reduce, it's a little bit more difficult. So this is a good example of where a SQL-style approach to a problem is a lot simpler. And we can go beyond that. We can actually order our results using order by in descending count. So we're going to take the count field, order it in descending order. So in what we had to do in like multiple steps before, we can do in one line of code here. We're going to group up all of our movies by movie ID, count them all up, order them in descending order by count, and then cache the results so we can issue queries on that. So at this point, we should have a data set that looks like this, where it's movie ID and count, where the count is descending. And we're just going to show the top 20 results just to get that intermediate feel. Then to make it human readable, we're going to grab the top 10, load up our movie ID to movie name map, and just apply that map as we print out the final results. So we'll iterate through each of the top 10 results. We will take the movie names, extracting each result as an integer, and then print out the movie name for each one. Finally, remember to stop the session when we're done, and that's all there is to it. So there you have it. Again, the key point here is that what took multiple steps and a little bit of weirdness with an RDD is actually just a one-line operation here using Spark SQL and datasets. So pretty neat stuff. Let's see if it works. Go to run configurations. I've already created a popular movies datasets run configuration, so hit pause and go take care of that if you need to. And let's run it. 100,000 ratings, so it does need to chug through that a little bit. Optimizing that query as we go, and there we have it. So here we have that intermediate output here where we're looking at the top 20 results here of movie ID and count. So that's what that one line of code gave us at the end there. And then our little bit of code there to make it human readable. Sure enough, the #1 film in the Movie Lens dataset is still Star Wars, and followed by Contact, Fargo, and then Return to the Jedi. So this dataset's showing its age from the 1990s, but it is accurate information. So there you have it. Very cool stuff. So it's a good example of how using datasets can actually make life a little bit easier for certain types of problems. And we've gone back and taken an old RDD solution to a problem and made a dataset solution to the problem instead. And I would challenge you to do the same thing. Go back to a different example from earlier in the course and see if you can actually convert it from an RDD-based solution into a dataset solution using the capabilities of Spark SQL. It would be a very good exercise for you. We've done some other simple examples earlier in the course. See if you can use the power of datasets to actually make it a little bit simpler, a little bit more intuitive. So that's my challenge to you. All right, and there you have it, Spark SQL in action. Very important stuff again. Again, the whole Spark world seems to be moving in the direction of more Spark SQL powered features all across all aspects of Spark. So very important you understand this going forward. All right, hope that made sense. Let's move on. One really cool thing about Spark is that it has methods for doing machine learning and data science at very massive scales using a cluster. So that's kind of cool. It's called MLlib, stands for Machine Learning Lib. Let's talk about what it can do. So it's a little bit tough to talk about MLlib if you don't have some sort of a background in machine learning or data science. I do offer a course on that, a little plug there. But, here are some of the basic things that MLlib can do today. And this list is always expanding, so they're always figuring out clever ways of actually distributing some of these algorithms. It's not easy. Not all machine learning algorithms really lend themselves to being distributed, but they've figured out quite a few of them. One thing it can do is feature extraction, so TF-IDF, term frequency, inverse document frequency, basically a fancy way of breaking up documents into features, words, and figuring out how the probability of a word correlates to a given document. That's basically a useful thing for doing search. Okay, so if you're implementing some sort of massive search algorithm, MLlib could be useful in actually processing your documents into data that can actually be used for search. It also has methods for basic statistics, chi-squared, correlation coefficients, simple min, max, mean variance. Honestly, you probably don't need MLlib for that sort of a thing. It's pretty simple to do anyway, but if you're going to be using MLlib anyhow, it does offer quick ways of doing those sorts of things. Linear regression and logistic regression, very common thing to do in data science. It basically, you want to fit a bunch of data to a line and use that line to predict values that you haven't seen yet. So let's say you have some data set of something plotted against something else, like, I don't know, age and income or something, or anything you can dream up. If you think there might be some sort of linear relationship between these two things, you can use linear regression, for example, to get a line equation that fits the data, and then use that line to predict, say, income for ages you haven't seen before. So MLlib can help with that at large scale as well. Support vector machines, basically a way of doing classification in multiple dimensions, a little bit beyond the scope of this course. Naive Bayes classifiers, a common example of that is a spam filter. So you can actually train a naive Bayes classifier with a bunch of email data that's known to be classified ahead of time as spam or not spam. And after training on that data, you can apply that classifier to new emails to try to predict if they're spam or not. So you can build a very simple spam filter using naive Bayes. And MLlib gives you a way of scaling that out to a cluster if you're going to deal with a massive email data set. Or email is just one example of it. Decision trees, cool stuff. That's basically a tree of decisions based on how to actually predict something given, a chain of data. So one example I've seen recently is basically a decision tree of who will win the presidential election in the United States in November of this year. There's a decision tree that shows, okay, well, if Trump wins Florida, there's this set of decisions that can lead to a certain outcome. And if Trump loses Florida, there's another set of decisions that can lead to a different outcome. And little aside, I live in Florida, and it turns out Florida is, in fact, the biggest deciding state there. But MLlib, if you have some massive set of data that you need to construct into a decision tree, it can help you do that as well. K-means clustering, also something that MLlib can distribute for you. It's just a way of automatically clustering data. It's an unsupervised learning technique, meaning that you don't have to actually train it on real data. It can just look at a spread of data points and actually try to cluster them together into areas that seem to be like tightly correlated. It's up to you to figure out what those clusters mean, but sometimes it can help you sort of discover genres in music or things like that. Principal component analysis, singular value decomposition. These are all what we call dimensionality reduction techniques in data science. Basically, if you have a lot of different features of a given data and you want to boil that down to something you can more easily visualize or process, these are techniques for doing that. For example, an example that I use a lot is flowers. Let's say that you want to be able to predict the species of a flower based on 4 attributes: the length and width of a petal and the length and width of a sepal. Well, it's kind of hard to visualize 4 dimensions of data, but with SVD or PCA, you can boil that down to a lower dimensionality set and actually visualize that data and look for clusters in a lower dimensional space. And finally, we can also do recommendations using a technique called alternating least squares, and we're going to do that as part of this lecture. So earlier in this course, we actually found movie similarities using our own algorithm written from scratch without using MLlib, and the results are pretty good. So we could say, for example, if you're a person who likes Star Wars, you might also like The Empire Strikes Back and Indiana Jones. And we got some pretty good results there. Well, a while ago, there was actually a contest run by Netflix called the Netflix Challenge. They used to have their own recommendation algorithm, and they had a little contest where they would award, I think it was $1 million to anyone who could improve upon their existing algorithm in an existing way. And one of the winners was based on a technique called alternating least squares. So let's see if that actually does outperform the way we did it. Now, MLlib introduces some specialized data types you have to use that we'll take a look at. One is the vector class. One thing you see a lot in data science and machine learning is that you have these big arrays of information where you have a lot of missing values or empty values. And a sparse vector is a way of compactly representing that sort of a thing. So, for example, if I have a vector of all of the movies ever made and I'm keeping track of the ratings for an individual, odds are an individual has only actually rated a handful of those movies. So we can much more compactly represent that vector of ratings as a sparse vector that only contains the movies that person actually rated. Label point, idea there is if you're doing supervised machine learning where you basically want to predict the label for a given point. Label point is a way of associating a label with a point, where a label might be some classification like genre or race, income range, whatever you can dream up, right? And rating, something we're going to use right now, for example, a rating of a user for a given movie. If you want more depth on MLlib, a good book I like is Advanced Analytics with Spark by O'Reilly. So go check that out and pick it up if you want to learn more about MLlib in action. Very good book and lots more examples in there too. So with that, let's go make some movie recommendations. And the nice thing about MLlib is just how darn easy it is. So look at this. Just a handful of lines of code, and that's pretty much all you need to make movie recommendations using MLlib with the Movie Lens dataset. So here we're just loading up the u.data file from the ML100K dataset into a data RDD. We're mapping that into rating objects. Remember, rating is one of the new MLlib data types. So we're basically creating a rating object for each line that has the user, movie, and rating. And we're stuffing that in a ratings RDD. And we're going to cache that because MLlib is going to use that data multiple times. Finally, we just call als.train with a couple of parameters here that we've chosen to actually generate a model that can recommend movies for individuals based on all those ratings. And with basically one line of code, we have that model back, and we can actually call recommend products on that model for a given user ID. So this is saying I want the 10 best recommendations for a given user ID based on the model that I made from all these ratings. And that's all there is to it. So deceptively simple, It's I kind of look at black boxes like this a little bit skeptically, and let's see if that skepticism is founded. So let's actually run this, see what kind of results we get. All right, let's use MLlib to actually make some movie recommendations using the Movie Lens 100K dataset. So the first thing I've done is I've modified the dataset a little bit. So I've gone into the u.data file and added 3 entries for a fictitious user. And what these ratings mean, basically, is that I've created a new user ID 0, which is going to represent me. And this particular user loves Star Wars, which happens to be ID 50, and loves The Empire Strikes Back, which is 172. 5-star ratings on both. But for Gone with the Wind, which is movie ID 133, 1 star. Hate that stuff. So, I've basically made a persona here of a science fiction geek who, doesn't like historical romances, right? Not that hard of a person to imagine, right? So I would expect, things that are similar to Star Wars and Empire Strike Back, but not similar to Gone with the Wind to come back in my recommendations, okay? Let's see if it works. So I have already imported the movie recommendations als.scala file from the course materials, and you feel free to run this yourself if you want to. And not a whole lot to talk about here that we haven't already talked about. We have the same function we've had before for actually constructing a map of movie IDs to movie names after parsing in the u.item file. That's all that function does. And down here is the same code that we looked at in the slides, so nothing's really different here. Just the usual boilerplate stuff for setting up your context, load up the movie name dictionary, and then the stuff we saw on the slide. We load up the u.data file, the actual movie ratings, and we map those ultimately into rating objects, which are part of the MLlib library that represents user, movie ID, and rating. And we cache that ratings RDD that comes back because it's going to be used more than once. We train a recommendation model just using als.train. It's just that easy, where we pass in the RDD of ratings and parameters for rank and num iterations. There's no real good guidance on how to set these, but I've tried, pretty much every recommended combination that's out there. And I've also looked up people who have actually done train test experiments to try to optimize that and find the optimal values. And around here is where it ends up. So that's kind of how I made an educated guess on those. We will take the user ID that we want to get movie recommendations for from the command line arguments, and then we will print out all of the ratings that we find for that user ID by just filtering that ratings RDD based on that user ID. And then we will actually call recommend products on the model that we had to actually get back the top 10 recommendations for that user ID and print them out. So let's see how it works. Now I've already created a run configuration for this script. I called it Movie Recommendations ALS, put in the usual stuff. We've done this enough times, you don't have to go through it again. The only thing different here is that I did add an argument to the Arguments tab of 0, meaning that I want recommendations for user ID 0. So let's go ahead and run that and see what happens. Pretty darn quick. Did a lot of work there. I saw a little flash there of stage 25, so it's a very complicated job, and it's using a lot of complex machine learning algorithms there too. So what happened here? We loaded the movie names, we trained the recommendation model, and we said we want ratings for user ID 0, and here are that person's ratings. And like I said, Star Wars 5 stars, Empire 5 stars, Gone with the Wind 1 star. But the recommendations I got just don't make sense at all. I don't even know what some of these movies are. I mean, Low Down Dirty Shame came back as a top result, Endless Summer 2. I mean, some of these kind of make sense. Underworld, maybe, but the other ones are just crazy. And what's even worse is that if I run this again, I'm going to get a totally different set of results. There's kind of like a random component to this algorithm where you don't even get the same result more than once. I mean, there's definitely something going on here where there's some minimum threshold that should be in there that isn't, right? Like I'm getting from some very spurious results here. But I've tried all sorts of different parameters for it, and I just can't get it to be better. So, well, let's talk about what might have happened there in a little bit more depth. So what the heck happened there? Those results were terrible. And this is supposed to be the greatest movie recommendation algorithm there is. Well, it turns out that ALS is really sensitive to the parameters that you give it. But I've tried a bunch of different parameters for this, and like I said, people have done a lot of research on the right parameters to use there, and even those didn't produce good results for me. I've tried normalizing the ratings data, that didn't help either, so it just seems that this particular algorithm isn't a good fit for the 100K Movie Lens ratings data to begin with. Honestly, I'm not even sure it's working the way it's supposed to. Those results are just so wacky, it's hard for me to believe that it's really doing the right thing. And this is a good example of where putting your faith in a black box algorithm like this can be kind of a dodgy thing. You know, I don't really know what's going on under the hood. Sure, I can go look at the source code if I want to and reverse engineer it, but you'll notice that we got much better results just getting our own movie recommendations using our own algorithm that we implemented in Scratch without MLlib. And it's really not much of a leap to take that movie similarity script that we wrote and take it to the next level and actually find similarities for movies that I rated highly and combine them together for a list of recommendations. That would have produced far better results in this case. But remember too, when I was making those movie similarities by hand, the hard way, I did have to put in a bunch of minimum bounds for the number of co-ratings and things like that, and minimum scores, and those sorts of heuristics might not be present in the ALS algorithm, which causes it to bubble up a bunch of spurious results. But again, you know, it's an example of where having more control and more in-depth knowledge of your algorithm can be a benefit. And it's also a great example of where complicated algorithms aren't always better. You know, this is sort of a general lesson in machine learning and data science in general. Good data will always trump fancy algorithms. And the fancier the algorithm doesn't necessarily mean you're going to get better results. You know, often simplicity produces the best results. Another lesson here is never blindly trust the results that you get back from a machine learning algorithm. You always need to evaluate them yourself and look at them critically and measure, are they actually good results or not? And in the case of movie recommendations, that's a hard thing to measure, right? How do you actually measure quantitatively whether this is a good recommendation? It's really kind of an art to it. So in some cases, you know, in this case, you could just take a look at it and say, this doesn't make sense, you know, and you know something's wrong and needs further work. But sometimes the issues are a little bit more subtle, and you actually need to figure out, okay, how am I going to measure the effectiveness of these recommendations over time? What's the behavior I'm really trying to generate by showing people these things, and am I actually achieving that? And sometimes, you know, the issue is the quality of your input data itself. So keep in mind, this is a relatively small data set that we're dealing with. It's also very old data, and probably people that are self-selected, probably mostly students at this college that was putting this project together. So lesson of the day, don't always trust algorithms that are outside of your control. More complicated algorithms aren't always better, and always make sure the data you're using is clean. So there you have it. But MLlib is still a very useful tool. So let's move on to a different example where it actually works better. And this is, you know, on a simpler problem, regression. So let's talk about that next. Let's talk about doing linear regression using Spark and MLlib if you want to create a linear model of a massive data set. And I think we'll have a little bit more success with this one. What is linear regression? It's a very fancy term for a simple concept, which is a common theme in the world of data science. People like to sound smart in this field, it seems. All it is fitting a line to a bunch of points, of observed points. So, for example, let's say I have a bunch of data of people's weights and heights. I can plot those on a graph like this and fit a line to it that minimizes the error between any given point and the line itself. And you can use that line to actually predict unobserved values. So, given this data set of people that I actually know the weight and height of, I can plot a line, and let's say I get a new person, and I know their weight, but I don't know their height for some reason. I can actually use this line to predict the height for a given weight. So usually the thing you're trying to predict is on the y-axis here. So let's say I have someone come along who has a weight of 120 kilograms. I can use this line equation to actually predict the height of that person, assuming a linear relationship. Obviously, not everything has a linear relationship, but if you eyeball the data, you can usually spot that pretty quickly. Why they call it linear regression or regression? Well, there is some weird historical reason that somebody told me once, but it's kind of confusing. It's really better thought of as just fitting a line to a bunch of points, or prediction would be a better word than regression here. How does it actually work mathematically? Well, it uses a concept called least squares, generally speaking. And the idea there is to minimize the error between the points and the line that you fit the points to. So, makes sense, right? Why squared error and not just plain error? Well, by using the squared error, we can make sure that positive and negative differences both get counted as positive. And by using the square, in particular, big errors count more against it than small errors. So it's a good metric for actually making sure that the line fits your data points in the best way possible. If you remember back to high school, the slope-intercept equation of a line is y equals mx plus b, where m is the slope and b is the y-intercept of that line. Basically, what linear regression does is figure out m and b for you. And it can actually do that based on some pretty easily derived statistical qualities of your data here. And how the math kind of works out is actually pretty elegant, but I'll leave that for another time. However, there are more complicated ways of doing linear regression, and that is what MLlib chooses to do. So, kind of like ALS was a little bit overkill in terms of complexity for the problem at hand, Spark MLlib does it again with regression. They use a technique called stochastic gradient descent instead of what I just described. And yes, this is actually a good thing if you're dealing with multiple dimensions of data. So higher dimensional data is going to find contours to curves in a more robust manner. But it is a more complicated algorithm, and therefore it is more expensive to run. Granted, we're on a cluster here, so we can get away with it. For standard linear regression, maybe you wouldn't need a cluster at all. So I can see the point there, but there are some caveats to it that we will talk about in a moment where that kind of makes it a pain. Anyway, using it is actually fairly straightforward. So you just set up a linear regression with SGD object from the MLlib library. And you set up an algorithm and give it a bunch of parameters for its optimizer. And again, we have a bunch of magic numbers here, and there's not a whole lot of good guidance on how to set these effectively. You just kind of have to keep trying things until you arrive at something that gives you good results. And often, half of the work is just iterating on different permutations of these parameters until you find the ones that yield the most accurate results and the best predictions. So the way you do that in practice, you'll take this algorithm and train it, given a bunch of known data points. So, given you have, say, 100 people where you've already measured their height and weight, you use that as your training data to actually make this model. And then you can use that model to create a line that you will use for predicting new data points. So if you have new people where you know the weight but not the height, you would then test the model using that data. Now, the problem with SGD is that it doesn't handle feature scaling well. So if you're dealing with things that don't fit a normal distribution, where your data is not distributed in something that sort of looks like this, the SGD variation of linear regression does not work very well at all. It'll give you really wacky results, and you'll be wondering why. So in order to use linear regression with MLlib in the implementation that they have chosen, you first need to scale your data down so that it fits this range more better. So you want to make sure your data isn't very large and it has a good distribution and it's centered around 0. Okay, so to do that, you often need to scale the data down because in the real world, very few measurements are actually in this range and in this distribution. So, big downside of using SGD. So you do need to scale that data down and then scale it back up again when you're done to restore it to the proper values that you want to display in the end. Also, a limitation is that it will default to assuming that your y-intercept on the linear model is 0. And if you want to actually support y-intercepts that are not 0, you need to explicitly say set intercept true on the algorithm model. So let's do it. So for the example we're going to do, I've fabricated some fake data that tries to find a relationship between page speed on a website and amount spent. So imagine we're running some big online e-commerce website and we're trying to figure out what's the relationship between the responsiveness of web pages and how much my customers spend. So let's try and build a model around that using some given data and see how well it predicts unknown data. Let's watch. All right, let's actually use linear regression in Spark using MLlib. So in the course materials, you'll find my data file, regression.txt, and you want to copy that into your course folder here, which I've already done. And if you examine the contents of that file, it looks like this. So it's just 2 columns separated by commas, and this turns out to be the format that MLlib expects for its input data, so it can read that in very simply. And this is just mapping simulated page speeds to amount spent. And again, I had to normalize this data down to a normal distribution range in order to get the algorithm to work properly. So you might say to yourself, wow, those are really small page speeds and really small amounts spent, but they've all been scaled down to fit into a range that the algorithm can handle. Again, big downside of SGD, but it's something you have to remember to do. Just scale it back up when you're done. So let's look at the code that actually runs it, and I've already imported that. So from the course materials, you'll want to import the linear regression.scala file into your project, which I've already done here, and take a look. So one thing I haven't talked about before is all the extra imports you have to do as well. So don't forget that. We are importing a bunch of specific MLlib classes that this script uses, including vectors, label, point, linear regression with SGD, and squared L2 updater that we all use inside here. So we set up our context as usual, load up our training data. So what we're going to do here deserves a little bit of explanation. So usually with supervised learning techniques like this, where you're training an algorithm given a bunch of known data and then applying that resulting model to unknown data, you do what's called training and testing. So to evaluate the model, you give it a set of training data where you know the answer already. You know the labels for each data point. So in this case, we're getting page speeds as one axis, and we're trying to predict amount spent as the y-axis. So amount spent is our label in this case. That's what we're trying to predict. And to evaluate the model, we're going to throw some more data at it where we actually know the result and we can compare the known result to what the model predicted. Okay, so that's what's called a train test. Normally, you train and test an algorithm using different slices of the data. So you wouldn't normally want to actually evaluate a model using the same data that you trained it on. But in this example, we're going to kind of pretend we never heard about that and actually use the same data for training and testing, just for simplicity. Now, in the real world, you wouldn't actually know the answers, so you wouldn't be able to actually evaluate the correctness of the final results. But same ideas apply. So to get this into MLlib, all we need to do is call labelPoint.parse on the training data and the test data, and that gives me back a RDD of labeled points based on that input file. Okay, so remember I had this comma-separated value 2-column data, and labelPoint.parse can automatically convert that into a labeled point object without any additional code. I am caching the training data because the algorithm may use it multiple times. Then I create my algorithm, linear regression with SGD. I set a bunch of parameters on it that I've tried a bunch on to find what works well. And then I run it, given the training data set. And at that point, I can create a model and use that to predict values on my test data. So what I've done here at this point, I've created a model that creates a linear model of the data that I gave it. I am now going to take that model and use it to predict values for just the page speeds of the test data. So what I'm going to get back are predictions that take the page speeds only from that test data, and then it makes predictions of the amount spent based on the linear model that we created. Okay. So what I want to do now is compare that predicted result to the actual result that was in that training data set. And that's what this next line does. It just zips in the known labels. See, testdata.map label. So that's extracting the actual answer that we got there and zipping it into our predicted results. So what I get back are these tuples of the predicted value and the actual value, so I can compare the two. And then I just go and print them all out. Make sense? All right. Let's do that. I already created a run configuration, nothing special about it, for a linear regression, and we'll run it. And there we go. So there you have it. here we have our predicted results using our linear model that we created and the actual results, and you can see they're generally fairly close. It's a relatively small data set, and there's a good deal of random variation, so you certainly shouldn't expect it to be perfect, but the results are pretty darn good. So it worked. Yay. Woohoo. Now remember, you'd have to scale these results back up again because we scaled them down for the algorithm. Well, that's an exercise for the reader, and you can try that if you want. But if you do want to get your hands dirty with this, I encourage you to do so. So let me challenge you. Take this script to the next level. Instead of just printing out these results, actually compute the total squared error among the entire data set. So as you're printing out each line, keep track of the difference between the predicted value and the actual value, and take the square and add it all together, and then divide that by how many data points you had. That will give you what's called the R-squared metric of just how good this model is in predicting new values. Okay, so that will give you a number with which you can evaluate how good this model is. And once you have that working, what you can do is try different values here for the optimizer here, number duration, step size, and reg param, and experiment with them. See what effect they have on the final results and whether it affects your R-squared score or not. So if you want to get down and dirty and get your hands on and actually write some MLlib code yourself and fiddle with it, there you have it. See if you can actually create a metric of how good your predictions are overall by keeping track of the squared error, and see what those values do to it. All right, so go play with that if you will, and I'll see you in the next lecture. So let's talk about using MLlib with datasets. This is kind of the new way of doing it in Spark 2.0. And going forward, MLlib is moving in this direction. They want you to use data frames or datasets as the input source whenever possible, and they actually have a separate API for this using the ML package instead of MLlib. But you can't always frame your problems in the terms of SQL queries or datasets. So the old API is still there, and it's still good to understand, but let's talk a little bit about the new API based on datasets. So it does perform better, that's why people are pushing you toward it, and it also lends itself to better interoperability. So not only MLlib is being pushed in the direction of datasets, but so is Spark Streaming, so is Spark itself, and so is Spark SQL, obviously. So if you want to be able to interoperate between these different systems within Spark, using datasets is a good way to hand data in between them if you want to. So again, you need Spark 2.0 or newer to use this, and if you're still using something earlier, then this isn't even available to you. But going forward, this is the way of the future. So it'll make more sense when we look at an actual example. Let's do our linear regression example again, but this time we're going to use the data frame-based API in MLlib and see how that works. So let's look, shall we? So let's go ahead and fiddle with MLlib's dataset API. We're going to do exactly the same problem that we did before, where we take that linear regression problem, where we have page speeds and amount spent data and try to fit a line to it. But we're going to do it in a different way. We're going to use the new MLlib dataset API instead. So you can see up here, we're actually importing the ml.regression.linearregression and ml.linalg.vectors classes. These are completely separate from the linear regression and vectors and labeled point stuff that we used before from the MLlib package. So important distinction. Before I get too far ahead of myself, I have gone ahead and imported the linear regression dataframe.scala script into my project here. So if you need to go take care of that and import that from the course materials you downloaded earlier in the course, please hit pause and go take care of that right now. And once you're ready to move on, let's talk about this code a little bit more. So we're going to start off like we always do, set our log level, but now instead of using a Spark context, we're going to use a Spark session. This is basically the API that we use in Spark 2.0 for doing dataset stuff and Spark SQL stuff. So the syntax here should look familiar from our Spark SQL lessons. We're going to call a builder to create a new Spark session with an app name of linear regression df, master of local star, and again, make sure that you comment this line out if you're not on Windows. This is a Windows-specific workaround for an issue in Spark 2.0, and you will need to make sure you have a C temp folder present on Windows. Get or create that session object, and now we have something we can work with. So again, our input data is not in a structured format, it's just a text file, so we first need to impart some structure upon it before we can create a data set out of it. So we're going to take the Spark context, the old school Spark context out of our Spark session and just call a text file on it to create a plain old RDD from our regression.txt data. And once we have that, we can call a map to actually give it some structure. So what we're going to do here is we're going to split it up based on commas. And this little syntax here with the underscore, it's basically a wildcard, so it's sort of a shortcut of saying, instead of saying, x arrow x dot split, you can just say underscore, and it means the same exact thing. So it means for whatever, each individual input coming into your map function, that's represented by the underscore character. So we're going to split that up based on commas. That creates a new RDD, that's comma delimited information. And then we're going to map that in turn to some structured data here. So we're going to extract the first and second columns, which represent the labels and the features of our input data. And the label will just be a double in the first column, and the features will be a dense vector of information, in this case a dense vector that only contains that one value. And this is just the format that MLlib expects. So if you're going to be dealing with this linear regression class in MLlib using data frames, this is the format it needs to be in. It's exactly the same format as a labeled point from MLlib, but you can't actually use labeled point from MLlib within the ML library. I think it's kind of a build issue that they had in Spark 2.0, so that might get cleared up at some point. But for now, we kind of have to create our label points the hard way by doing this. So at this point, we have a data RDD that contains two columns, doubles and vectors. So the double is the label and the vector is the feature data. And now we want to convert that to an actual data frame. Now, I have been kind of using data set and data frame interchangeably. I don't want you to get too confused by that. Remember, a data frame is a data set. It's just a data set of row objects. So, sometimes people talk about the dataset API of MLlib. Sometimes they talk about the data frame API. More often you hear about data frame because that's kind of the legacy terminology of Spark. But going forward, I think you'll hear about data sets more often. Anyhow, in this context, it doesn't really matter. We're just going to create a data frame from that data, and here's the syntax we're going to use to actually do that. So first we need to import spark.implicits to actually be able to infer the schema of our data RDD. So it's going to be able to peek inside there and say, oh, okay, I have a double and I have a dense vector of doubles. I can actually convert that to something structured and impart the correct types onto that. The other trick here is actually giving names to those columns. So in a data frame, you want to have names associated with those columns so we can actually do SQL queries on them and refer to them by name. And this is one way to do it. So before we used case classes to do this sort of a thing, but here's an alternative syntax. We can just create a sequence in Scala of the column names. So we know the first column is label, the second column is features. And then when we call df, we can pass in call names. And again, we have this wildcard character and a star. So that just means we're passing in a list of stuff, a sequence of stuff. Okay, in this case, it's going to be a sequence of column names. It happens to have two, so that will just map that sequence into the call names of this data frame. And at this point, we have a data frame object called df. All right. Now that we have that, we can actually pass that into MLlib. So let's do something a little bit fancier just to make life a little bit more interesting. If you're not familiar with machine learning, you'll get a little free lesson here. So one way you can evaluate the performance of a machine learning model is a technique called train test. And the idea is that you have a set of data where you have a set of known results. So in this case, we know the actual order amount in page speed for a set of data. What we're going to do is split that data in half randomly. So we're going to take half of that data and put it over here and reserve it for actually building our model. And the other half we're going to reserve for testing that model. So the idea is if you have a bunch of data and you randomly split it up, only use a certain percentage of it to actually create the model itself, you can then evaluate that model based on the other data that you held aside. And since the model had no knowledge of this other data when you were creating it, it's a good way to actually test how effective this model is at predicting data that it hasn't seen before. So that's what we're going to do. So we're going to call random split on the data frame, and we're going to say we want a 50-50 split, and that will give us back two data frames that we're going to call training df and test df. So it returns an array of two data frames. In this case, look at that. It's actually calling it a data set of row, which is equivalent to a data frame. And we're going to pluck out the first one and the second one, and we'll call one training df and one test df. And we're going to use that training df to actually build our model with. So we're creating a linear regression model using MLlib with a bunch of standard parameters here. We're going to call that LIR, linear regression. And then we're going to fit that model to the training data that we set aside. Okay, and that's going to be our model. So we have a linear regression model that we can now use to make predictions. So let's do that. What we're going to do here is take our linear regression model and call transform on it using our test data. So what this is going to do is add a prediction column to our test data frame. So our test data frame will now contain the labels that we know, the actual known page speeds or amount spent, the feature data, and the predicted data. So we can now compare the predictions to the actual known values and use that to evaluate our our model. So let's do that. Just like we did before, we're going to extract the predictions and labels, and it's actually a lot easier now that we're dealing with data frames. We can just do a select statement and say I want to pull out just the prediction and label columns. And then we're going to transform that to an RDD. That's just mapping those individual columns to doubles. So we end up with an RDD of 2 columns of doubles, the predictions and labels, and then we can just go through and print them one prediction at a time. When we're done, stop the session, and that's it. So let's see if it actually works. I actually already made a run configuration for it, so if you need to take care of that, go ahead and do that right now. And off it goes. Hey, you can see it actually worked. So these should be equivalent results to the earlier example, and you can see that the predictions and the known results are fairly close to each other. So that tells me that our model is actually pretty good. Now obviously there are more principled ways of actually quantitatively measuring how good that model is using things like R-squared or RMSE and stuff, but that's getting beyond the scope of this course. If you want to learn more, go take my data mining and machine learning course if you want to get more depth on that stuff. But there you have it. MLlib in action using the data frame API. So that's kind of the future of MLlib. Again, they're trying to tie all of the components of Spark together using datasets. So this is another step in that direction. If you can, think of your MLlib problem in terms of datasets or data frames. You should. It can perform better and will give you greater interoperability and compatibility with other systems. So there you have it. Linear regression using MLlib and data frames. Cool stuff. Let's talk about Spark Streaming, another technology built on top of Spark Core. Very exciting one, very powerful. The idea is that it can process streams of data as it comes in real time. So unlike the Spark jobs we've run up till now, that where you just run them and they're done, Spark Streaming jobs can run forever. Well, a long time anyway. So for example, let's say you have a fleet of web servers for a big website that you're responsible for. Those things are broadcasting log information all the time at a massive rate, right? Spark Streaming can actually let you throw a cluster at that, ingest that data as it comes in, transform it, keep totals of things as you go, maintain sessions, whatever you need to do, write it off to a database, anything, and actually keep up with it in real time. So it's not like a batch approach where you're taking all the data for a day and crunching it and getting a result. It's taking the data as it comes in and processing it as it comes in. Okay. So an example besides logs for a web server, maybe an Internet of Things application. You have a lot of sensors out there that are broadcasting sensor information at some massive scale. Spark Streaming might be a way to ingest all that information in real time and actually react to it quickly, as opposed to some daily batch that you might run. Now, Spark Streaming is a little bit different from something like, say, Apache Storm, in that it's not really streaming technically. What it really does is it breaks down that data into individual chunks that you process together as small RDDs, okay? So you're not actually processing data one byte at a time as it comes in, but you can process it, say, 1 second at a time. That's a more typical scenario. So technically speaking, Spark Streaming isn't really streaming. It's dealing with what we call micro batches, but for the vast majority of applications, the distinction doesn't matter. And you can configure Spark Streaming to talk to any variety of data sources. So you can just listen to a port that has a bunch of data being thrown at it and ingest it pretty easily. Or you can connect to other systems like Amazon Kinesis or Kafka or Flume or other technologies that are used to aggregate data and broadcast it, publish it on a network at a large scale. There are add-ons you can get for Spark Streaming to connect to all of these things and more. The other good thing about Spark Streaming is it's reliable. So it has a concept of checkpointing where it can actually store its state to disk periodically, and depending on what kind of receiver you're using and what kind of data source you're using, it might be able to pick up right where it left off in the case of failure. So it has a very robust mechanism for actually dealing with failures, and if a node goes down, if the whole system goes down, if it can recover from that. It can pick up where it left off and just keep on going, which is extremely important whenever you have a system that's running 24/7, right? It means you get woken up less often at night for random problems. So just like Spark SQL had the concept of a data frame built on top of an RDD, Spark Streaming gives you the concept of a D stream. And basically this is a collection of RDDs that embodies the entire stream of data. The cool thing is that you can actually apply a lot of the same functions to RDDs to D streams. So you can say things like flatmap to a D stream and just have this mapping operation happening all the time as this data comes in. But you can also break that D stream down into its individual RDDs and process the results one chunk at a time when you're done. Let's see how that works. So, just setting things up, basically you set up a streaming context instead of a normal Spark context, and you pass in how frequent you want the batches to be. So this is saying I want to create a streaming context that processes data 1 second at a time. I can then connect that to a socket. Let's say I want to listen to port 8888 on my own computer and just listen to any data that's coming in on that port as a simple example. And what I could do is just filter that for anything that contains the word error. Let's imagine that it's Apache log messages or something, and I'm interested in error lines, and I want to print those out. So these 4 lines of code is all it would pretty much take to listen to a stream of log data that's being broadcast on some TCP port and print out any error messages that come up. Okay, and well, it's a little bit more than those 4 lines. You also need to start the actual process and wait for its termination when you're done, but yeah, whatever. All right, so if you want to aggregate data, you can do that too. You don't have to deal with 1 second at a time. You can actually add things up over time too, and that's where windowed operations come in. So there's operations like window and reduce by key in window that you can use to actually aggregate over a larger period of time. So say you want some moving total over time. Say you want to get the most popular thing purchased over the past 24 hours. You could set up, for example, a window of 24 hours and say, I want to aggregate information over that time period. So that's going to be updated with each batch that comes in, which might be a much shorter time period, like 1 second, but keep track of things over the past, hour, 24 hours, whatever you need to do. So Spark Streaming makes that very easy to do. It also lets you maintain state associated with a given key that is persistent. So for a good example is web sessions. Let's say that you identify a session by an IP address over some period of time, like 20 minutes from the same IP address is defined to be a session. You can actually define a session object that gets associated with that key over time and automatically gets expired after a certain period. So let's just look at a simple example. Spark Streaming is a very big topic in and of itself. I actually have a whole course on it. So if you want to learn more, watch the bonus lecture at the end and I'll tell you more about that. But let's start with a simple example that is kind of a fun one. What we're going to do is connect to Twitter and actually listen to live tweets in real time. And we'll keep track of the most popular hashtag as we go. So let's talk about how that works. So the first thing we need to do is to get a Twitter developer account. We can't actually connect to Twitter data without registering ourselves with Twitter, but fortunately that's pretty easy to do. You just need to go to apps.twitter.com, give them some basic information about yourself, and it will give you back the authentication tokens that you need. So I'll walk you through all this when we actually run this interactively. And if you're not comfortable giving your information to Twitter or you don't have a Twitter account, fine, just watch me do it. But it is a fun thing to run and actually run yourself. So once we get that, we're going to just put that information in a twitter.txt file, and we're going to write some code to parse that in and actually set up our Twitter receiver to connect to Twitter directly using this authentication information. After that, we get into the meat of the script itself. So what we're going to do is create a stream, and there's a Twitter utils function in the examples of Spark that we can use to do that. So that's going to give us back a D stream of tweets. We are going to map that to just extract the text field. So every tweet is like this structured piece of data that contains the text of the tweet itself, who sent it, where it was sent from, and all sorts of other stuff. All we care about is the actual text. So we're going to extract the text and put that into a new D stream called statuses. So let's imagine that people are talking about Bodie McBoatface. It's kind of a silly example, but if you don't remember it, this was like an internet thing a while ago. Basically, some navy somewhere in Europe held an online contest to name their new ship. And of course, the internet being what it is, came up with a bunch of goofy stuff, and the winner ended up being the name Bodie McBoatface. And of course, Twitter was all a Twitter about this at the time. So let's imagine that people are talking about Bodie McBoatface. So we have 4 tweets that come in. Vote for Bodie McBoatface, vote for I like big boats and I cannot lie, which was also on the top results. What iceberg or Bodie McBoatface all the way. So we're going to look for the most popular hashtag that we run across. So at this point, our statuses, our D stream contains this information, the text of each tweet, one on each entry of the D stream. Okay, so now we're going to split that up into individual words. So we're going to just call flatmap on that, and it works just like with an RDD, and we can just pass in this little lambda function to split it up based on spaces. Obviously, you can do something more fancy if you want, like we talked about before. So now we're going to get this new D stream that contains every word of every tweet that comes in. Vote for Bodie McBoatface, vote for. But all we care about are the hashtags, right? So we need to then filter out anything that's not a hashtag. And to filter things out, we use the filter function. So we're going to pass a filter function of word has to start with a hash sign. And if so, it will survive into our new hashtags D stream. So at this stage, we have a D stream that just contains hashtags. And Bodie McBoatface, what iceberg, Bodie McBoatface, etc. All right, now we can convert that into key value pairs, so we can actually count them up. We've used this trick before, so we're just going to map that to tuples, key values of the hashtag itself and the number 1, so that when we add all this up and reduce it, we get to count up all those ones to get the grand total of how many times each one occurred. All right, now how do we do this over a given period of time? Like, we don't want this to keep track of things forever, but that's where windows come in. So we're going to do reduce by key and window, okay? So this is your usual, there's something a little bit extra here. So when we're doing reduce by key and window, to make things more efficient, you want to pass in a function not only on how to combine things together, but also how to remove things, because it needs to take things off as they expire, right? So that makes it a little more efficient. You can actually do it without doing both of those functions, but it's faster if you do it this way. So we're passing in a function for combining things, for removing things, the window time, which is going to be 5 minutes, and the batch and the slide time, 1 second. So basically every 1 second it will update a new result over the past 5 minutes, if that makes sense. And what we end up with is Bodie McBoatface is in the lead with 2 and What Iceberg has 1 in our example here. Finally, we can just sort and output the results. So we're just going to sort by the count, which is in the second element, and print them out. And that's what we end up with. And this thing will just chug along forever, keeping track of the most popular hashtags as it runs over the past 5 minutes. So let's actually run it, see what happens. So let's see Spark streaming in action. So again, for this example, what we're going to do is listen to Twitter tweets in real time and keep track of the most popular hashtags that we encounter over a 5-minute sliding window. Now to do this, first we need to set up a developer account with Twitter so that we can actually connect our Spark streaming application to the Twitter API. And this doesn't take long, so all you need to do is go to apps.twitter.com, https apps.twitter.com, and you should see a screen like this. Go ahead and sign in with your Twitter account. If you don't have one, that's okay. You can just follow along and watch me. And I already have an app defined here for the work I've been doing, but you'll want to create a new app. And you can call it whatever you want. Spark, Scala, course, I don't know. And messing around with Spark streaming. And you need to put something in for the website. I happen to own one, so I'll put my website in there. Put whatever you want in there. Callback URL can be left empty. Read through the developer agreement. Make sure you don't object to anything, assuming you're cool with it. Hit I agree and create your Twitter application. All right, but we're not quite done yet. Now we need to click on keys and access tokens. These are the credentials that we need in order to actually connect. So let's click on that. And we want to create an access token as well as our consumer key. All right, so now we have all the information that we need. We have a consumer key and a consumer secret, and we have an access token and an access token secret. So these are the credentials you will need in order to connect to Twitter. So leave that information up where you can get at it easily. And if you go to the directory where you downloaded the course materials, for me that's download Spark Scala, you should find a twitter.txt file. And if you open that up, it should look a little something like this. So what you want to do is copy and paste the keys that you just got into this file. So for consumer key, for example, I would copy that, paste it next to that. Make sure there is one space between consumer key and the token itself, no extra spaces at the end or anything. You want to keep on doing this for the other credentials. Of course, yours will be different, and don't try using mine because I'm going to delete this account when I'm done. Access token. This is a longer one, has a dash in it, so copying it is a little bit trickier, but I'm sure you can handle it. And the access token secret. So you should end up with a file that looks like this. Make sure that you have a return at the end of that final line, and make sure there's no extra spaces, no extra returns or anything like that that might mess up this file. Once you're happy with it, save it. And it should look like that, of course, with your own tokens. All right, now we need to take that file and copy it into your course folder. I've already done that with my own tokens here. So at this point in the course, your Spark Scala folder should look something like this. And now we can just go ahead and take a look at our script. So let's spark up the Scala IDE. So next thing we need to do is import some libraries for Scala and Spark that will let it actually talk to Twitter. Now, if you were using something before Spark 2.0, that capability is just built into Spark itself, but they actually removed it in Spark 2.0. So if you are using Spark 2.0 or newer, you have to do this next step first. So go over to the Spark Scala course project in the IDE, right-click on it, and click on Properties, and click on Java Build Path. What we're going to do is hit Add External Jars, and I've provided the jars you need as part of the course materials. So if you go to where you downloaded the course materials, for me that's the Spark Scala folder in my Downloads folder, you should see these 3 jars. There's dstream Twitter, Twitter for JCore, and Twitter for JStream. And these are the libraries you need in order to get Spark Streaming to talk to Twitter. So go ahead and select all of those and hit Open, and hit OK. And now we can import the script itself. So click on the package there, right click, import from the file system. Again, we'll choose the directory we downloaded the course materials into, and we want to import the popular hashtags.scala file. All right, go ahead and open that up and we'll take a look at it. So let's take a look at what's going on in here. We reviewed a lot of this in the slides, so we'll just go over it quickly again. Basically, we're importing all the stuff we need, including a bunch of Spark Streaming classes and the Spark Streaming Twitter example as well. So that allows us to connect to Twitter and use Twitter as a Spark Streaming receiver. All right, we made a little function here to set the log level to error level, and here is where we actually load that twitter.txt file that you just created. And we parse it out one line at a time, split it based on that space character, and just set system properties based on those settings. So assuming you formatted that file correctly, that should set up all the system properties needed to actually connect to Twitter successfully. So that's the first thing we do in our main function. We set up those credentials for Twitter, and then we get into the meat of Spark Streaming itself. So note here, we are creating a streaming context as opposed to just a plain old Spark context. And we are setting this up to run locally on every core. We're calling it popular hashtags. And this third parameter indicates the batch size. So we're going to say we want to get information to process every second. And we're going to process information 1 second at a time. Okay. Moving on. We'll call the Twitter utils class to actually create a receiver that listens to a stream of tweets. So that's what Twitter utils create stream does, given our streaming context. And we now have a dstream called tweets that we can work with. All right, next thing we need to do is extract the actual text from each tweet as it comes in, and we don't want all the other information that comes along with each tweet, like who said it or where it was sent from and all that garbage. So we just do a simple map here that gives us back yet another dstream. So look at, it's important to note that we're actually operating on dstreams here. This is on top of an RDD, so we're actually saying we want you to do this mapping of extracting the text from each tweet on every single bit of information that comes in continuously. All right, so we're not dealing with individual little RDDs here. We're dealing with the dstream as a whole, which is kind of cool. And keeping on with that, we're going to apply a flatmap to that to actually bust those tweets out into individual words, broken up by spaces. Obviously, there's more robust ways of doing that, but that will meet our purposes for now. And we're still dealing with dstreams at this point. So at this point, we have a dstream of strings. That's just a big old bag of words. Next thing we want to do is filter out anything that's not a hashtag. So with this little function here, we're going to say unless an individual word starts with a pound character, we're going to throw it away from our filter function. So we're applying filter to our dstream now, and the resulting dstream is now just a dstream of all the hashtags that have come in. All right, now we're going to transform that. We're going to do our little trick of transforming that to a key value pair where the value is 1, so we can do a reduce operation to count them all up. So now we have hashtag key values where we have a dstream of key value pairs of individual hashtags in the number 1, and then reduce by key and window will add them all up. So what we're saying here, this deserves a little bit more explanation. This is kind of the meat of Spark Streaming here, and what we're doing. By taking that dstream and calling reduce by key and window, we're saying we want to combine together all of the information in that dstream over a sliding window. And in this case, it's a sliding window of 300 seconds, which is 5 minutes. And we're going to slide the window every 1 second. So every 1 second, we're going to look back 5 minutes and return the result of all of the summed up hashtags for each hashtag. So we have a pretty standard reduction function here. We're saying given 2 values, we combine them together by adding them. And reduce by key and window optionally takes a second function for how to remove something from it. So we also pass that in as well. If you want to remove y from x, we just say x minus y. You don't have to do that, but it does allow Spark to optimize things a little bit better, because with that sliding window, sometimes we have to take stuff out as well as add stuff in. Okay, so at this point we have a hashtag counts, and we're still dealing with the D stream here that maps hashtags to their count over a sliding 5-minute window that's updated every 1 second. All right, so that's how Spark streaming works. Finally, we'll call transform on that to retrieve a D stream that just sorts the results, so we end up with the most popular hashtags on front and print out the top 10 results. That's all that print does. All right, we set a checkpoint directory. This is important for actually being able to restart the job if it fails. And we start it and wait for it to terminate. So let's see if it works. I already created a run configuration for it, so there's nothing special about it. We just called it popular hashtags, put in the main class name here, and we can run it. And I don't have any control over what people write on Twitter, so there could be some naughty words here, just to warn you. So as the time of I'm writing this course, the Republican National Convention is going on, so we're seeing a bunch of political stuff go by, but actually it's getting drowned out pretty quickly by some other stuff. Let's blow this up a little bit. So this is pretty awesome. Like, what I'm seeing here is a running total of the most popular hashtags over the last 5 minutes. Now, I haven't actually run this for 5 minutes yet, so I'm just kind of like aggregating results as I go at this point. But right now, something's going on with MTV apparently, and MTV Hottest seems to be trending as a very popular hashtag right now. Welcome GOT7 to Thailand. I don't know, some gaming thing, I guess. I'm just not with the times these days. And you can see things are really starting to stabilize. MTV Hottest is in the clear lead right now. And if you're running this at home, be interesting to see what else you're seeing. I'm sure it's completely different. Another thing that I always find fascinating too is that English isn't as predominant as you might think, right? I mean, I know I have an international audience here, so maybe it's not a surprise, but in a kind of US-centric view that we tend to let ourselves be immersed in here in the United States, that can come as a little bit of a awakening. I mean, there's definitely languages I don't even recognize here. What is that? I think that's Korean, but I'm not even sure, to be honest. But it's pretty cool. You know, I mean, Twitter is a global community, and streaming popular hashtags won't necessarily give you results that are in English. And hopefully, whatever that says in whatever language it is nothing offensive. And there you have it. But that's pretty awesome, isn't it? I mean, I could let this run all day, literally. And it would just keep giving me a running total of the hottest hashtags in the past 5 minutes. So that's pretty cool stuff. And if I didn't want to print it, I could like store it out to a database, send it to some other service, send it to a website. Who knows? The possibilities are endless. So that's Spark streaming for you. It's pretty powerful stuff, and I can get pretty excited about it. Good application of Spark. So, you know, if you are dealing with continuous streams of data as opposed to dealing with batches of data, you know, at the end of the day or whatnot, Spark streaming could be for you. You might want to learn more about it. All right, with that, let's move on and talk about graphics. Just hit terminate here when you're done, and we can close out of it. So that's Spark streaming in action with a pretty fun example, keeping track of the hottest hashtags in real time from Twitter. So if you want to get your hands on and get down and dirty and get some more practice with Spark streaming, I encourage you to fiddle with that script and make it do something else. So here's a couple of ideas for you. What if you kept track of the most popular word tweeted in general? Don't just look at the hashtags, look at everything. That's a pretty simple modification to make and give you some confidence in just getting in there and making some changes. After that, try something a little bit more challenging. Why don't you try to keep track of the average length of a tweet that comes through, or the most popular tweet length. A little bit simpler there. Also, a little exercise you can do with the same kind of framework there. Lots of things you can do with tweets there. So get in there and get creative and actually make some changes to that script and make it do something interesting and learn something new about what people are tweeting about. So go have at it, have some fun with it, and I'll see you in the next lecture. So that's Spark streaming, sort of the legacy implementation. Going forward in Spark 2.0, they've introduced a new API called structured streaming in addition to the standard API. So let's talk about that a little bit because it's the way of the future with Spark streaming. Now, like with the rest of Spark, they're pushing you toward using data sets for an API on Spark streaming, just like they're doing with MLlib and GraphX and Spark SQL. They really want you to start using these higher level APIs because it gives Spark more of an opportunity to optimize things under the hood. So if you can think of your streaming job as a database problem, it's sort of a SQL problem, this can be a good way to do it. Now, it is still an experimental status in Spark 2.0, so I wouldn't go using it in production just yet. It still has very limited functionality, and it's not recommended for production use quite yet, but it will evolve quickly, and in Spark 2.1, that should all change. So how does it work? Well, imagine a data set that just keeps getting appended to forever. So you have a data set, which is basically a database, a very simple columnar data format, basically an RDD that goes on forever. And if you just keep appending data to that, that's very much like streaming data. It's very much like a D stream, right? So instead of like little chunks of RDDs being added to a D stream, instead we have rows of data being added to a data set. So same idea, just thinking about it a little bit differently. From a code standpoint, this is how it looks, and it's actually pretty neat. So once you have a Spark session object, just like you would create for any Spark SQL application, you can call read stream instead of read. So let's say that you have a bunch of structured JSON data going into a big S3 folder, like S3 logs is the name of the bucket, let's say. You can actually call read stream to just sit there and listen for new log files being added into that directory. And since it's in a structured format, a JSON format, it can import that directly into a data frame and understand its schema and the type associated with that data. So this is exactly the same code that you would write to do a non-streaming application, except instead of read, we're doing read stream. Okay, so it's very easy to convert a non-streaming application to a streaming application using the structured streaming API if you're using data frames. And once you have that data frame in place, it's just getting appended to over and over and over again. You can say things like this. I can say input df.group by. So let's say there's an action field and I just want to add up all the different action types that occur within a 1 hour window. That's what this does. So I can actually say group all the action codes together, have a 1 hour sliding window, and count them all up every hour. And I can actually keep writing that data out to a JDBC database at a given path, and that will automatically do the right thing. So a couple of things worth mentioning here. First of all, we can actually specify what column we want to order things by. So unlike with a D stream where Spark Streaming is kind of deciding what goes into each individual RDD that gets added to the D stream, you can say, I want to actually add things in order as they come in based on a column in a data frame. So, if you have a column in your data frame that's like hit time or, order time or something like that, you can use that and actually do your window based on that explicit column, and then you can get a guarantee that things will be processed in the correct order. So that's kind of a powerful thing. Also, it can automatically keep track of what's come in, what's changed, what's new, what's different. So this is going to keep appending to your database all the changes that come in, and it can keep track of fault tolerance and all that stuff for you. So it's a very simple API, but it belittles its complexity under the hood. So it makes it very easy to write what they call continuous applications. That's kind of the new terminology for a Spark streaming script, continuous applications, where the idea is you can take a data frame-based application, just change a read to a read stream, add a couple of lines at the end of the code to kick off that stream and keep monitoring it, and you're done. You have a continuous application instead of a batch application. So that's structured streaming in the way of the future. Let's talk about one more piece of technology built on top of Spark Core, GraphX. Pretty powerful thing. Now, we're not talking about graphs in the sense of, charts and lines and stuff like that. These are graphs in the computer science sense. Things like social networks. So if you think back to the example we did of a superhero social network, we're going to come back to that throughout this lecture. That's an example of the graph we're talking about. It consists of vertices, where each vertex in this case would consist of an individual superhero. And there are many superheroes in this graph connected by edges that represent relationships between given superheroes that appeared together in the same comic books. Now, GraphX is mostly useful for giving you sort of high-level information about a graph. So for a social network, it can tell you things like how many triangles appear in the graph in connections, how connected is the graph as a whole, what are the degree distributions, the average path length, things like that. It also has some very highly specialized functions in it for doing things like applying the PageRank algorithm to a graph. And it can join different graphs together quickly and apply transformations to an entire graph all at once. Mostly it gives you a way of actually representing a graph in a structured way, where we have a graph object that consists of vertex RDDs specifically, and edge RDDs that connect these vertices together. So for things that are more specialized, like what we did with computing the degrees of separation between superheroes, it's not going to give you a function to just do that. You have to do that kind of the hard way. But it provides a framework that lets you do those sorts of operations a little bit more simply than the way we did it before, and that's called Pregel. We'll talk about that more in a little bit, but it's basically an algorithm that you can apply to a graph that defines how you iterate through it and branch out as you explore a graph in any way that you want to. So like I said, it introduces a couple of new data types, the vertex RDD, the edge RDD, and a vertex and an edge. So Vertex, again, just an individual node in your graph. Edge is a connection between two nodes, and a graph is constructed by passing in an RDD of vertices and an RDD of edges that connect these vertices together. So an edge just consists of two vertex IDs that an edge connects, and a vertex is just a vertex ID and whatever data you want to associate with that vertex. Apart from that, there's nothing really special from a syntactical standpoint. In fact, when you're creating a vertex RDD, you're not really seeing a whole lot of GraphX specific stuff here at all. The only thing that stands out here is the vertex ID type here. So what we're going to pass into flatmap as we're creating our vertex RDD from the source data is a tuple of vertex IDs and strings, which in this case is just mapping superhero IDs to their names. So this is an example of where we're actually going to go through the marvelnames.txt file and create a list of vertices from every superhero in that file. So all we do is split it up, extract the superhero ID, and that will be our vertex ID. A little example here of cleaning the data, which is always important. We happen to know that everything above 6486 are actually bogus characters in that data file. They don't show up in the data at all, so we're just going to discard them. But if the superhero ID is valid, we will return the superhero ID converted to a long, which is the same thing as a vertex ID, and the superhero name. So this is returning a sum instance that indicates that we actually have a result of the superhero ID converted to a vertex ID and the superhero name. And if it is an invalid entry, we return none, and flatmap will just ignore that entry. Now for making the edges, not much more complicated here. In this case, we're going to go through the actual Marvel data here for the actual connections. And if you remember, each line of input here is the superhero ID followed by a list of the superhero IDs of all their connections. So what we return here is actually a list of edge objects, and these edges are wrapping integer types that are just the superhero IDs themselves. So given a line of input, we create a list buffer so we can build up multiple edges, because we're going to end up with an edge for every single connection between that ID and every character that they appeared with, right? We split it up, extract the hero ID that we're talking about, and then we create a new edge for every connection in that line of input. So the new edge is created with the hero ID in the first position, and then with every subsequent hero ID that they are connected with. We build up that list buffer, convert it to a list, and return it back to flatmap, and we end up with a edge RDD in the end. Putting it all together, load up our marvelnames.txt file, call flatmap with parse name, so we get back our vertex RDD that contains all the superheroes that we know about. We will then load up the social graph itself and construct edges based on that information. So now we have an edge RDD. And to create our graph, all we need to do is call a graph with a vertex RDD, an edge RDD, a default case for in the instance where we have an edge that points to an undefined vertex. So in that case, we'll just call that hero nobody. And we're going to cache that because we're going to do a bunch of stuff with it. So that's all there is to actually creating a graph in GraphX. So once we have that graph constructed, we can do cool stuff with it. So for example, let's say we want to find the top 10 most connected superheroes. That's actually pretty easy to do. You can just call graph.degrees, and that will give you back a vertex RDD that contains all of the degrees of connectedness. Okay, so all the actual, how many lines are actually emanating from every individual vertex. And we might want to join that back with the vertices themselves so we can actually print out their names. And then it's just a matter of sorting them, taking the top 10 and printing them out. So that's an actual line of code that would print out the top 10 most connected superheroes given that graph that we just created. Pretty cool stuff. One line of code, that's all it takes. But what about doing breadth first search? So at this point, you might want to go back and rewatch that lecture about doing breadth first search using Spark the hard way. It goes through the algorithm a little bit more deeply. But if you remember, ultimately we're iterating through this graph from some given starting point. So let's say we wanted to measure the degrees of separation from Spider-Man to some other superhero. We're going to start with Spider-Man and iterate through that graph, expanding it out one step at a time until we find the person we're looking for, and we'll keep track of how many steps it took to get there over time. Now with Pregel, that gives us a general algorithm for actually doing iterations through a graph in a general manner. And we can actually implement breadth first search using the Pregel algorithm in a little bit more of a simple way than we did before. So let's take a look at how that works. So Pregel is just a general purpose mechanism for walking through a graph and doing stuff as you go. So it's very extensible into different problems. At a high level, the way it works is every vertex sends a message to other vertices, their neighbors, the ones that they're connected to, through edges. And this happens in iterations that are called supersteps in Pregel. And through each superstep, the following three things can happen. Messages from the previous iteration are received by each vertex. Each vertex can then run a program to transform itself, and then each vertex can send messages to other vertices for the next stage, for the next superstep. Okay, so basically, a superstep consists of receiving messages from other vertices, doing some sort of processing on the vertex, and then sending out messages to new vertices. And it does this over and over and over again until you say you're done. So how do we apply this to breadth first search? Well, first we create our initial state. So given that graph, what we're going to do is call map vertices on it. And this is another GraphX function that lets you transform an entire graph at once. And all we're going to do is say, for a given ID, if it's equal to the root, Spider-Man, say, the person we're trying to measure degrees of connection from, we will set the property of that vertex, the value, to 0. Otherwise, we'll set it to positive infinity. So this is the initial state, if you recall. We start off with the person that we're starting from with a distance of 0, while everyone else has a distance of infinity. And then we can kick off Pregel to actually do the iterations. So what do we do at each stage? Well, first thing we do is we have to figure out what messages we're going to send from each vertex. So this is the function that actually sends the messages off. And what it does is it says, well, as long as I have an actual value, I'm going to go and call all my neighbors with that value plus 1. Otherwise, I'll do nothing. So in the case where I have a white node that still has an infinite distance, we're going to ignore those ones. But if I have a value that I haven't dealt with yet, I haven't actually walked to this point yet, what I'm going to do, increment that attribute by 1 and send that to the neighbors. Okay, so we're doing the same thing that we did before, just using the Pregel construct. We also need to preserve the minimum distance as we go. So if you recall, there's often multiple ways to get to a given node, and we want to make sure that we're preserving the shortest path. And in this example, we're doing that in two ways. The vertex program is actually making sure that if we receive a message and we already have a distance in our node, we're going to preserve the minimum attribute, the minimum distance. Okay, so if someone's trying to send me a distance and I already have a distance that's lower than that, I'm going to keep the lower one. And also, we have a reduce operation that we specify in Pregel for the case of multiple things hitting a node at once. And in that case, we will specify a reduce operation that says we want to preserve the minimum distance being sent to me in the event that I have more than one. So how does that actually look in code? Well, it looks like this. Pretty simple. So we have that initial state where we set up everything with an initial value of positive infinity for the distance and 0 for the one we're starting with. We say here that we're going to take the minimum of the distances that are sent to us. Our function here will send off messages to our neighbors with the distance incremented by 1. And if we receive more than one message at once, we will preserve the minimum 1. Okay, so that's it. All you do is call Pregel on the graph itself. And these parameters mean this is the initial message being sent to positive infinity, the maximum number of iterations I want to run, so we'll give up after 10 iterations. And we just pass it in 3 functions that are the reduce operation, what we do when we receive a message, and how we actually send off messages to other vertices each step. So that will automatically do the iteration for us, and that actually implements breadth first search in a much more compact way than we did before. So let's do it. Let's actually see if it works. All right, let's go ahead and run this bad boy. So again, we're going to use GraphX to analyze the superhero social graph that we've used earlier in the course. And we're going to take examples of actually constructing a graph in GraphX using that social network of superheroes. And we're going to analyze that graph by finding the top connected people in the graph. And we're going to use Pregel to do breadth first search on the graph and find the degrees of connectedness between Spider-Man and everybody else in the graph all at once. Let's see how it works. So I've already imported the graphx.scala file from the course materials into my project here in the Scala IDE. Let's walk through it quickly again. We went through this in the slides earlier, but sometimes it just seems a little bit more real when you actually see it in an editor, doesn't it? So I've imported some stuff that we've imported before. I'm importing GraphX as well here, so all of the GraphX libraries are available to me. We talked about these functions that we're going to be using with flatmap to create a vertex RDD and an edge RDD that together make up our graph. So let's start with the vertex RDD. What we're going to do is pass in the marvelnames.txt file into here, which is just a text file of superhero IDs and their names separated by white space, by quotes actually. So let's split that out. We will convert the ID to a long, which can then in turn be converted to a vertex ID for GraphX. Okay, so vertex ID is the same thing as a long. And then we'll just associate the name as the data associated with that vertex. Okay, so we're just going to go through it one line at a time, and if we see a valid superhero ID, we will return a vertex ID string tuple. Otherwise, we return none, okay? Because there are instances of invalid data in here. Like I said in the slides, turns out the superhero IDs over 6486 don't really exist, so we can just throw them all away. Now, creating the edge RDD isn't much harder. We just go through the actual marvelgraph.txt file where we have the actual connections, and again, the format of that is a given superhero ID followed by all the IDs of that superhero's connections. So all we do is we build up a list buffer of edges, where the edges are defined by integer vertex IDs, split up the input line, extract the superhero that we're talking about from the first field, and then create a new edge for every subsequent field between that superhero ID and that connection. So we build up this list of edges that we convert to an actual Scala list to flatmap, and that gives us back a bunch of edge objects created from each line of input data from marvelgraph.txt. Putting it all together, we'll create our vertex RDD using parse names. We'll create our edge RDD using make edges, using all the code we just talked about, and then we'll make a graph out of it. So we construct a graph out of our vertex RDD, our edge RDD, pass it in a default case for edges that don't point to anything in particular, and we're going to cache that graph because we're going to use it more than once. So let's actually see if this code that we talked about in the slides actually works. First thing we're going to do, we're going to print out the top 10 most connected superheroes. Let's see what we get. So all we have to do there is call graph.degrees, and that will give us back an RDD of all the number of edge connections to every individual vertex. We'll join that with the vertex data itself so we can get back the actual names associated with each vertex. Otherwise, we'll just get a list of vertex IDs, and that's not very interesting. Sort it by the actual count of degrees connectedness. Take the top 10 and print them out. Okay. Next, we're going to do what we did before with the degrees of separation from Spider-Man, but this time we're actually going to do it for the entire graph all at once. So first thing we're going to do is say we're going to start with character ID 5306, who is Spider-Man. We're going to set up an initial state of our graph where we call map vertices to actually check whether you are Spider-Man or not. If you are Spider-Man, then your vertex attribute will be set to 0. Otherwise, your attribute, which represents the distance from Spider-Man, will be set to infinity initially. And now, here's where things get a little bit complicated with Pregel. So we're going to use the Pregel algorithm to actually iterate through the graph and measure the degrees of separation between each character from Spider-Man. So Pregel gets set up with, first of all, an initial message. So the initial state is going to be infinity distance coming into everything, and a maximum number of iterations of 10. So with that out of the way, we pass in 3 functions. The first function is our vertex program, and this is going to say that as a message is received, we're going to preserve the minimum distance between the incoming message and what we already have. Okay, so that just preserves the shortest distance as we iterate through. We have a function that will send messages to all the neighboring vertices. So in the case where we have an actual number in a node that we haven't explored yet or haven't traversed yet, we will send off a message to all of the neighbors with that distance plus 1. So this just propagates out the distance as we go from each superstep to each superstep. Otherwise, if this is a node that already has infinity in it, meaning that it hasn't been touched yet and is white in the parlance of our coloring terminology, we'll do nothing at this point. Finally, the reduce operation will preserve the minimum of the messages coming into a node if more than one is received. So if we're getting conflicting information about the distance at once, we'll preserve the shortest distance in that case as well. And that's all it takes. So with that, we can actually kick off Pregel. We're going to actually cache the final results of that operation. Okay, we're going to end up with a BFS object here that we can then play with. So we can just say bfs.vertices, and that will get back the end results of that Pregel traversal. And what we'll end up with is vertices that contain as values the actual degrees of separation from Spider-Man when we're done. All we have to do is join that with the vertices again, so we can just get the names back in there, and we can take the first 100 results, whatever they might be, and print them out. So we can sort of explore the data there and see if it's working. And finally, just to recreate the results of our earlier example in the course, we'll look specifically for the character Adam 3031 and make sure that we actually get a degrees of separation of 2 from Spider-Man, which is what we saw earlier. So let's go ahead and print this and kick this off I already created a run configuration for this GraphX. Hit run, and you'll be surprised at how quickly it actually goes. All right, we've already constructed the graph and we're done already. I mean, that's kind of impressive, actually. So let's take a look at what we got. All right, so we chugged away, we constructed our graph, and pretty quickly we came back with our top 10 most connected superheroes. The first result was Captain America, just like we found before. And the way to interpret this is the vertex ID, and what we're getting back is the total number of connections followed by the character name here. So this is the actual degrees result here, the number of edges pointing to that vertex. And number 2 turns out to be Spider-Man, followed by Iron Man, The Thing, Wolverine, so on and so forth. All the people you'd expect, although a little surprised to see Scarlet Witch showing up there. I never heard of her before. Maybe there's a good chance we'll see a new Marvel superhero movie about that person at some point. And then we ran the Pregel algorithm to actually execute breadth first search from Spider-Man to everyone in the entire graph and keep track of their distance. So that's kind of cool. And you can see, just kind of skimming through the data, that that whole 6 degrees of separation thing, well, in reality, it's a much lower number than 6. Pretty much everyone is 1 or 2 degrees from Spider-Man, it turns out. If you get into some really obscure people, you can find maybe a 3 if you're lucky. Let's see. I thought I saw a 3 in here. Yeah, Goom. Goom is 3 degrees, so I have no idea who Goom is. Kind of a cool name, though. And some people just aren't connected at all, like Marvel Boy 2 and Fagin. I mean, odds are they're not connected to much of anybody. And just to check our results, we did a filter looking specifically for Adam 3031, and sure enough, that character is 2 degrees from Spider-Man, just like we found before. So hey, it works. That's GraphX in action. So actually did a lot more than we did before with a lot less code. So it's an example of the power of GraphX in analyzing a social graph, and actually using Pregel to do a more complex algorithm where we're iterating through that graph one step at a time. Breadth first search just being one example of what you can do with Pregel. So there you have it, GraphX in action. All right, so that's pretty much some of the most complicated stuff you can do with Spark there. We've walked through it all, and we've done some examples here. As usual, I encourage you to fiddle with this if you wish. Print out the results in a different way. Maybe sort this breadth first search results to actually see who the most and least connected people are to Spider-Man and print them out in order. That might be a fun little thing to try out. But otherwise, hey, you've made it. That's Spark and all of its associated technologies for you. So let's move on and talk about how to learn more if you're so inclined. So congratulations, you made it through this course. Give yourself a pat on the back. That's kind of a big accomplishment. This is not easy stuff. And hopefully you've come through this having learned some very valuable new skills. You now know how to do big data using the latest and greatest technology too through Apache Spark. So these are highly desirable and highly marketable skills, and will let you process streams of data and big data sets that you couldn't do otherwise. So it's very powerful stuff. Now, if you do want to learn more, there's obviously stuff that I didn't cover in this course. So if you want to go into more depth, there are ways to do that. Here are some books that I've found useful in learning this stuff myself, and I don't get any money or kickbacks from this or anything. They're just books that I've found useful. One is the O'Reilly book called Learning Spark. And I'm generally a fan of O'Reilly books in general. Most of them are pretty darn good. And this is actually a really good one covering all the basics. So if you do want to reinforce what's in this course with a book, want to have something in writing, this is a good source to have. It's also written by the guys from Databricks, and those are the same people that run the certification program for Spark. So if getting certification is important to you, then you'll definitely want to review this book because this is what's on the exam. Certification, kind of a polarizing topic. As an employer, I never really put any faith or importance to certifications myself, but I do know some industries are different and some countries are different. So if getting certified is important to you, you will definitely want to pick up Learning Spark. If you want to learn more about Scala and the Scala programming language, we only really touched on some of what that language can do. There's a lot of advanced stuff, especially when you get into object-oriented Scala that we didn't really get into. But again, from O'Reilly, Learning Scala, really good introduction to the Scala programming language. It's how I learned it, and pretty easy to get through. I just sat down and read this puppy cover to cover and came away with it being able to actually write some Scala code. So that's saying a lot. And if you want to learn more about applying machine learning using Spark, if you're going in that direction, this is a really good book, Advanced Analytics with Spark. Recommend that one highly, and it goes into actually implementing more complex machine learning algorithms using Spark and MLlib. So we only touched on a couple of examples of that in the course. There's a lot more to explore, and this book goes into that as well. Beyond books, obviously there's the Spark website. So you can go to spark.apache.org, and they have all sorts of resources there for you to look at, including the latest news on the latest releases. And Spark is still a young technology, so it's still evolving quickly. You want to stay on top of the latest developments. And there are also community links there. You can sign up for mailing lists and forums and see what other people are doing with Spark and learning from the problems and solutions that they're discovering. So there you have it. A lot of people ask me about career advice. Is taking this course enough to actually get a job in big data? Well, probably not. This is the first step, I would say. What you really need, though, is to get some experience in actually applying these tools and techniques. So I'd encourage you, if you aren't in a position to do so at your job today, do some freelance work on the side. Find some people who are looking for work on Elance or something like that, and do a few small jobs for other people that you can put in your resume and actually get some practice in applying Spark to real-world situations. Another good strategy is to position yourself so that you can transfer into a big data job within the same company. So one thing that I think is a great idea is making sure that you're working at a company that has the sorts of opportunities that you have. So if you have an existing skill set, say in software engineering, those skills are highly portable. Chances are you could get a job at a company that has big data. And if your ultimate goal is to do Spark processing or other big data processing, getting your foot in the door just as an engineer doing something, anything within that company is a great first step. That gives you a way to connect with the hiring managers that are actually running those parts of the business, and maybe you can talk to that hiring manager about what sort of skills and transfer paths are available to you to actually transfer internally to a role in big data processing. That's often a much easier thing to do than trying to get these jobs from the outside where nobody knows you inside the company yet. So a couple of career hacks there for you that hopefully are useful. And there you have it. I wish you the best on your journey in Spark and big data. In the next lecture, I'll talk about some more resources that I offer for continuing your journey on learning about Spark.